to use tests with Dafny, and they're both like JUnit-like a test harness that you can use just with the Dafny test command. You can generate test cases, and the generation of test cases, that's done through the verifier. That is, you get semantically generated test cases. But then if you look around, you would think that, well, shouldn't there be a quick check for Dafny? Well, there isn't, to my knowledge. So maybe if you have some interest in that area, you might put that together. There's an auditor that's being used for Dafny programs. The auditor checks that the features that you use with Dafny that could be where you could be skating on thin ice, that they are highlighted. And where are those in a verified language? Well, they are at the foreign function interface. So if you want to interface with Java code, with JavaScript, with Go, Python, C#, and even Rust, and maybe KML, then you're going to write some specifications for those in the foreign function interface. And there we have found lots of errors. People write specifications that are just not correct, or they're the specifications that let them assume false, and that's bad. So the auditor checks for such things. Some development groups at AWS and elsewhere use interface description languages, and there's one called Smithy that's used a lot at AWS, and that connects with Dafny. If you look at the encryption SDK, for example, you will see that a number of things there have been generated by Smithy Dafny. Another feature that perhaps should have been there a long time ago is what I'm calling here a boogie extractor. So in the implementation of Dafny itself, there are a number of axioms that have been handwritten and these axioms axiomatize things like sets and sequences and things like that in the language. And when you have those, there could be errors. And indeed, there was one problem with the axioms for multisets that someone detected a couple of years ago. But now you can write. The part of the Dafny implementation is written in Dafny itself, and some of these axioms are formalized in Dafny with a model, and then you prove as theorems the things that become axioms, and they're extracted into Boogie. There is a standard library, and Dafny is this month. I think Dafny is 17 years old, which is staggering for me to think about. And you would think that the language that's 17 years old would have like a huge standard library, but that's not the case. There is one that's small, and there are a number of parts in it that when you try to use them, they're really not really so great, and they don't show the best Dafny style. These have to do especially with lemmas about arithmetic, some about the collection types and things like that. And I think we need a new design. They're not following the guidelines that we ourselves promote for example, avoiding quantifiers in particular ways. There are ways that you can write things without having them around. So there's a lot more to do there. And you would think that even like an I/O library, that should be there, but there's only small pieces of that. Okay, so another good thing that has come into being in the last year, maybe a lot was added in the last year, but it's been there a little bit longer, are project files. So when you have a Dafny project, you can have a project file, and that's something that you sort of would expect. And I think that's interesting again that if you think of languages that are new, were new in the last, say, 20 years, Go, Rust, what have you, you immediately get like a build system and like a package manager and project files. And Dafny hasn't had this, which seems a little bit odd as well. But I think that comes from that the applications that you tend to go to with Dafny, a lot of them are built up from the ground up, and the people have developed their own tools for this sort of thing. And of course, we'd like to do that heavy lifting. So now I'm very happy that there are configuration files. There used to be, well, actually still is, but it's not needed anymore, the include directives. And that's one of these things that as a language designer you put in because it's needed at some point, and then you realize how much it's misunderstood, and it was just a terrible idea. I should have designed configuration files long ago, but luckily other people have at least done it more recently. We've also changed the command line to be like a verb-based command line, which feels more modern if you happen to use things from the command line. Okay, so now I'm going to go into a number of slides on the language itself and how things have changed, and some new things in the language, and it really centers around, or many of the things center around types. So this font looks like it might be a little bit small for the back of the room. Is it all right? Okay, good. People with good eyesight are in the back. So essentially, so what I'm going to do is I'm going to give a brief overview of, or brief, several slides, but not going to all of the details of the types, but an overview of the types in Dafny. So it all starts with the 5 groups of types on this slide. So there are basic types like you would expect, integers and booleans and things like that. There are bit vectors of every length. I never have liked bit vectors, but I mean they have to be in the language. But you would use the bit vectors if you do like bit twiddling operations. You wouldn't use it for like bounded integers or arithmetic, whatever. You would use integers for those. And there are immutable structures like inductive data types, or what I call algebraic data types, and they exist in both inductive and co-inductive variants. Not so many languages support co-induction and co-data types, but Dafny does. And there are tuples, which are just a special case of data types, but with a special syntax. Then there are collection types that are built in, and this is important for the language itself because you need sets to describe certain modifications. So these had to be in the language, but it's also quite convenient. I mean, a lot of specifications use these sorts of things. And so you have finite and infinite sets and finite and infinite maps and sequences and multisets. There are also arrow types, and if you're familiar with an interactive proof assistant, many of those are based on higher order things, and you can't even say the name of the proof assistant before you get showered with lots of lambda expressions and things like that that you have to write, and monads and stuff. That's not the case in Dafny. I mean, Dafny has been, looks more like an imperative language, but of course it does support all of the functional features. So, and in specifications in particular, there are a lot of, you would, essentially write them as functional programs. So there are function values, or what you might think of as lambda expressions, but they don't have to be, they could be top-level functions as well. And they're all monomorphic, even though Dafny supports polymorphism, all of the arrow types are monomorphic. And finally, there are reference types, and reference types were in the language from the beginning, and that's essentially classes and arrays of any dimension. Okay, so these are like the basic types that you get everywhere in the language, but then there are things that you can do with these types to create other types. So, oops. And so in the last 2 years, maybe 2.5, is it longer? I don't know, 2.5 years. We have re-implemented the type inference in Dafny. And I must say that, there are lots of things going on with a verifier, and you might think, okay, a verifier is very difficult. But for me, I think the hardest thing I have ever implemented has been the type inference. Both the previous time, like 7 years ago, and now the re-implementation. This is really hard to get right, because to get the inference, you rely on heuristics. So the new type inference relies on many fewer heuristics than the previous one did. But the type inference is difficult. So you can get the new type system by using these 3 command line flags, and several of our users at AWS are using these. So actually, this has been in use for actually well over a year, but we're going to make those the default soon. And so what I'm going to talk about on the next several slides assumes these flags. Okay, so There are subset types in the language. Other languages have different names for this, refinement types, predicate subtypes, whatever. And essentially what that means is that you can declare a type it would have some sort of base type, and then you give a constraint. And the constraint is just a Boolean expression that you give. And this has been used quite a bit in some other, some of the proof checkers. PVS makes heavy use of predicate subtypes. If you go to an interactive proof assistant like Rock, you get a lot of these as well. And so they exist in the language. The difference here is, if you compare to, let's say, F star, which also has these sorts of things, is that the types themselves are only checked by the verifier after the type checking is done. Something like F star performs the type checking as you go along, so the two are more intertwined. But in Dafny, the constraints really happen afterwards. So there are some built-in ones like nats. So the natural numbers are just a subset type. They're not defined inductively in Dafny as you would find in some proof assistants like Agda or whatever. And there are some extra arrows like partial functions and total functions. They are defined actually as subset types over the more general arrows. You cannot, a type cannot depend on mutable state. That's something that people have tried, but it's very difficult, and it's not in Dafny, and I don't see that it's ever going to be in Dafny. And subset types cannot declare members, and the reason for that is that it would be ambiguous which member you would be referring to. So whereas most types can have members when you declare them, subset types cannot. And here's an interesting thing with the type system, which makes type inference more difficult as well. And that is that if you have a type, let's say, like nat, which is a subset type of integers, of course you can assign a nat to an int, as you would expect. But you can also assign an integer to a nat. So the type system is totally fine with that. And that may be shocking, but it's not so shocking when you realize, well, the difference is going to be made up for by the verifier. So if you have something that goes sort of in the wrong direction, if you will, then the verifier is going to check the constraints. But as far as the type inference and type checker are concerned, you can go in both directions. So in the verified language, when you have subset types and inference like that, you want something more than sort of principal types. In some languages, if you get some kind of, or I shouldn't say that. I should say you wouldn't be satisfied with just something that is going to satisfy the type checker, unlike in other languages. I should have said that instead of principal types. And so here's an example. Suppose that you have a quantifier, and you say for all x, p of x holds. Well, if you infer the type of this to be integer, if the type of x to be integer, that's different, then you're saying something different than if you inferred the type to be, let's say, nat. Because if it's nat, then you're only saying that p holds for just the non-negative integers. And so this matters. And in the new, Dafny used to do this differently, but now the new type inference, any inference of a bound variable like that is always going to be the base type. It's never going to be a subset type like nat. Okay, so those are subtype. Yes, Brian. Yep, thank you.
Even if P takes a nat as an argument.
If P takes nat as an argument, the type will still be inferred to be int, so that means you will get an error there. And so two things you could do is you could either declare the type as nat explicitly, or you can put an antecedent in there. Yeah. So that used to not be the case, and but it wasn't quite consistent when this happened and not with the previous type checker. So now it's consistent, but in some cases you have to write more. Yeah. So I think that's a kind of problem that that I think languages that don't look at the quantifiers like that wouldn't see in the same way. Okay. All right. So subset types have been there also for some time. I guess for about 7 years. And traits have also been in the language for some time, but they had started off very simple. So the traits can now do many more things than before. So, I should mention that the traits, they're like sort of Java interfaces or like a little bit like type classes in Haskell. And a difference from many other languages is that they can have data members. That's not all languages support that. So something that's new in the type system is that now it used to be that only reference types, only classes could implement traits. And that when I think, man, I mean, little world I was in when I designed that years ago. I mean, it should have been any type to begin with, and the new type system supports that. So traits can now be implemented by, well, almost any type. It cannot be implemented by a subset type, again, for the same reason that subset types cannot have members. And if you want to, so that means that you have traits that could be reference types or not. And the way, if you really need it to be a reference type, which actually is not very common, but if you do, then you just say that the trait extends object, where object is a built-in trait that says this is a reference type. And of course, all classes, they automatically extend object. So the traits has been, I mean, getting this into the language was something that we really wanted to do, and this really required rewriting the type inference engine, and that was sort of what started all of that work. Okay, so the language also supports derived types, or what Dafny calls new types. And what that means is that you can declare a type, in this case n, and you say, this is just going to be like some base type. So why would you declare that it looks like a type synonym, but it isn't? It's saying that you're going to have that the new type n is going to have the same properties as the base type, but it's a separate type. The two don't communicate unless you do some sort of explicit cast between them, and this is something that's used if you want to have bounded variables in Dafny. Then you would declare your own kind of integer and set that aside. And then the compiler analyzes some things to determine that, oh, this thing can actually fit into, let's say, 32 bits or whatever, and then it's going to compile it as such. Because the new type separates the type from the base type, that means that the compiler has the freedom to choose a different binary representation, and that's what we do with bounded integers. But people have wanted to use these for a lot of other things, and so they exist like that. And you can declare members of new types. And new types didn't always support type parameters. That's new in the last, I think, year or something like that. And what's also new is that the base type, it used to be that it could only be integer base types and real base types, but now they can be any type or almost any type. They cannot be traits and they cannot be reference types. The reason they cannot be reference types seems that, well, if you want a different reference type, you would declare a different class. But there is one exception, actually, and that is that data types are not allowed to be a base type. That is, you cannot base a new type on the data type. And the reason for that is just that when I got to that point in the implementation, there were no requests for that at that time, so it dropped off the priority list. I would love to see that, actually. I mean, it would all fit in to doing it. It will just require more implementation. And actually, as always, one finds there are parts of the design you have to redo, but that's also a project. I mean, this is a substantial project for let's say for a student, but it would be a great one to have. Now, a new type, you would think that the new type could extend traits, and that also makes perfect sense. That is, you declare your own type and you say that it extends some traits. And this too is the thing that when I got to that point in the implementation, it turns out, well, you need to change the compilers so that they would support fat pointers in general. So fat pointer is something that tells you the type of the thing and its value. And we sort of have that in for the compiler to Java, because in Java you have like the lowercase boolean and the capital boolean, and the lowercase integer and the capital integer, and we support those sorts of. The compiler to Java understands those differences. But it turns out that that if you want to do this in general, this touches many more parts of the compilers. So again, when I got to that point, we did not have requests for doing that. so I stopped and diverted my attention to other things. But that's something I would also love to see in the language. So these two are kind of like, I mean, if you think of like matrices of I mean, what can be supported with what, I would love to plug those so that these didn't have to be exceptions. All right. Now, something that was pointed out to me sometime during the last year is that a new type can also define a constraint, just like a subset type, and sometimes that causes some confusion. And but now that the new types can be based on anything, you actually don't need that. You could think of a new type as always having the form that I have here on the slide, that you just take some existing type, which perhaps the base type is a subset type that has constraints already. That means that there's no reason for a new type to also introduce constraints. So that's something that well, whether or not we change that in language, I think that there's a mental switch there. Well, especially for me, but perhaps for others who have used the types as well, to think of them that way. All right, so part of what you can do in the language. Oh yes, please. Yes.
So Brian pointed out a question earlier about the NAT type and you have a for all x. Brian pointed out a question earlier about the NAT type. If you have a for all x, p of x, and p takes in a NAT, and x is assumed to be an int, you need to either declare the type of x or have an antecedent. Mm-hmm. So if I'm understanding this right, if we have a new type for NAT, we would not need to write any additional annotations.
Correct. Correct. Yep. Okay. Thank you. A great question. So the subset types are different because there you can assign them in either direction. So things can become ambiguous with I mean, number of things. But for new types, then it's understood what it is. So if they happen to have some base type, I mean, with the constraint, and everything is understood. I mean, what you would get, and that there you can do. If the p that I had in the previous slide took a NAT, well, you can still pass in an integer. But if p took a new type, then you would not be allowed to pass in an integer. You can only pass in that new type. So it's unambiguous in that way. Yeah. Thank you.
So I was curious about this thing where you said that traits could support data members, yep, which I feel makes them somewhat different from what traits are in Java or yep, something like this, because like interfaces definitely can't, right, and this seems to be fundamental to the multiple inheritance aspect. Like you need to have fat pointers already in order to support, like, what does it mean for a base type to have mm-hmm, those members, for instance?
Right. So, indeed, I mean, if you look at like interfaces, subset types, I should have also mentioned mix-ins and traits. If you look at them in different languages, those terms are used a little bit interchangeably, and they in different languages they have different feature sets. So in Dafny you can have data members, but if you think of the data members in the trait as being a getter and a setter, then it's not so strange anymore. I mean, because then they are, I mean, essentially methods in the trait. And but then the thing that Dafny does is that if you extend a trait that has a data member, then it will give you storage for that in the type. So for example, if you have a class, it will add in storage for that, so you don't have to redeclare that and redeclare the getter and setter around that. So so in that sense, I don't think it's so odd to have them. Yep. Thank you. Great. All right. Let's see. Okay, so right, so type checks and conversions. These have existed in the language before. However, they didn't cover. I mean, they were really spotty in what they supported, and that's much more consistent now. And I'll say something more about the type test on a later slide. But this is more consistent now than what you had before. So there are type parameters in the language. They've been there for a long time, almost from the beginning, actually. And the type parameters support things that you might think of as usual things. You can have variants, like you can have covariant or invariant or non-variant parameters and so forth. There are also modes of type parameters for cardinality preservation, which in some other contexts are called like strongly positive and whatever, which actually I think is a terrible term. It has nothing to do with positivity. It has to do with cardinalities. Anyhow, but then there are type tests that you can then do on the. If you have something whose type is a type parameter, you could think that perhaps you could do a type test on that. Well. That's not always actually that's not allowed on the type parameters. So in Dafny, once something goes in as a type parameter, you cannot figure out or recover what that type is. Unlike in most object-oriented languages, at least, you can check at runtime what it is, but you cannot in Dafny. So Dafny, as such, supports parametric polymorphism. So parametric polymorphism essentially means that whatever you put into that type, from that point on, you don't know what it is anymore. It's really parametric. And something I have to say about that is that, well, that's actually great for when you compile to different languages, because Java doesn't really support type parameters. It sort of pretends to a little bit, and some other languages don't have such type information at all at runtime, and we compile to them. So it's actually convenient that we have this parametric polymorphism. But if you think of it, I think that if you talk to a type theorist, they would say, of course, this is a good thing. Of course you should have parametric polymorphism. And I've been of that mindset as well. But really, when I start thinking about it, well, why? I don't actually know. Other than the compilation issue, but that doesn't seem right. So if someone in a coffee break could tell me really why do we even care about parametric polymorphism, then I'd like to hear. Okay, so a new feature for type parameters is that they can have bounds. That is, you can have bounded polymorphism. So here's a method that declares a type parameter t, and it says that it extends some trait. And the things that you can use as bounds are either traits or subset types thereof. You can have multiple bounds if you want to. Now, there are a couple of things that are not as smooth as they could be. One is that when you use these, if you use, so x in this example is declared of type t, but perhaps you would like to use x as a my trait. Well, right now you have to do an explicit cast to that to be able to, to use it as a my trait, and that doesn't seem like it really should be necessary. So that could be a perfect project for someone. I think that's much easier actually, and also the fact that you could use only traits or subset types thereof as bounds. Well, why not allow it to be any trait? You could say that it's anything based on an integer, for example. That could be nice. That's not there. That could also be nice to add. But yeah, so bounded polymorphism exists. Okay, so I talked about types in many slides, and now I'm going to talk about some other features in the language. So one problem, if you look at the Dafny workshop last year, there was a whole session, I think 4 or 5 talks on proof stabilization. That is an issue that's called brittleness. And essentially what that means is that you have a proof that goes through wonderfully, and then you change something, or the tool chain changes somewhere, and now the proof, the automated verifier no longer finds the proof. And this can happen in any kind of verifier. If you think of a tactic-based interactive proof assistant that is going to use some heuristics to, let's say, unfold definitions. Well, maybe if it just had unfolded something one more time, it would have found a proof. And these things could change with a change in the tool change, or in the tactics, or in the program as well. But they've been more annoying to recover from in provers like Dafny. So we've paid a lot of attention to that in the last year, and more features coming up. I'm going to mention some of them here on the slides. So one is that, and this is now related to how you organize the proofs themselves when you write the proofs sort of manually in Dafny. If you have something that you want to assert, that is essentially you want to prove this, you want to check that there's certain property holds, then before, if you wanted to prove to prove this property, maybe you had to give some other asserts, and they would typically go before this assert. And that's not a nice way to organize it. You get these long chains of asserts that look like spaghetti code. And Dafny has supported for some time assert by statements where you can put the proof sort of inside. This is also good for as a mitigation for sort of proof brittleness, in the sense that proofs become smaller or more separated. Because the proof of this property is done sort of separately and then forgotten. So whatever proof details or whatever things that you need to pull in to prove this property are, essentially like the proof of a lemma that happens elsewhere, and so that they don't confuse the verifier any further. So this was a good idea. So this idea has been extended to all statements of the language. And there's also a change in that it used to be that assert by the proof would only be of the property itself, but not the well-formedness of that expression. So what I mean by well-formedness is, suppose that the property that you write down there divides. Well, you're not allowed to divide by 0. So somewhere you need to prove that you're not dividing by 0. And maybe you'd like to give a separate proof for that as well. And now that proof also goes into the by clause. And that's the same for all of the by clauses. If you want to organize some proofs of code to help the verifier more, you can use the new opaque code blocks. These have existed in VCC, the verified C compiler from 20 years ago, for example. And essentially, what it means is that you take a piece of code, and instead of refactoring it into a separate method somewhere else that you call, you just do it inline. But essentially, you get to write a specification for that code block. Another feature that we have is that you can hide some definitions. So Dafny tries to, whenever you have functions, it tries to unfold those functions automatically for you. And many times this is just a really great and convenient feature, and one that perhaps people coming from an interactive proof assistant where you have to do everything manually is surprised by. But sometimes this gets to be too much. If you have functions that are very large and they get unfolded, maybe you don't want that, it sort of confuses the verifier more and proofs take longer. Well, you can now, there was a mechanism before where you could mark a function as opaque. That mechanism is still there, and then you can reveal them. But here you can go the other way around to hide things. And especially hide star, that is hide all function definitions, is something that a number of our users are using to really speed up a number of proofs. Also when you're working with proofs, ideally, the IDE would take care of, would know where you're editing and would just spend all of its efforts on proving the thing where you're spending your thinking time. But that's unfortunately is not the case still, even after many years with the IDE. It's doing more caching and other things like that, but we still have ways to go. And so what you can do is you can mark something as only. And this is something that you would do temporarily. Let's say that you're working on a particular method or lemma. You could mark it as only, and then when the verifier runs, it's only going to check that one. And that sort of speeds things up, but it's a manual effort to put that in there. But it's something that's also being used in good ways. So these are some of the proof organization things. But all of these, I like the features that go for proof organization because they make sense in the language. They give you a way to express your proof. You're saying, here I'm going to assert this thing, but here's the proof, and you can sort of abstract over the proof. Some of these other ones are more like mitigations, and I like those less. But of course, if you want to stop mitigating or have a smaller need for mitigating, then the verifier needs to be better in various ways. And here we're putting some effort into improving the logical encoding of some things. So Dafny, being now 17 years old, the basic form of things are still as they were from the very beginning. And we've learned a lot about how you put things together to create verification conditions. So we've done some cleanup just recently. There's something called can calls, which you can think of as as a certificate that says, sort of a proof certificate that says, I am allowed to use this function definition for these parameters. That's also been not the language, it's been in the implementation for a long time, but it wasn't used exclusively. So really we got no benefit from, or not the full benefit of these can calls. And in fact, if anything, these can calls were provided as a disjunction to other things. So maybe we just really made things worse. And just as of this month, we've put the can calls are now the only thing governing the sort of these preconditions to functions. There are directives that we use to tell the verifier which parts of a proof could be used. Some of you may know these as triggers or matching patterns. And it's important to have those in there so that you can steer, that you as the tool developer can steer the verifier. And there were some places where these were not used. And one place that actually we, embarrassingly enough, have known about for a number of years and still not done anything about is in the induction hypothesis that's generated automatically. So it means that every lemma that you wrote, we produced an induction hypothesis and did not give any directives to the solver to say how this should be used. I mean, a terrible thing we should have fixed long ago, but it's been fixed. And there have been some other places like that missed triggers that we've fixed. We're going to look to see where else we're missing them right now. We're going to do some other changes coming up. There's a concept of fuel that's been very important in the verifier. And we're changing the encoding of that in a way that I think will make a big difference for how we encode or how these triggers play a bad role in various things. I think that we will get around that by this new encoding of fuel. Now, the fuel that we've used, there was one result that actually Nada Amin, who was going to give the keynote today, she contributed to Dafny a dozen years ago and implemented the fuel parameters, but also implemented a special, actually she implemented a special track of the fuel parameters that meant that if you invoke a predicate with literals, let's say, or a function with literals, let's say that you want to prove something about the Fibonacci of 12, I mean specifically the literal 12, then it would, the encoding would let the verifier just unroll that function all the way to the end, which I thought was just super cool, and it's been used a lot and it's sort of on automatically all the time. But we've noticed that this costs a lot in performance. So I've had on my to-do list that we should remove this until something that happened more recently where I've found some bugs in Z3. And I think that it could be that the problems that we saw with the performance of these were due to a bug there. I don't know. We'll have to investigate. Okay, so here's a difficult issue that is still needs addressing. And it's an issue that arises in a language like Dafny or like Java or like any other object-oriented language, but does not occur in functional languages. So people who do more, proofs of things that are all immutable things, they don't see them. And if you do Rust, Rust is really a functional language. You also don't see this issue, but Dafny has it. So let me describe what it is. If you suppose that you have a class with a field, and you have a method here that takes one of these things, C, as a parameter, and it allocates a new one. Well, you and I as programmers, we would know immediately that, of course, this C that we just allocated here is different from that D. We got the D before, and we're newly allocating the C. Of course, these are different. But proving that they are different is it takes a lot of machinery. If you look at Tony Hoare's paper of his axiomatization of Pascal from must have been 1972. All good things were done in 1972, I think, right? He has a very simple way of handling this that does not work with what if the parameter here is a set of C's instead, or some other data structure that further down has some C's. Well, those are also allocated, so they will not be equal to this new C. So Greg Nelson and I had called this sort of thing in the when we did the extended static checker for Modula 3 in the mid-90s. We called it the alloc morass. And it's still the alloc morass. I mean, this is a terrible thing. And you also need it in one other place, and that is that when you update some data, you would like somehow this method needs to be allowed to allocate new stuff and update its fields. Well, what gives you that permission? Well, that's also tied into allocatedness. And because of those two things that seem rather minor, we get lots of things that we have to axiomatize about allocatedness, and it's really uncomfortable. Yep. Oh, just wait. Yep.
Isn't that just separation logic? If you have separation, like when you allocate, you get a new object.
If you have separation logic, then you don't have allocation in this way. So in separation logic, you treat the heap as essentially you have many different small heaps, and that's also what you do in Rust. Well, Rust is really a functional language. You don't have the updates in that sense, but that means that when you get something new, you have another piece of storage for it. Whereas here, it's the same old heap as before that you have. So if you have something that allows you to interchange the pointer C and D, then you can get this issue.
But this is not really a language feature; it's more of a reasoning feature, right? It's not about Rust or.
That's true, right? Yes, okay. Yes, it's a reasoning feature, and it's prevalent all over the. Dafny does not introduce, a separate logic for verifying programs. It just uses, standard techniques that have been around for, decades. And with those, you have this issue. I'll have one bullet later that I'll say one more thing about this. But yeah, thank you. Okay, so that's still an issue. My last bullet on this slide is on bugs in Z3. And I must say, in the last many years, sometimes we run into problems with instability and you look at it and you go, oh yeah, right, we're converting between bit vectors and integers. Z3 is terrible at that. And so we understand that it's not going to do it well. Or yeah, there's nonlinear arithmetic here. Okay, we understand this is not always going to work, whatever. And then we have very large examples, and there are quantifiers kicking around, and you go, okay, all right, so it didn't do all the things right. So I've given up too soon for these things. In the last several months, there have been 3 cases where I've drilled down to the Z3 level just to prune things down manually and rather painful, I would say, and found that there are bugs in Z3. The most recent one I found about a week ago actually turns out to be fixed or at least I can't reproduce it in a newer version of Z3. But the other 2, one of them was, I had a bug report that it's been fixed in the newer version, and another one is in discussion right now. But I think that some of these bugs in Z3, they were incompleteness bugs, not soundness bugs. But things where you expect that Z3 would produce the proof, and you change something minor that has nothing to do with it, and now it doesn't prove it for small examples. So that certainly should not happen. So we're going to be more proactive in actually reporting these to get these things fixed, so we have a more stable basis. Okay, so there have also been a number of other new language features, and these are smaller things, but let me list a few of them. You can put attributes on things in Dafny, and that's something that is always super useful especially for third-party tools or whatever. You can say extra things, and many other languages support these with different names. And the syntax for that in Dafny has been curly brace : before. But now we have an additional syntax, and we'll see, I mean, if we keep both or just go to the new one, with an at syntax. So that looks more like the ones, like the attributes in Java, which are called something else. And an advantage of doing it this way is that now we're checking that these are really declared types in various ways. So we can do more checking on them. And that's something that the C# and .NET has done for a long time. We support parameter default values. This feature is probably more than a year old, but one that perhaps not so many people know about. So you can give default values, and these can depend on each other. That's not all languages support that. And you can call them by binding the parameters by name if you want to. Actually, what you can also do, which was a feature requested in Dafny, is you can mark a parameter as being name only. And what that means is that if you can't pass it in positionally, you have to name it. And for some people, that's been an important sort of style thing to make sure that when they go from version to version, that things are done correctly. There are decreases to and decrease and non-increases to expressions. What these are is Dafny builds in the well-founded order that's used everywhere to prove termination, which is a surprise to some people that you can actually have a fixed such order, but that works very well with Dafny. Essentially, the user maps into that ordering. For most of those expressions, if you wanted to write the condition yourself that something is smaller than something else in that ordering, you had to then know what that ordering was for those types and then write it yourself. And in at least one case, you couldn't actually express it even. And now you can with the decreases to expressions. So this was added in an effort to, we want to be able to, when something fails, we have a little light bulb that pops up in the IDE. And if you click on that, you can say, give me the assertion, give me the condition that really fails, so that you can start working from that condition. Now that feature is still an experimental feature. It's not always working, but that needed decreases to clauses because that was the one thing that you couldn't express in Dafny itself. There's a minor feature, which is that if you've used for all statements before, you could not use them in expressions before. You had to wrap something around it. It was painful. That's been fixed. And we're stricter about some things. If you have a method or a lemma without the body, for example, before you could do that, and you would just get a complaint from the compiler later on saying that, hey, I can't compile this because there's no body for it. And now we're stricter about those things. You have to mark them as axiom if you to sort of acknowledge that you know that it's there without the body. Okay, so I have a long wish list myself of features that I would like to see in the language, and I'm going to run through them. I will not have time to go into all of the I'm sure very interesting details about all of these. But let me go through the list. I should say that this list, for some of these features, no one has particularly requested them. I just think they'd be really great to have. For some other ones, other people have even fleshed out some proposals for how to do it, and I would just, so here I'm just endorsing those. Okay, so first one on my list is adding, well, what to call them, both regions, linearity, uniqueness to the type system. This is something that the Linear Dafny project had done a few years ago now. I was quite inspired by the regions there. So a region is essentially, think of it as your subheap. So if you have a subheap, you can declare, you can allocate things into it. And the intriguing thing is that if you put a subheap as one of the fields in your object, or as one of the fields in a data type, for example, it is just one field. It's not like a deep structure. Of course, inside it has a lot of structure because you have lots of things that are allocated in it. But it's just one thing, and this helps abstractions, and it simplifies specifications. and which I think is a really great thing to try to achieve. Now, you can also hope for better verification performance because you've separated some of those things. You could hope for compiler optimizations. You could perhaps do some inline updates, that is, in-place updates of, let's say, sequences or data types. And here I'd like to make another comment about the linear Dafny paper. So if you read that paper, it seems the reasoning there is to say, if you start with a program that uses mutable data structures, so classes, and you specify them the way that you would in Dafny with dynamic frames, that can be problematic for the verifier. It can perform poorly, and you have more work to do. So then the paper seems to say, well, the solution to that is like linearity. And that's not actually what the paper does. I claim Brian is here; he can fight me. But I think this is misstated. What made a difference in the performance is going from mutable data structures to immutable data structures. But it's just that, well, if you have immutable data structures and everything is copied every time that you want to sort of update it, that gives you bad performance. No one would want that. So there, linearity kicks in, and linearity essentially is what allowed the switch from the mutable data structures to the immutable data structures. So I don't see the linearity as a solution. As a replacement for dynamic frames. It's if you have immutable things, then that's useful. Now, linearity is also useful for mutable data structures. So there are a number of things that one can do. Separation logic was mentioned. That has some sort of similar features. If you look at Viper, for example, Viper makes good use of that, the connection of Rust and these features. Now, Rust has linearity in various forms, and there are forms of OCaml that have it now as well. And of course, if it's good for those languages, then there's useful programming features, and you can do concurrency better. But you restrict the programming model. And what I think is really, amazing is that, as a programming language designer, what you try to do is put restrictions on the language so that you can avoid certain kind of errors and make things smoother in other ways. And a type system is like that. For example, we have a Boolean type and we have pointer types, and you don't mix them. And maybe that's amazing that as programmers, we don't have a reason to have a variable that sometimes holds a Boolean and sometimes holds a pointer, unless you're a Python programmer, maybe. But most of us don't, and that's amazing. What's amazing here is that you can actually have linearity, that you can write a lot of programs without having two pointers to a mutable thing. I think that's just amazing. Anyhow, so this is high on my list, but it's a big project, and and as the Dafny team, we've had this has been near making it as a goal for several years now, but then something drops off, and it's not the most important thing for our users. So it's taken a back seat. I would actually like to see more systems programming features in general. For example, allocating manual memory allocation and other things like that. A feature that I would really like to see that I've been discussing with Peter Miller is the naming quantifiers. So I think that if you could name quantifiers, you would have a different model in how users would interact with quantifiers. Essentially, it's saying you name your quantifiers, and if you want to instantiate them or give witnesses to the quantifiers, okay, you have a name for it. Just use the other standard mechanisms for doing that. But if you don't give a name for it, well, we're going to try to give some automatic witnesses or some automatic instantiation sort of rules, which some of you may know as triggers again. But by focusing it that way, then it really says you are in control of these things. Name your quantifiers if you want control. If you want Dafny to try to control it, well, don't, and we'll do our best. But that means that if we don't find a trigger for a particular quantifier that you write, you always have a way out. Right now, we produce a warning message, and that warning message is usually ignored because the moment you introduce the quantifier, everything seems to be okay, and then later you run into trouble. So this is something I'm excited about. There are a number of things, when you put constraints like on subset types, those constraints, in my mind, they've always been like ghost constraints. They're not there at runtime. But now, actually, we detect when we can compile them, and we compile them sometimes so you can do runtime tests and so forth. And this is odd in the language. It doesn't fit. It would be better to have these be declared as such. And furthermore, it causes a number of problems early on when you try to figure out, when you try to bootstrap the resolver and type inference and stuff like that. This would be much easier if we had declarations. But if we have a declaration, then it would be compiled by defaults, which is a switch of sort of methodology. And we have some other things with auto init that are done by default that probably we should change. There's some other like just nice language features. One that the people complain about or are surprised about is when they use the sequence and array constructors, they often have to write specifications for those like lambda expressions that you put in there. Well, there's a way around that I would like to see. And then often when you work with, especially sequences, but also arrays, you want to talk about the last element of something. Or I'd like to see a syntax where we give that, where we simplify the program text. You don't have to write so much. It's a less important feature, but one I'd really like to see. We've talked about function values in Dafny, and I think that we've gotten the semantics for those wrong, because the semantics of the function values include what a function reads from the heap. I think that should not be part of the semantic value of it, and that I think could fix a number of things. I mentioned traits, and there are a lot of things you can do with traits. One thing you cannot do is after the fact say that type supports that trait. You can do that in Rust, for example. You can do it in Go. I'd love to see that. There's something called type characteristics in Dafny, and many people have commented, well, aren't those just like traits? Yeah, sort of, so we should do that conversion at some point. Okay. Oh, yeah, and I had two more on the slide. Thought we were done. It has been suggested to have type invariance. So before I did Dafny, I worked a lot, with Peter Miller's and others on like object invariance, and there we dealt with mutable states. Things get very complicated once you really get into it, but the type invariants here that I'm talking about are things for immutable states, so they don't change. And those are much easier, and they still have several uses, and people have requested them. So that's something I see as going in. And I haven't talked much about IDE support. There are a lot of things that we could put into the IDE that's not there. But I think IDE support for writing proofs is something that would be nice. Many people request, they want to see the proof context. Well, the proof context is implicit in the data flow and in the control flow of the data of a Dafny program, up until some point where you start using functions and unrolling them and so forth. So showing that proof support, that proof context, is something that would be nice to do, and it can be done because all interactive proof assistants do that, but they don't have the automation that we have. And they typically work on an embedding of the program that you want. Sort of, it's like you're eating your food with rubber gloves or something like that. I don't know. Anyhow, so that better IDE support would be great. Okay, just one comment about the SMT solving. So SMT solving powers a lot of things that we do. And it's what gives us that automation, and I think it's a great technology. We make heavy use of the matching patterns for quantifiers. In fact, we don't use many of the decision procedures that are available. We use arithmetic, we use uninterpreted functions, and we use quantifiers. That's essentially it. People love to develop all sorts of like string theories, data types, array theory of arrays, all sorts of things people want to somehow put into decision procedures. But we're quite happy just encoding them as quantifiers. But we want those quantifiers to work. And there it may be the case that I'm the person on the planet who has worked with triggers the longest, because I started in the 90s, where they were implemented in the simplified theorem prover that we were developing as part of the extended static checking project. Still, I was surprised in the last, year or two of a number of things that I found in the way that things work that I should have thought about but didn't. So an SMT solver does lemma learning or clause learning. And when it does that, it pays no attention to triggers. And I can understand that because the triggers have to do with terms, whereas clause learning has to do with like formulas and clauses. So still, I had totally missed. And so I was really surprised by some proofs that went through and I really thought that they shouldn't. Which actually, that seems like a good thing if more proofs go through, but it's a problem because if you have two execution paths, let's say, and the SMT solver happens to look at one of them first, well, maybe it then finds the proof of the thing that follows. But if it looks at the other one first, it doesn't find the proof and it complains. So that's an issue of brittleness. So anyhow, I think it'd be really great for someone to rethink SMT solvers, that is, rethink the sort of the formalization of them. Many people, I can think of Shankar and a number of people have made beautiful presentations of what like all of this clause learning and how an SMT solver really works and how you do the backtracking and the non-chronological backtracking and stuff like that. But I would like to see such a simple framework, but with quantifiers added. In fact, I would like to see a minimal SMT solver. Think mini-SAT, but SMT and quantifiers. So mini SMT cube, whatever it would be called. But to just do those. I mean, forget all the other decision procedures, but give me quantifiers, because we need those. And there are other things. I mean, triggers, when you start working with them, they kind of work like just matching rules. So there's a whole big community that does rewriting. And this sort of the egg tool by Zach Tatlock, for example, and others at UW have developed that into a tool. Others have too. And there's been some proposals from Ranjit Jala and Niku Bazu and others about how you can think of like having more guards than just the syntactic triggers that we use. I think that some of those things would be interesting to rethink in this context. Okay, I think this is my last slide with some contents. So there are a number of open design questions and questions about how to do things technically and where to go with a project like Dafny. So one design question is termination of dynamic dispatch, and for that matter also termination of applications of function values. Dafny handles this in a particular way. The way that it handles termination for dynamic dispatch is that it doesn't allow it across module boundaries, which is, I mean, a very strict, too strict of a restriction. So there are solutions to these, but they have to fit into the language in a nice way, and we've not decided on what to do with that. And the first bullet here has been sort of open in that sense for quite some time. So that's something that needs to be done in some way. Dafny always checks well-formedness, and what that means is, again, if you divide by something, you check that the divisor is not 0. If you call a function, you check that the precondition holds. This is something that in tools that I've developed before Dafny was always the intention that we would do, but we never did a complete set of these things. And that means that you get a lot of strange errors, like something doesn't prove. And why doesn't it prove? Well, in the end, it turns out, well, it was because something could have been null. And I mean, in those checkers, because they didn't have the non-null types in the same way. But you're not living up to some restriction on the operators that you're using. And Dafny checks that. And that's been, I think, a great comfort that you know that it's not that because you had something that was not well formed. But a question is, well, when you have those well-formedness checks, should they be treated as the sort of a check and forget kind of variety, where the verifier will check it and then forget the proof of those things, that they don't sort of pollute the rest of the context? And That's not how it's done for most things today in Dafny, but it may be the way to go. So the question is, what should be the scope of those? And I think that's a sort of nice, well, theoretical, methodological question. Dafny supports compilation to a number of other platforms. I mentioned earlier in the talk that the encryption SDK now is written and verified in Dafny and compiled to and released as a library for 5 different platforms now. And it's a little bit odd to have that is, the fact that we do multi-target compilation, that has nothing to do really with verification. It's just that Dafny was a good language for doing that as well, because it's a bit more abstract than those other languages, so you can compile to them. And we've gotten a number of users that have picked a particular target, and that's what they want verified code for. I think the encryption SDK is the only one that has used 5 compilers. And but there's a question there: should that really be in Dafny, or should it be in some other language? And you would think that there'd be a number of programming languages that compile to many other targets, but that's really rare. So in that sense, maybe that should be kept in Dafny, but I don't know. That's a design question, and where to put our effort. I would actually love to see a native compiler for Dafny. Dafny verifies that certain things don't happen, but then when we compile to Java or .NET, for example, or other managed languages, you still get runtime checks for all of those things. It'd be really nice to have like a best of compiler for Dafny that would just do better performance-wise. And of course, we'd like to verify the compiler. This is something that we've made small steps towards for a long time. And now there's an effort at Chalmers to use CakeML as part of that mix to try to get to verify part of the compiler. Okay, so I went through lots of laundry lists of lots of things. I think maybe the more tutorial thing that I presented was, some parts of the type system, which has become rather rich with a number of things that you can do these days. And I think that with the applications that we have, both in the academic community and in industry, of how these sorts of things are picked up, it's not like it used to be a couple of decades ago where people just didn't know verification, or would mock you when you would mention it and things like that. But it's paying off for something, including something as big as and important as the authentication engine in AWS. So I think this is a great time to be in this area. There are lots of things to do in Dafny and in similar languages. And remember, Dafny is open source. Remember to teach using Dafny and prove good things. So thank you very much. All right, I'm happy to have questions in what do we have, 10 minutes before the coffee break?
Can you say more about the new fuel encoding?
It's one that I mentioned to you years ago. It's going to be a little bit more detailed. So, the fuel is a parameter that we use to say how many times the verifier is allowed to unroll function definitions, and it's usually set to 1. That is that every occurrence of a function, so every textual occurrence of it is going to be unrolled once. And I think that's a really great idea in most cases. But we've found that sometimes we need a fuel of 2. So in checking context, like for example in a post condition, we use fuel 2. And what that means is that if you have a large function, it unrolls it and then unrolls it again. So essentially you get a quadratic blowup. And most of the time that's really not needed, and we get lots of extra clutter. So this is a problem that we want to solve. So the way that the fuel is encoded today is that the fuel parameter is added as an extra parameter to the functions themselves. I'm talking about, this is under the hood in Dafny now, right? So you would pass in the fuel parameter. So if you have the Fibonacci function, it takes not just the Fibonacci argument that you want to compute the Fibonacci function for, but also a fuel parameter. Well, this is causing a lot of problems because then when we write other triggers, you have to be careful in matching that up, that fuel parameter up with other things. And so we've actually put in quite a complicated machinery in Dafny that would allow you to specify the fuel in various places. And this is also what causes us why we needed a fuel parameter to be 2 in checking context. So the better way to do it is to make use of the can calls that are now in place. So a can call is like a certificate, again, under the hood, that says, we've checked that these parameters in this context are good ones that you can use for instantiating the function. So you would be allowed to unroll it. And it would just make sense to, in that certificate, to also say, hey, by the way, you're allowed to unroll this 6 times or 1 time, or and most of the time it would be just once. So that means that these fuel parameters, of course, for fuel to work, they have to be part of triggers. But that means that the fuel will be part of triggers only for definition axioms and consequence axioms, not anywhere else. And that, I think, is going to clean up the encoding, and especially since we can avoid that fuel too, I think is really going to help. So, yeah. Yep.
Thank you. Could you say more about the boogie extraction feature?
Yeah.
Like what is extracted and under what conditions?
Right. So let's say, suppose that you have something that like sequences or multisets. Let's say sequences, and now you want to encode some axioms for that, so that the SMT solver, you want to tell the SMT solver what it can do about these things. Well, then you need to have some axioms that you would give it. So these had been written by hand before. Now, if you talk to someone doing interactive proof, like using an interactive proof assistant, they would immediately think, oh, well, we're not going to have these axioms, of course. We're going to write some sort of model for these things and then prove theorems about that model. And then those theorems that you proved, those could be used as part of the proofs. So what we wanted to do was to give a model for sequences and some other things, and then prove theorems about those models to say these things really hold. But then once we have those theorems, we want to give them to the SMT solver. And that's what the boogie extraction does. So it extracts those theorems that we have proved into the form that essentially that we can pass, that's part of the Dafny verifier itself. So of course, Dafny all the time takes any kind of program and translates it into boogie. So one might say, well, why is it different? Well, in the normal encoding of things from Dafny into boogie, it adds a lot of things like the allocatedness and the types and all sorts of things. And you don't want them there since this is part of the implementation. So therefore, the extraction feature is a cleaner, leaner kind of thing. It's specialized for this sort of thing. And one final point about that is, again, if you talk to someone using an interactive proof assistant, they would immediately think, oh, we should do this in some other tool. Well, of course you shouldn't. Dafny is a verifier. You should do it in Dafny. So these are done in Dafny. Yeah, thank you.
So if there are no more questions, then I will ask one question by myself. So I was wondering about the proof brittleness and about like the restructuring of the proof. Mm-hmm. And my question is like, how does restructuring or like the organization solves the brittleness in the sense that how do I know how many times I need to unfold, or do I need to do some more things?
Yeah, right. So a number of questions there. So one large thing that we have noticed where brittleness comes in is that when you have if you have, in general, larger proofs, then there's a larger chance of brittleness. We can measure, we get a resource count, which is a measure of how hard the verifier had to work. And we have found correlations between, if those resource counts are high, then we have a lot of variation and that tends to go with larger proofs. So then one thing that you would like to do is you'd like to make the proofs smaller. I mean, the way I'd like to think of it is that you'd like to give fewer things to the SMT solver so that it would get confused less often. I mean, otherwise it would say, ooh, squirrel over here. I'm going to like instantiate all of these things and unfold functions and do case splits and stuff like that. If you give it less things to look at, then you would be better off. So the features that let you compartmentalize the proofs, I think, are good structuring things. And I think, I mean, as programmers, I mean, we like to have extra methods. We refactor our programs. We don't like write long monolithic programs, and the same should hold for proofs. So those features are good both for organizing your proof and for reducing brittleness. So then your question was, well, how should you know, like, how many times you should, well, unroll things? And some people, they learn about, I mean, triggers, and then all of a sudden they think that they have to write all sorts of triggers, and they do, and they all, I mean, they make mistakes, and things don't work, and it's awful. So I think that all of those things should really be out of the way of the user. The user should not have to think about this. So instead, I would encourage you, when you have a proof and it doesn't go through, then you ask yourself, well, why doesn't it go through? Well, does it know this thing? Does it know this thing? Or you start writing the proof by yourself. And what we would like to do is that once you've written such, I mean, if you have to write the proofs like that by yourself, that it should be stable. But that's that's our responsibility to stabilize the proofs. But you may have to write manual proof steps. But when you do that, the question that you always have is not like, how many times should I unfold this, or how should I tweak the parameters? You write the proof. That's and you don't have to think about that in coding. So that would be my, or at least that's my design philosophy in, I mean, both for the language and for the verifier and the IDE, whatever. We should try to remove these from sight from the user, because users, I mean, don't do good things with tuning the parameters of things. Yeah.
All right, perfect timing. Let's thank Rostan again.
Right. Thank you very much.
The next session on proof stability and application starts in half an hour at 11.
All right, sorry for the delay. We're getting it pulled up here.
No worries.
Okay. Can you hear me?
Yeah.
The next talk is by Remy Willems from AWS on how to reduce brittleness in Dafny programs.
All right. Hello, everyone. My name is Remy. I'll be presenting this talk about helping users reduce brittleness. It's joint work between myself, Matthias Slijfer, and Olivier Poisson. First, I'll show you an example of brittleness. Then I'll show you a way to measure brittleness. Then I'll go over 3 features that have been added to Dafny that help Dafny users reduce brittleness in their programs. And then I'll conclude. So first, let me show you what brittleness is. So I've taken a Dafny proof shown on the left side, and it's just showing part of a proof, so lots of the statements have been left out. And I've made a small modification to this proof. So I've taken the statement on line 6, and I've moved it up a few lines, but this statement does not relate to the statements that I moved it over. So semantically, there's no change in the program, and we don't expect any change in verification. But now if we look at verification time, then we see that the program on the left consistently verifies in 11 seconds, while the one on the right consistently verifies in 16. So there is a change in verification. And now this change might not matter so much to the user, but when it comes to brittleness, the effect can be much bigger. So for example, a harmless change can cause a proof to suddenly verify 10 times as slow or 100 times as slow, or Dafny might no longer be able to verify the proof at all. And that's a big problem for users, obviously. So brittleness is when a small change to a Dafny program, one that seems harmless, can cause a big effect in the verification output. You can see that I've also noted these resources numbers in the bottom. So besides verification time, Dafny also emits resources used as a metric when you verify a proof. And this is similar to verification time in the sense that it more or less scales linearly with verification time. But what's nice about it is that it's deterministic. So if you verify the proof again, the verification count will be the same. And this property is so nice that in the following slides, I only look at resource count and not verification time. So in the previous slide, I showed you an example of brittleness, but I also want to show you how do we figure out how brittle a particular proof is. And we can do that by making not just one mutation to a proof, but by making many mutations similar to the one I made in the previous slide. So here I've taken 2 proofs, one sure-white proof that's brittle and another index-off proof that's not brittle, and I've made 1,000 mutations to both. And in the graph on the left, you can see how for each mutation, the resource count changes a lot for the sure-white proof. And you can see the resource counts they vary a lot. And on the right, you see the striped bar that shows timeout and also failures, so situations where Dafny was no longer able to verify the proof at all. But for index-off, the not brittle proof, you can see that for all the 1,000 mutations, the resource count stays tightly centered around the mean. And if we want to summarize the graph on the left, we can compute the relative standard deviation of resource count. And then we see that for sure-white, it's 1.4, while for index-off, it's much less. So on the previous slide, I showed you a way to measure brittleness, but that's a time-intensive method because it means having to verify a particular proof for many mutations. And if you have a large code base and you want to quickly iterate on a particular proof, then you might not want to compute all these mutations all the time. So it's great to have a faster way to guess or to know that a particular proof is brittle. And we've found that it seems like there's a positive correlation between brittleness and resource count. It's hard to prove this correlation because in real-world programs there are few brittle proofs because Dafny users tend to remove brittle proofs from their code base. But here I've taken some real-world libraries and from there it seems like there's that positive correlation. So if you look at the graph on the left, you can see that as resource count goes up, relative standard deviation goes up as well. And if you look at the graph on the right, you can see that as resource count goes up, the number of times a particular proof has mutations that contain failures goes up as well. So in the following slides, I will look at Dafny features that help users reduce brittleness, but the way in which I'll measure it is to see to what extent those features reduce resource count, in the assumption that that also helps reduce brittleness. Okay, so let's look at some Dafny features that help reduce brittleness. First, I'll go over assertion isolation. This is a feature that's been in Dafny for a while, but we've recently extended it with a few parts that I'll show a bit later. Here you see a proof max of concat, and there's an explicit assertion on line 9 with this by isolate clause. And what that clause does is it tells Dafny not to prove the max of concat lemma all at once, but to do it in parts. Each part we call an assertion batch because it contains one or multiple assertions. And in this case, there will be two batches, one that asserts just the explicit assertion on line 9, and the other that will assert all the other assertions in this program. Now you might say, what other assertions? But there are many implicit assertions in this program. So let's look at what the batches look like. So here's the one that contains just the explicit assertion that we isolated. You can see there's an assumption at the start that comes from the requires clause, and there's two other assumptions. These come from the requires clauses of the preconditions of the subrange expressions that we have in the condition on line 5. And if this had been one big batch, those assumptions on line 3 and 4 would have to be asserted as well, but now we've moved those assertions to a different batch. So in this batch, they're just assumptions. And then if you look at the second batch, then we can see that the explicit assertion that we isolated, here it's on line 5, has now turned into assumption. So these two assertion batches by themselves are simpler than the single assertion batch we had before, and that means their resource count is also lower and that they're likely to be less brittle. We can also isolate other statements than just explicit assertions, as you see here, and this allows us to isolate any explicit or implicit assertion that occurs in the Dafny program. And if you want to isolate all the assertions in a particular proof and you don't want to type this by isolate so often, you can also use different syntax to isolate everything at once. Now, the syntax that I'm showing here is not the syntax that Dafny is currently using, but this was easier to read for the slide, so I've used this. But you can find the current syntax in the documentation. So let's look at what isolating assertions does to resource count. You can see in the table on the left, that on the graph, in the graph on the left, that as we isolate more, the maximum resource count of any of the assertion batches goes down, but in the table on the right, we can see that the more we isolate, the total resource count also goes up. And for that reason, Dafny does not isolate assertions by default, because that would slow down the verification of large projects. So we leave it up to the user to decide when a particular proof seems brittle, and then for that proof to decide to isolate maybe particular problematic assertions or all assertions, so that the project as a whole doesn't change much in its total verification time but there are no particularly brittle proofs. Let's go back to the Schur-White proof that I showed before, the brittle Schur-White proof, and see what happens if we isolate it. Now you can see it in this graph. Once we isolate all the assertions in the Schur-White proof, suddenly it's not brittle anymore. So now the resource count stays tightly clustered around the mean. And then a recent feature for assertion isolation that we added is path isolation. So instead of isolating a single assertion, we can also isolate a pair of paths and assertions. So here we're saying for this this call that happens on line 9, it has preconditions that need to be asserted, and we want to isolate each pair of a path that leads to this call and the preconditions of that call. And in that way, we get more isolations, and those individual isolations are easier to prove. This is a new feature, so I don't have real-world data on it yet. Okay, now let's move to function hiding. One problem that we've noticed is that when Dafny tries to verify a proof, the more information that is sent to the solver, the more difficult it is for the solver to verify the proof, and the higher the resource count becomes, and the more brittle the verification becomes. And the one way in which a lot of information gets sent to the solver is through the definitions of functions. So what Dafny tries to do by default is to figure out which function definitions will for sure not be needed to verify a particular proof, and then not send those to the solver. But sometimes Dafny doesn't know whether a particular function definition is needed, and then it has to send it over in case it is needed. And for these cases, we enable the user to tell Dafny, no, this function isn't needed for the proof. So the way to tell Dafny that is using hide and reveal clauses. And a way to use those is using hide star. So suppose you have a method that's brittle, suppose this method foo is brittle, then we can start by saying hide star, and that means that after that point on, all functions are hidden, all function bodies are hidden. So we won't be able to prove much, and if we try to verify this assertion on line 5, assert p of 0, then that fails. But after we reveal p, like we do on line 7, then we'll be able to once again verify assert p of 1. And we can see what effect this has on real-world data. So this is data taken from an unreleased AWS project, and they've used hide and reveal statements on some of their proofs. So many they have not used it at all, but some of the proofs that were problematic, there they've used this feature. And you can see that there's a big reduction in resource count in general. And for them, this has been really effective. Okay, now let's go to opaque blocks. So first I'll motivate opaque blocks. And one thing we see is that Dafny method sizes vary greatly, so they can be 200 lines or even longer. And the problem with that is that the resource count of verifying a method increases super linearly with method length. There are many reasons for that, but one reason is that every time a Dafny program mutates the heap, this creates a new heap layer, and that makes it more difficult to read data from the heap afterwards. And well, a way to deal with the problem of large methods is to make them smaller, which a Dafny programmer can do by extracting smaller methods from a larger method. But the problem is that this can introduce a lot of boilerplate in terms of method signatures and call arguments. And we wanted to lower the bar for doing this extraction. So we've added a new feature called opaque blocks that looks like this. So the way to create an opaque block is to add the keyword opaque in front of a block. And what that does is that everything that happens inside of the block becomes invisible to the context outside of the block. So here on line 9, we're assigning the value 1 to the variable r, but on line 11, we won't be able to assert that r equals 1 because that assignment was invisible to this point. So then we still need a way to know something about what happened in the block, usually at least. And that's possible through ensures clauses on the block. So on line 5, you see this ensures clause, and that allows us to prove the assertion on line 12 that has the same condition, r is bigger than 0. Opaque blocks also have modifies clauses. So this one has an empty modifies clause, which means the heap is not modified at all by the block. So So we knew before the block c dot a equaled 1 because of the requires clause, and that means that after the block that's still the case, which allows us to prove the assertion on line 14. And what's nice about opaque blocks is that, well, in this case, because the modifies clause is empty, there's no extra heap layer introduced, even though we are modifying the heap inside the block, but no part of the existing heap was modified. We're just creating, we're just allocating a new object. So that can happen sort of opaquely. And then also, if we were modifying parts of the original heap, then if we would do multiple modifications, that would still show up only as a single extra heap layer to the context outside of the block, which is also better for performance. And to better understand the effect of opaque blocks, we can look at assertion batches like we did before. So here's the assertion batch for the previous program if we had not used opaque blocks. And you can see there's two heap variables, heap 1 and heap 2. And these are tied together using a quantifier on line 5. And that means that if we want to prove something that involves both heaps, like the assertion on line 13, R2 is bigger than 1, then we need to instantiate this quantifier, which can be an expensive operation. So here's the assertion batch if we do use the opaque block. And you can see it's much simpler. There's only a single heap variable and there's no quantifier, so it's much cheaper to prove the assertions here. Opaque blocks are a new feature for Dafny, and I don't have real-world data on them yet. We have applied them to some real-world proofs with great results, but here I'm showing data just from a toy method that I made myself. It's a very boring method. It repeats the same code 200 times, and it creates an object, sets a field for it, and then passes it to a method call. And I've measured how the resource count of verifying a single assertion in this method goes up the further down in the method that assertion is located. And you can see that the further down we go in the method, the more the resource count increases exponentially if we're not using opaque blocks. But when we do use opaque blocks, then the resource count used by the assertion stays, doesn't stay the same, but stays much more the same as the method grows longer. So for this toy program, opaque blocks make an absolutely huge difference. So to conclude, it seems that brittleness is correlated with resource count, and we can add language features to Dafny to enable users to reduce brittleness, in particular assertion isolation, function body hiding, and opaque blocks. And then for future work, we plan to enrich or extend the work that we've done with hide statements. So we want to make it easier for users to know what hide and reveal statements to add to their program, which we'll do using IDE code actions. We also want to enable users to hide not just their own function definitions, but also definitions from the Dafny prelude. And we want to enable hiding subset types and ensures clauses. And then lastly, so this is something that doesn't require any user involvement, but we want to improve the efficiency of the Dafny to SMT encoding so that the resource count is reduced in all cases. Okay, that was it. Are there any questions?
Hi.
Not hey.
Oh.
Go ahead.
Can you hear?
Yes, I can hear you.
Thanks. What does the resource count actually measure, just to get an idea of that?
Sure. Yeah, it's a metric that's emitted by the SMT solver, and it's the SMT solver is implemented in a way so that the resource count attempts to scale linearly with verification time. So the intention of that metric is that if verification time doubles, resource count doubles as well. Now, it's impossible to make that correlation be exactly linear, but there is a strong correlation, and because it is a deterministic metric, it's nice to use because then you can get consistent measurements. And for example, you can say if the resource count for verifying this particular proof goes above some threshold, then I will fail. And if you would do that with verification time, then you might get unstable behavior, which you don't want.
Thank you.
Hi, this is Peter Müller from ETH. Thanks for a very nice talk. I just wanted to mention, because you said you had no real data yet for the opaque blocks. So we have basically the exact same statement in our Gobra verifier. We call it outline statement. And we used it quite heavily in a very large verification project, and it made a huge difference for us. So there were many large methods that we couldn't verify without this feature, but with the feature, it was quite doable. So our real-world experience is that this feature is actually extremely helpful.
Oh, that's really good to hear. Well, yeah, that sounds great. I will look at that feature, see how it compares, and also see if you've published some data on it.
One last question.
Could you say again how the heap layer is modified by an opaque block? Is it always create its own new heap layer, or essentially does it what is its relationship to the existing context in the program in a method?
So normally, if you have an operation in Dafny program that modifies the heap, a new heap variable is created. And for an opaque block that has a non-empty modifies clause, that happens as well. But then from the outside, it seems as if the entire opaque block is a single operation that modifies the heap. But inside the opaque block, you might modify the heap 100 times. So if you would not have the opaque block, you would get 100 heap variables. So a very deeply nested heap. But with the opaque block, you only get one nesting. I hope that answers your question. I'm not sure if I understood it correctly.
All right, let's thank the speaker again.
All right. Thanks, everyone, for listening. You.
So the next talk is by Izu, who's a PhD student at CMU of Brian Parnell.
Okay, great. All right. Yeah, thank you very much for having me here, I guess. I'm E from CMU, and I'll be talking a bit about our work on towards more stable proofs for SMT-based verification. So this presentation will draw materials from the following papers. And obviously, I didn't do all these work by myself. So let me first start very briefly with some backgrounds on SMT-based verification pipeline. We start with the source code, then we have the verification framework, which includes Dafny, for example. It encodes our VC into an SMT query, and whether our program verifies or not depends on the response from the solver. And if we get inside, we're happy. But in reality, we often need to make a lot of modifications, as we discussed earlier. That means updated queries. But the solver, even given a semantically equivalent query, could potentially give different responses. And we're no longer happy. And that's the phenomenon of instability or burdenness. Okay, so there seems to be a form of belief that we have to trade off between automation versus stability. On one side, we have high automations. Let's say how these three handle all the undecidable theories. And then, but we get poor stability. So to have more stability, we need to do more manual handholding, so more manual proof steps. And the other extreme is kind of we just drop down to decidable theories only, and so we lose the automation over quantifiers, for example. But this talk, I would like to cover a bit or have a discussion on can we actually have automation and stability at the same time. So this is drawn from the observation that instability means a mixture of a failure and successes. Right. So the high-level idea is that we learn from the successes and we remember the success lessons at the source code level to avoid future failures. And we propose to do this all automatically. So this talk will have three parts. First is detection. That is telling what is unstable. And the second part is debugging. That is to tell why a particular query is unstable. The third part is a bit speculative. It's once we know what's wrong with the query, how do we fix it at the source code level? Okay. I'll go through this very briefly to talk about our work on Mariposa, which is for instability detection. So Mariposa is a tool that takes a query and a solver as a pair of input, and on a very high level answers the question of whether it's stable or not. Okay, the way Mariposa does it is by performing mutations on top of the queries. And the mutations here are meant to be preserving the semantics. That is, say, shuffling the assertions around or renaming the variables. And the intuition here being that if we are seeing certain failures and a mixture of successes coming out of these mutants, then we're seeing instability. So Mariposa, we actually use a series of statistical tests to decide which category query solver pair belongs to. I will not go into the details here, but I would like to just argue for doing these tests a little bit here. Let's just say, for example, we're doing assertion shuffling. Even if we only have 100 assertions, that means we have a huge number of mutants. And we really would like to be statistically sound in the judgment here. But let me not go into too much detail of that and say that, well, once we we could detect a particular query or label is unstable, can we tell why is it unstable? Let me first talk a little bit about the query context and our work on Shake that discuss the cause of failures in context more generally. So an SMT query is, on a high level, made up of a set of assertions where the overall semantics is whether the conjunction of all these assertions implies a conflict or unsat. So as it turns out, not all of these assertions are strictly necessary towards proving unsat. So as we kind of discussed earlier, a lot of these contexts are irrelevant. But as it turns out, it's a huge amount of context that is irrelevant. Typically, it's more than 96%. And these are from Mariposa benchmark, where we have tens of thousands of queries. And 78% of the instability actually gets mitigated if we were to, say, drop down to the irrelevant context. Of course, that's the idealized case, because sometimes we don't know which are or are not irrelevant. So in Shake, our work at POPL'25, we had a discussion on how to do SMT level pruning that makes an observation on the context pruning being axiom selection. And we're able to achieve reasonable stability improvement at the SMT level. I would like to talk more today on the specific causes of failures rather than just the general irrelevant context. So that is our work in progress on pinpointing the problematic quantifiers within the query. So again, let's abstract the query as a set of quantifiers. And our debugger, what it does is that given an unstable query solver, it pinpoints particular quantifiers within this query that is responsible for instability. Okay, how do we do that? Again, we come back kind of to the original picture on instability, where we have mutants. Some of them succeed, some of them fail. And the intuition towards answering what's wrong or why is it unstable comes to answering the question of what went wrong in the failed mutant. So in the case of quantifiers, a failure mode includes over-instantiation, or maybe it's under-instantiations. In more details, we could collect the tracing data from the solver, say enable tracing on Z3, which will give us a trace of failure, including all the quantifier instantiations that has been attempted, but doesn't lead to a success, obviously, in this case. And in the case of success, we could ask for a proof of unsatisfiability from, say, Z3. And that would also include quantifier instantiations that are necessary towards constructing this proof. Okay, then the idea is that we kind of differentiate or tell the different contrast these quantifier instantiation profiles to tell what went wrong. Okay, so in more details, our debugger works like this. Start with a query, gather a proof of unsatisfiability, also get a trace of failure. And at the core of our debugger, we have this query editor that performs edit upon the original query based off a single quantifier only. Okay, so we literally try all the each quantifier here and performs one edit on top of it. And each edit is a singleton edit based off just one quantifier. So in more details, let me give an example of what this edit looks like. Let's suppose the phi naught is never used in the proof at all. That means it's probably unnecessary. But at the same time, if we look at the trace, let's say this quantifier is heavily instantiated, then it might be reasonable to suspect that the failure or instability is due to over-instantiation of this quantifier. So within the editor, we could try remove this quantifier completely, which gives us a new query that is almost identical to the original one, except we don't have this phi naught anymore. Okay, now the idea is that if we rerun stability test on this edited query, now it's stabilized, that tells us, well, our hypothesis on phi naught being over instantiation is probably right, and that is to be blamed for the failure or instability. Yeah, in a similar fashion, let's say phi1 is needed in the proof, but it's never instantiated in our failure trace. And that it might be reasonable to suspect that the solver is missing key quantifier instantiations of phi1, and which leads to the failure. So what we do in the editor here is we could try provide the instantiations of phi1 as facts, right? So just let's say assert them, insert them into the query. So again, if this query is not stabilized, that means phi1 is to be blamed. Okay, so that's kind of a simplified picture, but hopefully the high-level idea is here that these edits are meant to reduce or eliminate solvers' need to reason about particular quantifiers. Right, so in practice, we have more edits, but that's the high-level idea. So using this workflow, we have some preliminary results on the Verus benchmark. So in case you're not familiar with Verus, it's a program verification language. A lot of it is inspired by Dafny. So yeah, we have 70 unstable queries from the benchmark. In 4 cases, we cannot build a proof for analysis due to, say, some issues with Z3. But in 62 cases, we can find at least just one stabilizing singleton edit. That is, the instability could be blamed on top of just a single quantifier. And in 4 cases, we didn't find any singleton edit that would fix it. But it doesn't mean that maybe there exists some combination of, say, 2 or 3 quantifiers, and the interactions between them kind of led to the instability. And that's kind of our work in progress on how to intelligently schedule and compose these edits to do better debugging. Okay, so yeah, after we could tell or identify what is wrong with a particular query, the next step is towards repair. This is a bit speculative, but bear with me. Let's say our debugger here reports that the solver has trouble, say, instantiating the quantifier v1. And the intuition here is that we can record and replay the instantiations of v1 at the source level. Right, so the idea is that the solver doesn't need to rediscover the quantifier instantiations every time. Right? It just needs to figure it out once. And we could just record them at the source level. So let me give a kind of a silly example here. Let's say we have an associativity of multiplications as a quantifier, and say our debugger points to this UF lemma, says it's unstable, and it's unstable because the solver has trouble instantiating this quantifier. We could manually adopt to a different programming style in which we explicitly provide the quantifier instantiations, and that would actually fix the problem. What I would like to point out here is that first, these instantiations, we could just ask the solver for them, right? We don't have to manually come up with these. And second, this is a very programmatic transform of the source code, right? So we talked about IDE actions previously. So we already have this framework, POPL'25 for Verus code that kind of does these programmatic transform of the Verus source code that would enable such changes. Okay, let me kind of pop back up on our discussion towards automated stability. We have 3 parts: detection, debugging, and the repairing. The takeaways I would kind of like to leave here include that, well, we can enjoy both automation and stability, and the key idea is that we use past successes to prevent future failures. And we can often even localize the cause of instability rather than say it's a general context problem. And furthermore, I would like to root for more statistically sound detection and validation method for instability. And yeah, these are the references. And thank you very much.
Thanks for the talk. We are short in time, so maybe one quick question.
Thank you for the very nice talk. So the slides, that was the title 2.2, gives an impression that to start the debugging process, you need to get the first ansatz, right?
Right.
So basically, if my proof times out and I don't know why, that would not be very helpful. Is that correct?
Then it will no longer be a consideration for instability, right? If it completely fails, then it's not unstable, right?
So if it just times out, then, well, there is nothing to begin with, right?
If it times out completely, that is, it never succeeds at all, that's not a problem of instability. It's a problem of, yeah, that is not within the scope of the discussion here. We do have some other works on that, yes.
Okay, thanks.
Yeah.
Let's thank the speaker again. Next speaker is Stephen. He'll be talking about verifying the Fisher-Yates shuffle algorithm in Dafny.
Can you hear me? Not sure what the slide.
All right. Yeah, thanks for the introduction. So this is the first talk amongst 3 that follow on applications of Dafny. And it's joint work with my colleagues at Amazon. So the Fisher-Yates shuffle is a method that goes back already to the 1930s, I believe, that essentially allows you to permute a sequence or an array using randomness such that any permutation is equally likely. And it's an interesting target because it's pretty simple, but also simple to mess up. So if you just get one number off by 1, then the distribution won't be correct anymore. So the way it works is, in this example, we're given a sequence of length 10. Then you start on the left, you fix the first element of the sequence, and then you sample uniformly a number between 0 and 9. In this case, say we get 7. Then you fix the 7th element of the sequence, and you swap the 2 elements, which gives you a new sequence. Okay, and then you start again by moving 1 to the right, so you fix the 2nd element, and now you uniformly sample not from 0 to 9, but from 1 to 9. So say we get 5, and we go to the 5th element, we swap it with with x1, have a new sequence, and so on. Then you go 1 to the right, and this procedure continues until you end up at the end of the sequence. Here we get the 9th element, you swap one more time, and then you end up with the last element, in which case there's only one element, one number to sample, so there's nothing to do. And that leaves you then with permutation from the initial sequence. And in this paper, Extended Abstract, we sort of described how we implemented the Fisher-Yates shuffle in Dafny and how we prove it correct. And even though for this case things are still relatively simple, I think it's a nice blueprint for more complicated methods that use randomness in Dafny. So the way we model randomness in Dafny follows a perspective taken by Joe Hurt in his PhD thesis. So essentially a randomized algorithm or a sampler from a distribution D that takes values in a domain V would be modeled as a transformation that takes as input so-called bit streams, which are essentially infinite sequences of Booleans, and then transforms that into a sample or into a value in this domain V. And then you say that such a transformation truthfully represents a sampler from a distribution D if this equation here is satisfied. And I won't describe that into too much detail, but essentially what it does, it transforms the correctness statement to a statement about bit streams, okay? So you have this mu, which is a probability measure on bit streams. And that's essentially what's happening here. So we have a probability measure on bit streams, and the correctness is transformed to statements about that. So to make that more concrete, so how do you model a simple coin flip in that framework? So you would take a bit stream as input, and then you return a value in the domain of Booleans, which would be the V in the previous slide. And this transformation would sort of truthfully represent a uniform sampler from 0 and 1 if the measure for the set of bit streams that map to true is the same as the measure of the bit streams that map to false. So both have the probability 1/2. And one way to implement that would be just by returning the first value in the bit stream. So on a high level, the approach we take essentially consists of 3 parts that I think a lot of projects follow. So one, we have a functional model of Fisher-Yates, which operates on Dafny sequences and uses this bitstream transformer approach. Then we have a correctness proof of the function model, which establishes that this function model of the Fisher-Yates shuffle has the right distribution. And then lastly, we have an imperative implementation that you would actually execute that we show is equivalent to the function model and operates on arrays. So let's look at the function model. So I've shown you this coin prime, but actually to compose such functions, you would not just return a value, a sample, but you would also want to return the bit stream that hasn't been used yet. So you can use it in the next step. So formally, what we use, and again that goes back to Joe Hurt, is we use the state monad of type bitstream, which if you instantiate it, gives you these definitions. And if you uncurry the definitions, then you would operate between tuples of values and bit streams. And under that view, the return function would be just the identity. And the bind, the multiplication of the monad, would be essentially just a composition between functions between tuples. So it's pretty simple, and it looks a bit more complicated because we curry it essentially. And if you take the previous coin prime, then you can extend it to this definition by not returning just the first element of the bit stream, but also the remaining bit stream, which is shifted by 1. And more generally, randomized functions would be randomized functions that take an input of type S and return something of type T would be functions that take an input of type S and return herd of type T. Okay. Sometimes these are also seen as Kleisli morphisms for a particular monad. And in the example above, the type S would be just empty, and the type T would be bool. So to speak about the correctness of the implementation, we formalize this probability space on bit streams. Concretely, we assume that there are two elements, the event space and the probability measure, which assigns to a set of bit streams a real value. And we assume that these two constants, which are not defined concretely, they're just abstractly, that they form a probability space, which this axiom here captures. And I won't go into the definitions of the predicate, but it follows sort of classical probability theory. And then then we axiomatize the existence of a uniform sampler that returns values between 0 and n. And this is indeed a uniform sampler if, for any I between 0 and n, the probability that that the probability of all the bit streams that under H map to I is 1 over n. Okay, and that's what I was talking about before, that everything gets reduced to measuring the probability of these sets of bit streams. Okay, and then having assumed this uniform sampler, we can lift the definition to a functional definition of Fisher-Yates. First, we lift the definition of sample to a definition of interval sample, which is straightforward. And then the actual implementation follows the example I showed you in the beginning. That is, first we sample between I and the length of the sequence. Then we take that element, swap it, get a new sequence and a new bit stream. And then we have a recursive call that goes on with the new sequence, the new bit stream, and increases I by 1. And that's the recursive call, and that continues until you hit the base case, in which case you return the sequence. So let's look at the correctness proof for that. So essentially, that is the lemma that we have proven, and what it says is so it has two arguments: a sequence, the initial sequence, and then an arbitrary permutation, which is captured by the second requires clause. So the permutation means just they have the same multiset. And we also assume that the sequence doesn't have any duplicates. And then it's well known that there are factorial of the length of the sequence many permutations for a sequence that doesn't have duplicates. And then the lemma really just states that the probability such that you get this arbitrary permutation P after using the Fisher-Yates shuffle will be 1 over the factorial because there are that many permutations. And again, you measure the probability of this set E of the event that is a set of bit streams. And the actual proof efforts, so we don't operate on the lemma directly, but we establish a slightly more general lemma which has an additional parameter I, and otherwise has the same signature. You just need to figure out sort of the right spots to add the more general component. And the reason we do that is that it allows us to do induction over that lemma, a recursive call. And then you deduce the other correctness lemma that we actually want by just instantiating this one with I equals 0. And the interesting part is that the proof of that more general lemma, which essentially reduces to using two properties that we assume about the uniform sampler. That is one, something called weak functional independence, and two, measure preservation. And I won't go into details, but independent functions, so the independence here refers to independence in the sense of probability theory, which says two events are independent if the probability of their intersection is the multiplication of the probability of the individual events. And measure preserving is essentially what you can see here. And yeah, these two assumptions are sound by previous work, and they essentially they're sort of at the heart of the proof. All right, so in reality, we won't use the functional model, which assumes this infinite stream of bits, but actually we use an external source of randomness. That is, we assume access to an external uniform sampler, which is assumed to correspond to the functional model in the sense that is shown here, the ensures clause. So you have access to some sort of internal bit stream that the imperative implementation modifies. And it does that in this way, which is a bit hard to put into words, but you can see the old keyword here. And yeah, so we assume that on the level of uniform sampler, and then that allows us to lift that assumption again to the correctness of the full Fisher-Yates shuffle, where the correspondence to the function model again is captured as this ensures clause. And the actual implementation is very similar to the functional one, but you operate on arrays, and it's a method, right? And you modify this internal bit stream. And the proof of equivalence uses some appropriate for loop invariant and some assertions that I have omitted here. And yeah, so we can compile the Fisher-Yates shuffle to target languages if, one, the Dafny compiler compiles to that language, and two, the target language offers us an implementation of this uniform sampler, which a lot of languages obviously have. And we have that, I think, for 3 languages in the framework right now. All right, to sum up, we use 3 assumptions. One is that there exists a probability space on bit streams, which is something that Hurt has shown, and that was independently proven. And then we assume the existence of this functional model of the uniform sampler, which we then lift, and an external method sample that implements it and corresponds to that functional model. And even though we sort of draw the line of axiomatization on the level of uniform sampler, you could also go a bit lower by just assuming a coin flip, so uniform 0 and 1, and then lift that to define a uniform sampler. And again, it's well known that this works, but here we have sort of drawn the line a bit higher because of simplicity for the proofs, but also for the efficiency of the actual shuffle, because it's, instead of defining your own uniform sampler, it's easier to use an external one already instead of lifting the coin flip. And then finally, we actually worked over Dafny's bounded int32 type rather than over ints because we wanted to compile to Java's int and not big integer. But we made a change later, but there was almost no proof overhead by that modification, which was interesting. And yeah, with that, if you're interested, there's a GitHub repo and the extended abstract of that of the workshop. So, thank you.
Thank you. Are there questions? Yeah.
Thanks for that. Historically, when we've tried to use reals in Dafny, it's been very unstable. Did you run into that anywhere, or how deep were the real properties you were proving?
So we did not run into that. There was this is actually a broader framework, and I think we just used a sort of discrete version and not the continuous one. So we avoided that there.
Okay, maybe one final question.
Yeah, maybe I didn't quite understand how you managed to get, like, you started from a bit stream and you gave an example of getting a coin flip from that. But if you wanted to get, 1 out of 3 or 1 out of 5, then you have to do some rejection sampling or something like this in order to get uniform distribution on that. Was that implemented as part of this?
So that, yeah, essentially you're referring to, on the last slide, what I said is that you could draw the line a bit lower. Like you can start with the coin flip and lift that to the uniform sampler. That would sort of do exactly what you said. Sorry? So there's only termination with probability 1, so you run into things like this. But yeah, here we draw sort of the line a bit higher, but if you go sort of into the history of the repo, you will find actually the implementation of that as well. And
Okay, I think that's all. We can move on to, let's thank the speaker again. And he'll be talking about shipwright, a modular framework for verifying liveness of Byzantine fault tolerance systems.
Test. 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 So when I tell friends that I'm a grad student in computer science, they get really excited. Derek, you're a grad student in computer science. We should do an AI startup so we can get rich and retire early and live on a private island. I don't know anything about AI, actually. Sorry, guys. You can hear about it later today, but I'll tell you about the next best thing, which is Byzantine fault tolerance. If you don't know what Byzantine fault tolerance is, here's an illustration by James Mickens in 2013.
So Byzantine fault tolerance, or BFT, refers to a family of protocols where a group of servers, some of which are malicious, try to establish some consistent information about the world over an unreliable network. In such a setting, liveness is very important for security. So there's a lot of non-determinism that happens in these systems. So we, the authors, think that BFT systems are a great target for formal verification. And so our goal is to create a framework to verify and implement BFT systems in general. For this talk, I'm going to focus on how we verify a Dafny library that implements PBFT. PBFT stands for Practical Byzantine Fault Tolerance, and it's a protocol by Castro and Liskov in 1998. Now, this is an old protocol, but it forms the foundation for a lot of modern protocols used in blockchains and in payment systems. One thing we can observe about these systems is that there's a lot of structure, and so it is important for our framework to support a modular development and verification strategy. Of course, Dafny is designed for straight line, currently designed for straight line single-threaded code, and we need to adapt Dafny to a distributed system, so we run into many challenges with modularity. The first challenge is that we need to be able to state and prove liveness properties that are composable. So a liveness property is a property over an infinite execution that something will eventually happen. The second challenge we run into is to model the system's environment. So a lot of proofs of these protocols' correctness depend on assumptions about clocks and message transmission, as well as cryptography. There's a lot of really interesting related work, including some by some of the audience members here today in Rock, and with model checking protocols automatically. I'd love to chat about these after my talk. Contribution we have is Shipwright, a Dafny framework for verifying liveness of Byzantine fault tolerance systems. The Shipwright framework is about 12,000 lines of Dafny code, which is gives you a flavor of how complicated it is. And we're able to implement and verify a single view of the PBFT protocol with around 24,000 lines of code. I'll start today by telling you about our approach. So let's start with the simple protocol, which I'll call multicast, or the proposal protocol. In this protocol, we have a bunch of servers, and there's a special server called the leader. It's the leader's job to send a value to all the other machines in the system. So throughout this talk, I'm going to show you many snippets of Dafny code that might be in small font here, and I'll highlight the parts that are important. The first thing we have to do is specify exactly how a programmer implements code for a node in our system. So on the left, we have a API module, and it defines a function type called run. Run modifies some node state in response to some input from the environment and returns a list of messages to send on a network. On the right is an instantiation of this generic run function for our particular proposal implementation. Now, there are two cases for this implementation. In the first case, leader gets from some local external call a value. And if it hasn't done so yet, it sends this value to all of its peers in the system. In the second case, a node receives a value from the alleged leader. And if this value checks out and it hasn't received another value yet, it saves this to its state. Our goal is to prove a state machine refinement theorem about this code, similar to that in Iron Fleet, which is prior work from Hobblitzel and the rest in 2015. We start with a concrete state machine that models the network and calls into the code that I just showed you. And our goal is to show that it refines an abstract state machine that implements our protocol. So on the left is our state transition system that models our network. We have a network module here that has a function type parameter, the same run parameter as you saw before. And this generic network uses this run parameter to update the state of the nodes as well as the network. We have a second module which instantiates this generic network to our particular protocol. And it does this by setting the run argument accordingly and by instantiating the type arguments to the things in the network as you'd expect. Now, I don't know how to put drawings by James Mickens into Dafny, but I do know how to put a state machine. And so on the right, you have a description of the proposal state machine module. In this state machine, the state is much more simple than the state on the left. And so is the transition function. And in fact, the entire transition function fits on the slide right here. So it's a much simpler object. I'd like to emphasize that we use type and function parameters to support a generic network and then instantiate it for a particular implementation. We use non-ghost functions in Dafny and not methods because these functions serve a dual purpose. First, they are executable code that can run directly, and second, they can compose with the ghost functions that are used to define our models of the network. All right, there's a lot of interesting techniques in our project. I'm going to skip some and go straight to telling you how we prove liveness. So let's move on to our next example, which is a protocol I'll call a voting protocol. In this protocol, let f be the number of malicious nodes in the system, and suppose there are 3 f+1 nodes in the entire system. Each node sends to all the other nodes some value, and we say that the protocol is done for a node if it's received a set of signatures from distinct signers on the same value. And this is called the quorum, and its size is 2f+1. So what things are live in this example? In order to prove liveness, we first have to define liveness. So we can define liveness to be something that always eventually happens intuitively. So for example, we can say in the network, always eventually a message is delivered, or abstractly, a node always eventually receives a quorum. And we represent these kinds of constraints in shipwrights as something we call a task. So here's a couple tasks in our network module. The first task is the stabilize task, and the second is the message task. And every state machine specifies a function called a predicate called fair. And so this fair predicate looks at the task, the state, and the transition. And we can see that it's true for the message task if the current transition is a message transition, and we've sent a message but not yet received it. And the stabilized task is fair if we have a stabilized transition and their network is not yet stable. We use this fairness predicate to define liveness in terms of temporal logic. In particular, we give this a temporal interpretation on executions in the way that we'd exactly expect intuitively. The problem we run into is that if we unfold this definition all the way, we realize that we have a definition that involves nested quantifiers over some execution, where an execution is an infinite sequence of states and transitions. In other words, if you unfold this, you get for all tasks and for all numbers k, there exists a k prime greater than k such that fair is true on task, the state at index k prime, and the transition at k prime. Obviously, Dafny is not great at handling these kinds of statements, and in order to figure out how to deal with them, we need to do a little more high-level thinking. So intuitively, we should be able to show that suppose we have some arbitrary step, and we have some assumptions on the progress of the concrete tasks in the system. It should be sufficient in order to prove liveness to show that over the same step, the abstract tasks also make some kind of progress. We'll formalize this with something we call a completion measure. So here it's denoted mu. And we associate a completion measure mu with every task and with every state, such that either the fairness predicate is true at that point, or the measure decreases. Now the measure can be a natural number, but we found that it's much more useful to have a general definition. And so we can take any measure that has a well-founded partial order. And you'll see how this is useful, an example of this in a second. So once we've defined a completion measure, we can write down our reasoning principles for proving liveness. So consider some state st and some next state st prime. Suppose that we have that for all concrete tasks C task, either C task happens or the measure decreases. It is then the job of the proof engineer to construct a measure such that for all of the corresponding abstract tasks, AST or AST prime, and for all abstract tasks, a task, either a task happens or this constructed measure decreases. And we verified within shipwright that this is sufficient for establishing liveness. How does this look like in our voting protocol? So let's look at the abstract task associated with node k receiving a quorum. So because we cannot depend on malicious nodes to have progress, let h of s and k be the set of honest nodes in S that k has not yet heard from. If h is 0, if the size of h is 0, then it doesn't matter what we return because the proof is irrelevant. Our fairness predicate is true, and so we're done. Otherwise, we return a pair, and the first element of the pair is the size of h, and the second is the measure for the delivery of a message from node I to node k, and where I is picked arbitrarily from h. We can see how this looks like in Dafny. So we have some code below here that defines a variable pending. Pending calls this helper function map nodes pending, which I made opaque. and it uses that to compute h of s and k. And it returns a partition data structure, which is a special data structure we use to identify subsets of all of the nodes in the system. So once we've computed h of s and k, it's very easy for us to return the measure we want. And so once we have this measure, we have two remaining cases. Either the current transition is the delivery of a message from some node in h to a node in k, and then the first element will decrease, or that's not the case, and so the first element of this pair will stay the same, and the second will decrease. There's a few additional things that are useful to us when we define our refinements. First, it's useful for us to make custom libraries for various abstractions, such as quorums. So on the right here is an expansion of our partition module. And the nice thing that this library does is it helps us prove many useful facts about partitions without having to reveal definitions that are opaque. The second thing that's very useful to us is to have a way to pick something from a set consistently, globally in the whole system, and deterministically, but also arbitrarily. So in order to do that, we wrap the Dafny neutral choice operator in a ghost function here that's just global, and the output of the ghost function actually only depends on, if we fix the set, the type of the element inside the set. So great. Okay, so now I'm going to talk about decomposition and how we use it to verify a single view. So a view in PBFT is a technical term. It means a single attempt to reach agreement. And so the view consists of 4 message types. So we associate a subprotocol with each message type and refine that subprotocol to some corresponding abstract state machine. And I'd like to point out that 2 of these state machines are the same, so we're actually able to completely reuse the code and proof effort there. So each of these boxes are a specification, which involve our fairness predicate, as well as a few other things. And what we do is we define a combine function that takes in a left specification and a right specification and gives us a composite specification. And we also prove that this combine function is consistent with our notion of refinement. Once we do this, we're able to combine all 4 of our abstract specifications and show that it refines this new specification that we call graded consensus. There's some prior work that refers to such a protocol. So the last thing we have to do is produce an executable implementation. The problem is the bottom of this diagram is not executable. It's the product of 4 different state machines, and that doesn't actually even correspond to anything in physical reality. So our solution, of course, is to create a mechanism to compose 2 pieces of code together. The requirements for this is that it must produce executable code. It must ensure that each piece of code that's being composed has assumptions that are consistent with each other. And the most important requirement is that verification effort needs to scale with the growing implementation size. And this is the most important requirement because if you look at this diagram, this bottommost state machine is the most complicated state machine in the whole system. It encodes the whole network, it encodes the entire implementation, and to prove this refinement is actually pretty tough for Dafny. So this composition mechanism is actually the most complicated part of our framework. It's about a quarter of the code there. So this is very important for making this tractable. Once we have that, we have all the ingredients we need to do our top level implementation and proof. So we're able to show a refinement from about 670 lines of code, which implement this view, to a spec with about 300 lines of code. When we run the Dafny verifier on everything in the system, it takes about 4 minutes on a 12-core machine. And we run it through the Dafny extractor to produce Go code and call this Go code from a trusted server implementation. Implementation is around 250 lines of code, and that implements things such as signatures, networking, and timing, really the whole server environment. What this looks like is really similar to that in Ironfleet, a top-level event loop that handles local inputs and network packets and timeout events. And as you might expect, the run function shows up for the 3rd and final time in exactly the way we'd expect. So I'm sorry if you were disappointed because you didn't get to learn about AI, but today I showed us Shipwright, our Dafny framework for verifying liveness of BFT systems. We prove a refinement theorem on a single view of PBFT using completion measures and techniques for decomposing the system. Thanks for listening to my talk.
Thank you. Very nice and clear talk. So I asynchronous consensus is not live, but you can prove it live under partial synchrony. So that's FLP. Could you explain how your fairness assumptions assume, like, imply partial synchrony or something similar?
Yeah. So you can use whatever assumptions you want: partial synchrony, asynchrony, synchrony. So if you squint very carefully, proving liveness under partial synchrony is a safety property and not a liveness property. You can prove liveness using these measures we have, and they depend on things always eventually happening. So like reliable broadcast is live, not consensus, but reliable broadcast. And you can prove this using our framework. When you talk about like partial synchrony, which is what PBFT uses, you'll need to, a lot of the complexity in our proof actually is dealing with timing, because PBFT's liveness depends on very specific assumptions about timing. And so our framework is able to encode both of these things as safety and liveness properties, whatever you prefer. And the cool thing about our framework is actually during the refinement, you can convert a safety property into a liveness property if you're able to write a specification in the right way. But I guess to maybe answer your question, we, if I understood it, we handle basically any kind of synchrony. And this refinement theorem in our formulation of liveness will be able to capture whatever assumptions you'd like to prove for your particular property.
Maybe one last question while we are setting up for the online talk.
Thanks for the talk. You mentioned very briefly in passing that you wanted to be generic over the network model. Can you say why?
Yeah, so the network model is generic, and it's important that the network model is generic for several reasons. One, the network is part of the trusted code base, so it needs to be audited by someone who understands like really carefully what the assumptions are. Two, we need it for our composition theorem for pieces of code. So when you compose two pieces of code, you better not have proven that one piece is live under asynchrony and the other is live under partial synchrony. They need to match. So it's important for us to literally reuse the same network model so that we can write that generic theorem.
Okay, let's thank the speaker again. So the last speaker in this session is Wojtek Rozowski, who's a PhD student at UCL. Can you hear us?
Hi, everyone. Yeah, can you guys see my slides? Let me turn on. Yeah, hopefully it works. Perfect. All right, so hello, everyone.
One second, Wojtek.
Yeah?
We can't see it yet.
Yeah, sorry, we're having a few issues from the AV side. We'll check it out in a minute.
Yeah, no worries. Yeah.
Can you try to stop the share screen and do it again, please?
Yep. Does it work now?
Yeah, we have some connection problem from our side. Okay, now it's working.
Perfect. Can I kick it off then?
Yes, you can go.
Oh, perfect. All right. Hello everyone. My name is Wojciech Różowski, as I was probably introduced, but I couldn't hear. I'm a PhD candidate at the University College London, where I'm supervised by Alexandra Silva. And normally I'm working more on the theory side of programming languages and their semantics. And today, I would like to talk about the joint work I've done with my colleague Stefan Zetsche, who previously was a PhD student in the research group where I am currently at. And the reason of this talk is not to scare you with a bit of formalism, but rather to show that you can formalize fairly complicated results using quite interesting Dafny features. So the talk focuses on a classic result from automata theory in the semantics of regular expressions, namely that the 2 points of view at regular expressions match, and we rely on the support for co-induction in Dafny, which allowed us to construct these proofs. And this is based on the paper that Stefan recently presented and was recently accepted to ICTAC conference. All right, so without further ado, let's just get started. So regular expressions whose syntax you can see at the bottom of the slide are a formal syntax for specifying languages, and languages are simply sets of words where words are sequences of letters taken from some alphabet. So, for example, 0 represents the empty language, so an empty set, or for every letter there is a singleton set containing that letter. We can combine them using the union of languages, or compose them sequentially, or form a creamy star. So from your beginner, like from the introductory automata theory or theory of computation module at your university, you know you can go about semantics of these things in 2 different ways. So first of all, you can look at this compositionally. So the syntax of regular expression is something you can define via induction, and if you're able to interpret each of the operations, such as interpret plus some operation on the set of formal languages, namely in this case it's union, or for example this dot to interpret it as a concatenation of languages, then by induction you can interpret every regular expression. And essentially that means that it's some sort of a compositional or algebraic point of view at this problem. And if you fix those interpretations, there is only one way you can do so in a well-behaved way. Alternatively, you can do it via automata theory, so we can construct automaton representing that regular expression, and to every automaton you can uniquely assign a language each state accepts, and this automata theoretic point of view gives some sort of the alternative structure where the set of languages is equipped with a automaton operating on a set of all formal languages, and somehow map assigning the language to the states is also well behaved and preserves the automata theoretic structure. So we have those 2 ways, one at the top, which is this compositional algebraic, and one at the bottom, which is this automata theoretic one. So the obvious question is, like, are these guys well defined? Are those well behaved maps, which are called homomorphisms, match? Is the map arising from automata theory preserving this compositional inductive point of view, and vice versa? Are these things equal? So this result, namely that these 2, since I'm asking these questions, the answer is yes. And in this paper, in our work, we encode these 2 point of views at the semantics of regular expressions in Dafny and show that they are equivalent. So let's dive in. So in Dafny, you can very easily define the syntax of regular expressions as an inductive data type. So you define all the constructors corresponding to all the ways you can build a regular expression, and intuitively, the set exp is the smallest structure that is closed under those constructors, and this is like an inductive or algebraic point of view, and people call this initial algebra for the signature representing regular expressions. On the other hand, normally we view formal languages as just the sets of words, but we can look at them extrinsically, namely as the biggest structure where you can test for the empty word and check for cutting the prefixes. So essentially, the greatest structure that is equipped with a deterministic automaton structure. And this is something that arises through the dual of induction, where previously we talked about the smallest one, here we talk about the greatest one. Namely, it is something that arises through co-induction, or more, it's something in the semantics community is called final coalgebra. And those, again, excuse the formal terminology, but the point is that you can formalize in a pretty straightforward way these things using Dafny. So let's dive in and let's go at the first point of view. So this compositional / algebraic one. So this is the textbook definition. This is how you would go and take the set of formal languages and equip it with all the operations corresponding to the signature of a regular expression. So again, you identify the 0 as the empty set, you identify 1 as the set containing the empty word, you interpret the plus as the union, the Kleene star as the Kleene star, and so on. And this is how you would do this if you just view the set of formal languages in this the set of words point of view. However, if you do this extrinsically via co-induction, you can define it using those observations you can make on the co-inductive type, because while in the inductive point of view you can think of the different parts of the definition as constructors, those things in the co-inductive point of view become some sort of a destructors, where you can check or make some observations of some potentially infinite data structure. And essentially, this is how you define all those operations on the set of on the formal languages by combining these observations. So for example, an empty language is the one that if you check it for the empty word, it does not have it. And if you try to cut any letter, you cannot do this. Or, for example, the singleton language is the one that if you try to check for the empty word, it does not have it. And if you try to cut the letter that corresponds to the one you put in that set, then yeah, it's there. So this point of view gives rise to something that people call denotational semantics, or like compositional semantics. And the idea is that through the induction on the structure of regular expressions, you can just take, and every time you see an operation, you just use its interpretation on we just defined. And this thing preserves the algebraic structure, namely you interpret plus on the syntax side as the union on the semantic side, and so on. And this is something that is called algebra homomorphism. And in this talk and in this paper we've been presenting, we deal with looking at equality of things. And since we are talking about equality of co-inductively defined things, let me mention the following subtlety. So you probably know about issues with extensionality of equality in Dafny, because it's not extensional. And when you try to compare two co-inductive types, there is a canonical notion of their equivalence, namely by similarity. And it works that you can compare two potentially infinite things if you can make consistent observations between them, and they are in some sort of a lockstep. And of course, on paper, by similarity of languages and their actual equality is the same thing, but to go from bisimilarity to actual equality, you rely on functional extensionality, which is just not supported in the meta theory of Dafny in the current form, as I understand. So we'll just work up to bisimilarity. But again, this is a very technical remark. But you can show that up to equality, this co-inductive notion of equality, this inductively defined map nicely preserves the algebraic structure that is there. Now let's go at the dual point of view. So we went through the algebra point of view. Now let's go into the one through automata. So you can build an automaton whose state space are formal, are regular expressions. And to get a meaning of a particular expression, you'll just look at the language corresponding to the state corresponding to that expression. And it's somehow defined similarly to the one operating on the set of languages. You just say how you would observe the empty word and how you would cut the letter from each of the regular expressions and to what regular expression would go to. So this gives you the output and the transitions map of the automaton. And you can take this automaton and embed it, take it to the world of formal languages and take something that behaves the same way. And this essentially is the map that takes the states of automaton to the corresponding language. And this we'll see in a second is a well-behaved map that preserves automata transitions, namely is an automaton homomorphism, or again, speaking more abstractly, is something called coalgebra homomorphism. Again, it's well-behaved up to bisimilarity. So now let's get to the main point, which is the well-behaved semantics. So showing that these two very different points of view are actually the same, they're equivalent. So that combining like compositional point of view and the automata theoretic point of view are consistent. So this is our strategy. Essentially, the well-behaved maps on which preserve the algebraic structure defined on the set of regular expressions are unique, and same with maps that take each automaton to a corresponding language. They are also unique, if up to bisimilarity. So we will show that the algebraic point of view also nicely preserves automata theoretic transitions, and these guys are unique up to bisimilarity. So it must correspond to the one arising through taking as the one taking automaton to its language. So they are equal up to bisimilarity. And you can flip the picture and do the same thing and show that the map arising through automata theory also nicely interacts with the algebraic structure. And I won't go into detail, but the main point is that the fact that the denotational semantics also preserve automata theoretic structures relies on the fact that bisimilarity is reflexive relation, and it's compositional with respect to the syntax of regular expressions. And the fact that bisimilarity is reflexive actually gets automatically solved by Dafny without any hints. So I would say this is quite impressive. You don't even have to hint these things. The fact that those well-structured automata maps are unique up to pointwise bisimilarity relies on transitivity of bisimilarity, and it's again a fairly straightforward proof. And the flip point of view that operate like semantics arising through automata theory works well with this compositional point of view relies on the symmetry of bisimilarity and its compositionality with respect to the star operation. So let me just wrap it up by talking about some related and future work. So we took this idea of building an automaton whose states are regular expressions circles back to Brzozowski in the 60s. This idea that the nice semantics are the ones which have both compositional point of view, but also some sort of an operational point of view given through automata or automata-like objects that interact the right way, have been introduced in the late 90s by Turi and Plotkin in the framework of mathematical operational semantics. And they introduced something called lambda bialgebra that was picked up later by Jacobs, who wrote a very nice review paper. There was a starting point for us. And in the context of theorem provers, Tritiel also very similarly to us looked at this extrinsic co-inductive point of view at the sets of formal languages. But the different thing we've done compared to them is the fact that we actually gave this well-behavedness result. Regular expressions are quite of a simple language, but you can extend it to some more useful languages for equivalence-based verification, such as cleaning algebra with tests, which allows you to reason about programs with contour flow, with a Boolean contour flow, which has a very nice, nicely decidable fragment, which allows to talk about the programs with while loops and if-then else's. And there is in its extension for reasoning about packet passing software-defined networks. And this co-inductive point of view there is actually very useful for efficient proofs. So long story short, we took quite of a nice and classic pen and paper proof that relies on a not so obvious theory and formalized it using Dafny, which has a very nice support for co-induction. And it allowed us to go formalize those abstract theorems in a quite neat way. So with that, I would be more than happy to answer any questions you guys might have. And thank you very much for having me.
Are there questions?
Hi, nice talk. I wanted to ask you if you have considered the full expressiveness of regular expressions. I mean, the way Brzozowski introduced them in '64, including intersection and complement. That would be the first question. And the second question would be, have you thought about encoding things that involve very large alphabets, like infinite alphabets, where you need to take a more symbolic approach, as is done, for example, with symbolic automata?
Both, I would say both are really nice ideas. So I presume to answer the first bit, any derivative-based some sort of automata theoretic structure is something you could go and define and try to give a similar well-behavedness result. I think it would be very interesting. As for the latter one with infinite alphabets, that could be a very interesting path of the future work, because as you mentioned, symbolic stuff or nominal stuff are incredibly useful, and the tooling support can be tricky for them. I'm only aware of this functional programming language called nlambda, which had some sort of a support for nominal things that also relied on SMT solving. So I guess it will be a very cool avenue for future work. And thank you for the recommendation.
Yeah, thanks. I have a third question and the third suggestion, which is to look at use of regular expressions as a search mechanism rather than a Boolean condition evaluation. Essentially, what I mean is looking at regular expressions with lookarounds, which can be defined with the span-based semantics rather than sort of language semantics on words. I think it would be interesting to know if your approach can also be generalized to this world.
So in that context, I was only aware of the formalization of the extended regular expressions in Lean. I don't know if these, so there was a work presented last year at, I think, Tidy workshop that talked about this, but I think they only had one side of the coin, like this derivative-based approach, but I'm not sure. But I know that people are interested in these. So yes, it would be also a very interesting avenue for the future work.
So there is a work last year at CPP'24 that you could take a look at.
Oh, it was CPP. Yes, yes.
Yeah, which does this. Okay, thank you.
Thank you very much.
I think there are no more questions. Let's thank the speaker again.
Thank you very much. Have a nice lunch.
Thank you, Wojtek. That was the last talk in this session. Lunch is on the third floor.
as time went on, there were more features added to the Dafny AR that we should support. But two things I would like to highlight is what I alluded to before, the data types and the type arguments. The question is, how do we initialize variables? Again, for data types, we might get around it with something called the grounding constructor in Dafny. We might be able to smuggle that into the IR somehow. For type arguments, I would assume we probably need to disable the static type checker and then just initialize the references with a dummy value. And in case it makes you a bit uncomfortable, it shouldn't, because we're proving correctness anyway. And Dafny guarantees that there's a correct Dafny program, at least in the semantics, that every variable is initialized before it's used. So that shouldn't really be a problem. Another thing that I would be very interested in is looking at how to translate traits and classes into an ML language like KML. Because that, while we got away with variables by using references, but for traits and classes, it's not super clear how we would do this. I would assume we need something like vtables, so we use like tuples, function closures, things like that. We probably would need to disable the static type checker again. But again, if you're proving correctness, that really shouldn't be a problem. But beyond, so what is there to be done, right? Beyond just implementing more stuff, right? Because that's always an obvious thing, extend the feature support. Another obvious thing would, of course, be, just prove more things, But these are like kind of going up, like building tall, and building more wide would be something, for example, verifying the translation from Dafny to the Dafny IR. So it's that front end that we kind of trusted should be part of, or could be part of KML, where we then define Dafny semantics and show that our compiler from Dafny to Dafny IR preserves the semantics too. And then if you wanted to go super, wide and like super explore new things, one could think of maybe having a representation of boogie in whole 4, and then also essentially verify the whole rest of Dafny, all the proof obligations that are generated by Dafny, they're properly translated into boogie, and then maybe even this SMT requests when they are given to Z3 and we get some certificate, maybe we can check that too, and like more or less have an end-to-end mini Dafny program or compiler or project. But yeah, this is very much just speculation or like ideas on our part. Nothing concrete has been done yet. And with that, I'm done. So thank you very much for your attention. I'm more than happy to take any questions you have.
So thanks for the talk. This seems like a very ambitious undertaking.
Yes.
Do you have a sense for, is the goal to find bugs in how Dafny is doing this? Is the goal to just have a proof of concept that this could be done, or do you see it being kind of a long-term, something that would be used in the long term?
I think it depends on what one wants to focus on. I think you can very much have the KML backend as something like, because Dafny already has a bunch of backends, right? It has the C#, the Java backend. So making the KML just another backend that has, at the very least, it has the guarantees that once you are in the translated state, you get all the you get like a verified pipeline. So that's, I think, a very practical goal. The end-to-end verification, that's more like a proof of concept and would probably take a PhD or two. I would guess, if you want to do it fully.
Okay, thanks.
Thank you.
Hi. So you mentioned, I guess, like, if you wanted to translate the IR, you said like, well, this works because like it checks the variables are used or they're initialized before they're used. But was that, where did you get that information? Like, is that part of that? Like, that was checked by Dafny in one of these boogie pipeline things, or was that like where, if you were to do a full verification, you would need that information. Where would you get it, and how could you verify those aspects?
I see. So where I got the information that it's always initialized is I think it's in the Dafny in the pro semantics. And and when you verify the boogie, when you verify the Dafny code, it will probably complain. So to answer your question, if I understood correctly, right, for the Dafny to the Dafny AR, that shouldn't really be a. So it depends how much of the pipeline you want to have in KML, right? if you want to have a Dafny to Dafny IR front end, you still kind of need to trust the boogie part that you got a legal Dafny program, all right?
So
I'm not
you
sure.
want to represent the Dafny IR, like that property as well-formedness of the Dafny IR. So for your purposes, that would be a precondition of your theorem.
Right.
And,
yes, exactly. So yeah.
And you intend to do the same thing for all of the like precondition, postcondition, all the things that the SMT solver is actually working on in Dafny.
Well, no, I don't think that's quite correct. So I haven't. So this part is really we just thought about it. We haven't actually done it yet. But the way I would understand it is that there's a set of well-formedness conditions that we have. That is, for example, that every variable needs to be initialized, and then we kind of just assume that that is true, right? So for now, when you give me a Dafny IR, assume you've gotten it from you got it from Dafny translate, which would fail if you didn't verify it. In the theorem, if we would have to prove that, we would somehow need to express that for the assumption all of these things hold, then you get the correctness statement. But if, for example, this doesn't hold, well, then all bets are off the table, and I guess you'd have some form of undefined behavior. But it's a good question. We haven't thought about this in detail.
Thanks.
Thank you.
Thank you. Could you elaborate a little bit about the strategy for proving correctness between the two output results? I think I read that it's done for basic logic and binary, so I'm guessing like propositional logic equivalence there. But what about for more expressive result outputs? Like in what language is the proof of correctness completed?
So it's all whole 4. So it's all written in the whole 4 theorem prover. So the compiler is essentially a whole function, a higher order logic function that takes a Dafny ASD and creates a compiler ASD. So you have a statement, and it's also in the paper for like a bit more details, which essentially says that if you started in some equivalent state and you pass that to the Dafny IR semantics, and then you compile it and have the KML and you pass that, then you get a new state. One that was generated interpreting Dafny code and one from KML code. Then these two states have some correspondence. I'm being very vague on what this correspondence means, but this is just like one theorem that you can, that's a simulation theorem that you can prove and that we start to prove in whole 4. So everything lives in whole 4, really. Yeah.
Thank you.
I hope that's answered the question.
Let's thank the speaker again.
Oh, sorry. Yeah.
Nope, you're good.
Perfect. Yeah. All right. So hello everyone again. For those who
Sorry, Vojtech, can
haven't
you
seen,
hold on
yeah.
for just a sec? I've got an AV issue here.
Okay. Right. Just let me know whenever you guys are ready.
Yeah, sorry, we're running into some more technical issues. I'll give you a heads up when we've got it resolved.
Perfect. Thank you.
Yeah, sorry about that. We're still working on getting this issue resolved.
Fair enough. Do you want me to maybe, I don't know, unshare the screen and share again or something like that? Or
Unfortunately, I think it's something on our end with OBS.
fair enough.
Can you hear us?
Yes, I can. Can you hear me?
Yes.
Fantastic. I'll put my volume down because I hear the echo of myself, if it's fine.
Okay.
But
we can decrease our volume.
oh, perfect. If it's on your side, then it's perfect. All right. I'm glad that all the AV issues have been resolved. So, for those who haven't seen my talk before, hi everyone. And so my name is Wojciech Różawski, and normally I'm a PhD candidate at University College London, where I'm working more on the theoretical side of programming language semantics. But right now I would like to talk about something very informal, more hand-wavy, but also more practical. And I like to think of this as some sort of an opinion talk or some sort of some sort of almost like a video essay or pointing out one interesting thing. So this is a joint work with George and Sean, who were mentoring me during my Amazon internship 2 summers ago. So yeah, let's crack in. So Dafny offers amazing levels of automation for being to be able to write programs and then and write contracts, what they should do or what they shouldn't do, and then verify that those programs obey those contracts. And it, as we all probably know, it relies on encoding to the intermediate language being Boogie, and then generating verification conditions out of Boogie, which are logical formulae whose correctness, whose validity entails the correctness of the program, which leverages the opportunities of possibilities of SMT solvers such as Z3. And the main story of this talk is that as much as this automation is amazing and it's something that by default you would like to have, there are some cases where one might opt for more fine-grained approach. So I'll be talking about fine-grained approach to reasoning about some difficult, and I'll mention what kind of difficulty do I mean, Dafny programs using Lean Proof Assistant. So Lean is a theorem prover or a proof assistant, so some sort of a tool from a similar domain as Dafny, however, more centered towards mathematical proofs, more popular in the mathematical community, and it essentially allows one to develop proofs in this semi-manual conversational way, where in the IDE, which is form of Visual Studio Code with a plugin, one writes the proofs, and then while writing the proofs on the right-hand side, in the editor, one can see how different steps of the logical proof change the assumptions into conclusions of the proof. So rather than relying on automation by default, you are the one in charge of constructing the proof, but also you get this interactive experience of developing the proof. So if you were to compare these two guys, Dafny is a highly, I mean, first of all, they are from completely two domains. Dafny is mainly for program reasoning. It is aimed for also for people outside of the usual domain of mathematics or type theory. It is a highly automated tool where, as much as people say they prove things, I like to think that you don't really prove things in Dafny, but you rather hint them to the SMT solver, which is the one that actually is doing the job, where Lean is a semi-manual tool where you are in charge of developing the tools, developing the proofs. Of course, there are some tools in the forms of tactics that allow you to resolve some kinds of goals, but it's more on the manual side. So let me motivate you why on earth one might want to reason about a Dafny program using Lean. So let's look at this very simple piece of code, which is a split function that takes a string, that takes a character and an integer, and it replies with a sequence type, so a list of strings. And the idea is that we take a string, which might contain some separator. We take a separator character and a number for which will specify the limit. And we're trying to split that string by that separator bounded by the limit. So for example, if you give this Sid, Nick, and Roger concatenated with a semicolon inside, and we ask to split it by semicolon, and we give the limit of 2, then we get Sid and then Nick and Roger, so 2 elements. We don't split these two guys. If we give it a negative number as a limit, and we give again the same string, so Sid, Nick, and Roger, and ask to split it by semicolon. We get those 3 members of early Pink Floyd as a separate elements of the list. All right, so this is how you might go about implementing it. So you could argue it's a fairly simple program. There is no mutable state. There is mutable state, but there is no heap reasoning or locality-based reasoning. You simply go through the string and you accumulate the segment you've seen so far. You keep going through the string, and if you see the separator, then at this point you cut the string. So namely, you take whatever you've accumulated so far, you push it to the working list, and you keep going. And once you're done with the loop, then you take all the remaining segment you might have accumulated until the end of the string, and you push it to the working list. The only interesting thing is this break statement. So the idea is that if we are about to hit the limit, if it's a non-negative limit, then we just stop traversing the string and we immediately go into just remembering the rest of the string. So let's say that we're trying to prove some specification of this code, try to show that this code adheres to some specification. So let's say we provide some precondition and postcondition and loop invariant. So this is how it would look like. Fair enough. So then let's say that you get a following error. Okay, a postcondition could not be proven on this return path. So you inspect the code, and you, as a Dafny user, you think, okay, we return something. There is a loop. Maybe the problem is with a loop invariant, because essentially this is the last thing you enforce before doing this last manipulation before returning. This could be a good hit. It could be an issue over there. However, there is one extra thing. Turns out that the problem might be on the branch that breaks out, where the invariant is not established. And this is something you might be aware of if you're a more skilled Dafny developer, that you know how it actually deals with non-local control flow. But the thing is, in your head, you're thinking about 2 different execution paths, and you're trying to construct 2 proofs with different set of assumptions. Because in one hand, you enforce the invariant and you just do this little manipulation with a finished variable. In the other one, you still have some modification. There is a bit more assumptions on the way. So in a situation like this, I would like to argue that it would be really good to be able to visualize the proof state, not in order so you don't have to keep the mental model of what's going on, but rather you could rely on some sort of a external help saying what is true at a given point, what I'm trying to prove. So now I would like to talk about our proof of concept, how we went about this particular problem. And this is the tool that we've implemented. So we go from a Dafny program, and we extract a bunch of straight line programs that correspond to different possible program paths, and such that the correctness of those individual straight line programs will entail the correctness of the global program. And those programs, those straight line programs, are in a small boogie-like language. Therefore, I'll refer it to as microboogie. And in our case, microboogie is a data type implemented in a lean theorem prover that is equipped with a formal semantics and with formally verified verification condition generator, which spits out you the thing you have to prove using lean, that if you can prove, that means that it's correct with respect to the semantics. And this process of proof is something you do through the interactive semi-manual proof. So let me talk about the first bit of it, which is the extraction of the straight line programs. So we rely on this very neat result from Jean-Christophe Filiatre's paper on formal reasoning about mix programs. And mix is the language used by Knuth in his book, which is a very low-level programming language with non-local control flow. And very similar idea has been studied by Rustan and Mike Barrett, and in the case of Boogie. And the idea is that we construct a control flow graph of a program, which is annotated with preconditions, postconditions, and invariants. And such a graph contains 3 kinds of things. So contains white nodes, gray nodes, and edges, which might be annotated. And the idea is that white nodes represent the code that is being executed. Gray nodes lump the idea of precondition, postconditions, or invariants. Those are just predicates that should be true at a given point once you pass through them. And edges correspond to the control flow. And if there is a some sort of a Boolean formula on them, it means that you you assume that if you take that edge, that thing is true. So you construct such a control flow graph, and then you extract all possible paths between any two gray nodes that do not contain any intermediate gray nodes. And you just concatenate the code contained on the white nodes, as well as the conditional, like the Boolean formulas on the conditional branches. And the idea is that the starting gray node is something you assume to be true, and the ending gray node is something you assert you're trying to show that you would like to be true after executing the program. So you start with assuming the gray node you start from and asserting the one you end at. So let's look at an example. This is the very simple block which ends with a gray node and ends with a gray node. So we assume the precondition, we perform the initialization code, and then we assert the loop invariant. So essentially it means that we're trying to establish the loop invariant before entering the loop. This is how it would look like. Let's go back to the motivating problem. So this is the straight line program that corresponds to exiting the loop in the normal way. So you assume the loop invariant holds, you touch the finished variable, and you assert the postcondition. This is how the other branch stemming from the break statement should look like, where you assume the loop invariant holds, you navigate through the loop body in a way that you take the branch that might break out, and you try to assert the postcondition. So there are two completely different programs that once you prove, they deal with two different set of assumptions. So to deal with these guys in a interactive way, let me talk about very briefly about encoding them in Lean. So here is the syntax of this micro-boogie language, where you can assign to variables whose identifiers are strings some sort of expressions, where you can put assume and assert statements. You have also non-deterministic choice statement, which allows you to model external function calls as well as you can sequentially compose programs. And the idea is that the semantics of such program is a relation between states, where a state is a mapping between the values of the identifiers of strings and the values they might take, which are some sort of a primitive data types like integers, naturals, booleans, characters, primitive lists. And we deal, so we've given semantics of these programs in Lean, as well as implemented the weakest precondition style generation of verification conditions, which essentially takes a predicate, which is a statement about the program, and unrolls the program and accumulates the things that needs to be proved, and generates generates a proof obligation that should be dealt in Lean through the semi-manual proof. So very quickly, to sum up, we've built a very simple prototype tool which supports a small fragment of Dafny, namely the one where you don't deal with heap reasoning, where you only deal with those very simple data types. And we've done a case study on string splitting. And the main lessons I've learned through this is that it was quite straightforward to develop the proofs once you had this level of visibility, that you know what is true at a given point, what you're aiming to prove. On the downside, because of the way it was encoded, there was a lot of sublemmas you had to prove that involve boilerplate properties, which weren't interesting, and you had to do with a manual proof. And this is something I really like, and that Dafny can figure out automatically. And I envision that it will be difficult to build a solution that would target a full fragment of Dafny. So what's the point, you might ask, of this whole thing? I like to think of this as some sort of starting debate, how and what would be the good way of improving the user experience of Dafny if you would be like to be able to see the internal state of the proof. This is something that Rustan mentioned in his keynote about the IDE support. Like, can one add proof state to Dafny? How one would go about this? I'm not trying to propose a full revolution to replace any part of Dafny with Lean, but rather I would love to see similar things that Lean enables being part of Dafny. The bigger question is like, can one improve Dafny support for reasoning about those non-local programs in a making explicit this extraction of different paths, as this is what we've mentioned before, and quite orthogonally to this, how one can use proof assistance to discharge proof obligations for Dafny. And again, this is something that has been studied before. So for example, Y3 or YML are intermediate language. Y3 is an intermediate language like Boogie, where you can deal with, you can rely on SMT solving, but you can also do this, resolve the proof obligations via Coq theorem prover. So one could think that maybe the problem I present is not really a problem with Dafny, but rather something that should be targeted at the level of the intermediate representations of the program, that they're encoded well enough so SMT solver can deal with them, but also they're encoded in a way that you can get meaningful proof obligations to deal with them manually. So here are the two main references I mentioned. So this paper of Jean-Christophe Filiat and Mike Barnett and Rustan Leino. And with that, I would like to wrap up, and as I would be more than happy to answer any questions you guys might have. Thank you very much for having me. I really regret I cannot be in person with you. So yeah.
Anyone?
I cannot hear anything, so I don't know if there are questions or not.
All right. Hello. Can you hear now?
Oh, yes.
Okay.
Yes, it works.
Thank you. Thank you for the talk. So I saw you had the data type that encoded like the assert and havoc and things like that. For your propositions, it looked like it was like a state to prop function. So how are you embedding the like logical part of Dafny into Lean?
That's an excellent question that I would love to elaborate more. So essentially, in the prototype tool we had, we relied on the assertions being written in Lean rather than in Dafny immediately. And the idea was that we relied on the rich annotation system of Dafny, where you could reference Lean specification using attributes in the code, and essentially those were referencing the names of the mappings into prop in Lean. And the reason I done so is because being able to encode a full Dafny assertion language is something I find very difficult. One, because of the well-formatness conditions, such as, for example, conjunction is not commutative. This is a very nice example. It really relies on the ordering and on like how it interplays with well-formatness. Additionally, there is a very interesting interplay between some sort of a meta theory, that in one case you're dealing with a first order logic meta theory, in the other one you're dealing with this type theoretic meta theory. So I kind of avoided the problem. But again, I would love somehow the intermediate language where you can use to write the assertions to be flexible enough to both rely on SMT automation and something you could deal with the theorem prover. So yeah, this is an excellent question.
Thank you.
All right, it's Frank Wojciech again.
Thank you.
Oh, hey, Mikhail. This is the AV guy from on-site. Can you try talking and start sharing your screen? Hey, Mikhail, can you hear me? Maybe we just need a higher gain. Oh, okay. We see your video. Can you try talking again? We can't hear you right now. Just a sec. All right, let's try it one more time. Can you try saying something? Yeah, sorry, we're still not getting audio. But Discord's lighting up on green, so I think it's picking up audio from your side. Okay. Sorry, can you try one more time?
Yes, can you hear me if I speak a lot?
Yes.
I can hear me in echo, so it seems like it should work.
Yeah. You're coming through quite loud, so we've got you at the right level.
Okay.
You're good.
No problem.
Perfect. Can you go ahead and start sharing your screen, and then we'll pop that up.
Yes, let me share my screen. All right. Do you see my screen now? You see my screen and my face?
Sorry, just one sec.
Yeah.
Perfect. Yeah, it's pulled up. We're gonna work on getting you full screen, but you should be good to go.
Okay, you just tell me when I can start speaking. Huh?
All right, perfect. You can go ahead.
All right. Thank you everyone for attending my talk. Today I'm going to explain you how we can generate performant, readable, and interoperable REST from Dafny. My name is Michael Meyer. I work at Amazon Web Service, and this is joint work with Siba, John, Shadaj, and Fabio. So in English, we have an expression that says, let's address the elephant in the room. As you know, Dafny until now has been mostly compiled to garbage collected languages, and which is symbolized here with trucks full of plates going to a recycling factory. And Rust is not garbage collected. So how would we address this problem? And this is the first problem I was thinking about when I was giving the task of taking over this Dafny to Rust compiler that John and Shadaj had worked on before me. And we'll go back to this later. But first, the first question is, why would you even care compiling Dafny to Rust? And I will assume that you are this person in a deep committed relationship with Dafny, and you love writing proof. You sometimes wish it was a bit easier and less brittle, but overall it's a good experience. And now you want to publish a Rust library from your Dafny code. And so this is the case for one of our clients at Amazon. As Ruslan mentioned it earlier, the encryption SDK now compiles to several programming languages, and it's not a coincidence if all these programming languages are the one that Dafny support as backends. And if you see, just this week they released a new Go library based on the Dafny to Go compiler. So it makes sense that they would want to expose their encryption SDK for Rust, right? So for the story, I developed the compiler for a few months, and then Fabio and Siva joined me at the end so that we were able to publish a compiler for Rust, from Dafny to Rust, mid-July last year. So that was a great success experience. Along the way, we gathered a few needs for this compiler because it was based on a novel architecture with an intermediate representation that project mentioned earlier. sorry, Daniel mentioned earlier. And about this, the final output, we wanted the output to be readable so that we could debug it and it would be easier to trust. We wanted also the code to be correct and compiled in a way that can be run extremely efficiently, if possible, because this is what Dafny was meant for. And last, we want to be able to import and export Rust definitions so that the API of our libraries are not kind of weird, they're actually quite readable. And what we wanted was based on what we gathered from our users. So let me first show you a few challenges we faced. Can we improve local names? For example, in Dafny, let's say we have a Dafny program with 11 holidays. We have days off, which is the same number as holidays. And if you're lucky, you get 2 extra holidays and you reassign the holidays to day off. And here you see in the blue, we are overriding a variable with the same variable name. So in every other backend, what you will see is you have 2 variables for these 2 holidays, which are homonymous, which are prefixed with underscore, number, underscore, and they have different numbers so that we identify them uniquely. And it's necessary because we declare variables before assigning them. But in the Rust compiler, we worked on so that we could actually reuse the same variable names and get rid of all this, most of the underscore, number, underscore, so that I think at the end, the Rust generated code is much more readable. And we can do this because we have a novel architecture in which you can even do some post-processing to gather assignments and declarations. Another readability aspect is, can we keep single underscores? Let me explain you the issue. Let's say we have a function, how many dogs can you have? Depends on whether you have a cat, which is a Boolean, another cat, prime, which is a Boolean, and whether you have a yard, well, that ends with a question mark. And if you see, the first 2 identifiers are perfectly valid characters for most programming languages, but Dafny identifiers can have apostrophes and question marks. And obviously, this doesn't fit well into our backend. So what we do for every other backend is we double the underscores, and that way we can use underscores as an escape character to encode the apostrophe and the question mark, which means the identifiers are not the same when they have underscores. So in Rust, we made it so that we can reuse the same names if there are underscores, and if there are special characters, we prefix identifiers with underscore and apply the escaping transformation. And you might think, well, hey, will that actually collide in some ways? Will we have any problems? And the good news is, since the pipeline is written in Dafny itself, the last part of this pipeline, we actually have a lemma that proves the mapping to be injective. And this is in our CI, continuous integration, so it will always remain valid as soon as no one touches this proof. So we have more readable identifiers. Now, can we have relative path? It's something that's almost in every other backend. Let me show you what happens. In Dafny, let's say you have a module living room, and you define a present as either being a toy with an index or a box with a present. And if you import to the living room, and you have a method main, you can you say, okay, in my method main, I have a present, which is a box or a toy of 1. Very concise program. So in almost every other backend, we always mention the living room module. And the reason is it's very hard to import something and make sure there is no ambiguity. So because in Rust, we have control over the final generated tree, we can actually have a post-processing phase which will read the entire tree and factor out this absolute path into import statements, and that's why we can have shorter types overall. And this is very interesting because it resulted in a 20% code reduction in the encryption SDK. So for readability, it was a huge improvement. There are many more readability improvements, but I would like to move on now to the other aspect that I talked at the beginning, how to manage references. And let's go back to our garbage collection. The story was as follows. I was tasked to implement a garbage collector so that we could actually enjoy garbage collection within Rust itself. I did implement one myself. It was not an easy task. And then I realized for maintenance, it would be better to use an external library. There were 2 garbage collection libraries in Rust at the time. one was not maintained, and the other one would require to keep track of the path from the root level of every reference. So the code will not be readable, maintainable, everything you don't want. So then I realized something very interesting is that Dafny is not assuming garbage collection. Dafny actually assumes, if it assumed anything, that objects live forever. Because you could always assert some properties about an object which was a long time ago garbage collected, and still the assertion will still hold. So this led me to thinking perhaps we should do one thing that I wanted to experiment with. We should just have a row pointers and have a way to manually delocate references if we have a good theory of that, which is kind of washing dishes yourself. And the crypto tools, the team is responsible for the encryption and SDK wanted something more like reference counting, so that at least the cleaning will be done automatically. They will not have to add this free statement. And so I also thought we should do mutable reference counting for them, which in some cases could have some deadlocks, but for them it will not be the case. So how to encode mutable references? So in Dafny you have this class York, and you have a new label variable x that is an instance of York. And in Rust, you have a struct of the York, but struct in Rust are just a collection of bytes. So if you wanted to have a pointer, it should be behind a kind of wrapper around your structure. And this wrapper should indicate that it's nullable, reference counted, and mutable. So the reference counted part is called RC. The mutable one is called refcell in Rust, and the York. And here's how it's laid out in memory. It's very interesting. So in memory, if you look at the heap, what the pointer points to, it's a strong count, a weak count, then a borrow flag, and then the actual data of the York class. So since we don't have any runtime borrow checks, we can just replace refcell by unsafe cell, and it works the same. And with the variant with the row pointers, we can actually use non-null instead of RC. We get rid of the strong count and weak count. Now we have the nullability of this pointer, which is done in a very clever style in Rust, because it knows that non-null and RC are not null pointers, so it can encode the 0 as the non-variant of the option type, and that this is a zero-cost abstraction. There are one more zero-cost abstraction that we need is a wrapping with a new type, so that we can fine control the equality, because equality of object has to be based on pointer addresses and not pointer addresses and virtual dispatch addresses like it is done in Rust. So once we did that, we can have pointers that match the semantics of Dafny pointers. So now we have a reference, we have a covariance. In Dafny, it's possible to have covariance. Let's say you have a holiday, and you have a class MLK that extends holiday, and your data type option with our covariant type parameters. And now you want to test something. You do something crazy. You put an instance of MLK into a sequence, into an option, into a sum, and then you convert it to an option of sequence of holiday, because MLK is a holiday. This is possible in Dafny. Rust doesn't allow you to do this normally, because simply the traits have 16 bytes with the virtual table, whereas the classes will only have 8 bytes for the data. So if you really want to do this, we emit coercion combinators that you can use to convert all your data, your types to the types with the traits. But I would advise against it. If you can avoid it, use bound type parameters and try to upcast only at the last moment. So there are also initialization tracking bits. So let's say you want to make a step where you are alive or not, you are eating or not. It requires that if you are eating, you must be alive. And let's say we want to measure the luck, which is an intermediate variable. If you are alive, you define luck to 1. If you're eating, you define luck to be equal to luck plus 1. And this is a bit tricky in Rust, because in Rust, it assumes that every local variable will be collected at the end of the scope. But the problem is, if it doesn't know whether it's initialized or not, it will emit an error that we have to resolve, because it will not be able to determine it. So if you look at the generated Rust code, we need to assign luck a value, which we put as a placebo value, so it's a kind of option type. And with this one, Rust is satisfied. We not emit warning, but you can see that the readability of the code is really affected. So to avoid this initialization tracking bit, we implemented an abstract interpretation over the Dafny intermediate representation. And if you rewrite the program in a way that if you not alive, you return, and if you have food, you assign luck. So in every pass, you know whether luck was initialized or not. And in the step on the right-hand side, you see that our abstract interpretation engine figures out that the Dafny, that the variable luck can be assigned the type Dafny int, which will be collected or not, and Rust can figure out this out by itself. So Dafny also supports external instance methods. Let's say you have a coin flip that returns a boolean, but you define it as extern. And now you have a coin flip int that will convert this boolean to integer. Though you can run this command line, and now you have something interesting that happens is the external method doesn't appear. Excuse me. Yep, something's wrong with my slide. Yes. The external method doesn't appear, but it is being called. So you can actually implement in an external file, and Rust makes it very easy to implement external methods on types in other files. So you can support external instance methods quite easily. Same way you can support external types, although it's a bit more complicated. If you have a time in a time container and you want a get method, you will see that in generated code it will import all the types from an external module, which will import all the types from an external file. This means that in your external Rust file, you can actually have the same module name, same struct that you want to have, and define its own implementation there. As an evaluation, we converted many different projects to Rust, and we had up to 100% the speed of a handwritten Rust code. 15 readability features, which include 11 unique to the Dafny to Rust compiler, and the encryption SDK has 28 external files. As a conclusion, the output is readable and debuggable. It can be made performant. It interprets well, and there is more to come. And you can try it out by yourself with the Dafny Translate or Dafny Build, Run, or Test on your files as of today. And if you want, we can continue discussion on Zulip chat. You can find me there or on this new Zulip chat channel. Thank you very much. Not sure if I hear questions. Will I hear questions here?
Any questions? No questions? Oh, there's one question.
If there is no question, I'd be happy to answer one myself. But go ahead.
So as Ruston alluded to this morning, we had a lot of success using linearity at least.
I had a lot of success using what exactly? Can you repeat?
Sorry, using linearity at the source level to simplify proofs in one way or the other.
Yes.
Since Dafny doesn't have that, do you run into places where it's awkward to satisfy the Rust linearity checker?
No, that's an excellent question, actually. And no, we don't run into that because we only compile to types that are clonable. And every time we need, we clone the variables, we clone the values. So we don't run into this linearity issue. But at the same time, we want to benefit from it. And we have plans to add some annotation or attributes so that you could represent types in our own way. And if you overwrite a variable with itself modified, you could actually compile this to an in-place modification in the compilation pipeline. Yes, we can do this.
Cool, thank you.
Welcome.
Let's thank the speaker again.
Thank you very much.
All right, next talk is by Kanbankot Bunrirong, who will, sorry for that, who will present her master thesis at Imperial College London.
Hello. Okay. Great. So we'll be looking at randomized testing of the Dafny compiler in the CI. I know that's a lot of words I just said, but basically randomized testing or fuzzing is a software testing practice where you generate a bunch of random input and you would put them into the software under test, and maybe one of the input will produce an unexpected output, and then you would know that you found a bug. And when I say in the CI, I meant continuous integration, which is a practice where code changes are integrated frequently, and this often involves automated building and testing. This is the case for the Dafny compiler. So a tool that does fuzzing is called a fuzzer, and in this work we'll be using a fuzzer called fuzzd. This is work done by a student from Imperial College London, Ali, my supervisor, and John Tristan from AWS. I'll tell you a little bit how fuzzd works and how the type of bugs that it can find in the Dafny compiler. So fuzzd always starts with generating a well-defined Dafny program. It will then try to pass that to the Dafny compiler. And at this point, we have an opportunity to find one type of bug, and that is called the compiler crash bug. So given a valid program, the Dafny compiler would just terminate without producing any valid output. It might come with error messages like that. If we find that, we would keep that test program, put it in a pile somewhere, and then we'll start again by generating another program in hope of finding more bugs. If that doesn't happen, we'll try to compile Dafny into all of the supported languages, try to compile the resulting file using their respective compiler. At this point, we can find another type of bug, which is called the non-compliant code generation bug. And this happens with Dafny more than with other languages because Dafny compiles to high-level languages, so these have a lot of rules and stuff. And this happens when the Dafny compiler emits code that doesn't comply with the rule of the target language, so it would just fail at the target language compiler. If that doesn't happen, we'll try to execute all of them in parallel. And here we can find the last type of bug, which is called the miscompilation bug. This is kind of like the most dangerous type of bug because it doesn't produce any errors. It's just silent all the way through until the end. And the only way you can find out if this type of bug exists is if you compile them to multiple languages at once and compare it. Yeah. So why do we give a fuzz? So imagine this is the execution tree of the Dafny compiler. Dafny already have a lot of regression tests in the CI that covers a lot of the branches in this tree. But as you can see, there might be some edge cases that is not covered using regression tests. For some type of software, this could be fine. It could be forgivable to have edge case bugs. But for Dafny, this could mean that in some of these edge, there might be miscompilation bug there. So that means that provably correct code might be compiled wrong and then behave incorrectly. So we're basically giving false guarantee to the user. And fuzzing is actually good at getting into these edge cases because it uses a lot of randomness. So together with regression tests and fuzzing, we have more chance of catching all the bugs and covering most of the execution tree. But then fuzzing and finding a program that triggers a bug is only the first part of the compiler fuzzing campaign. You still have to deduplicate the bug, which is the process where you find out if the bug that you found is actually a duplicate of something that's already known, already reported. So you need to eliminate that. You also need to reduce the test program that triggers a bug. So usually the test program would be really, really long. And you need to chop away all the irrelevant part of it until you have only the smallest part that still trigger a bug. You might need to bisect the bug in order to find out which commit in the history of Dafny compiler actually introduced the bug. Then you just have to report it and maybe monitor it to see how the developer are getting on with the bug. So only fuzzing is automated, well, before this work, and everything else was manual. And it takes quite a lot of effort to go and do all of that. And as a result, we have, like very, very powerful fuzzer that can find a lot of bugs, but then nobody ever uses it because they don't have the time to manage a fuzzing campaign. And that means that we have a project timeline that looked like this. So over time, bugs kept getting introduced. At some point, somebody comes along because they finally found time, and they do a huge fuzzing campaign that discover all of the bugs in the past. But then by that point, maybe the context of the bug is already lost, or even worse, maybe there will be other features that build on top of the code that contains bug. So then if you fix the bug, it will have bad consequences. So then we ask ourselves, okay, what about we do a mini fuzzing campaign as part of the compiler CI? So instead of a timeline that looks like this, we can have something that looks like this. So hopefully with smaller amount of fuzzing, we might be able to find these edge case bugs and fix them while the context is still fresh and nothing else is built on top of it. Long story short, we automated all of the steps that you've seen before. I won't get into the details, but I'll be happy to talk about it after, about how we implemented that. So we containerized all of these things, and every time somebody opens a pull request in the Dafny repository, that would trigger the tool to be deployed and run, and then it would just report bugs back to the Dafny developer, either with pull request comment or as a GitHub issue. Yeah, and I think the tool was quite successful. It has found 3 previously unknown bugs between August to September. But I think what's even cooler is that we learned a lot of things that was not known before. For example, this is something that we've learned from fuzzing Dafny to Rust, which is the previous talk. Because the Dafny to Rust, the Rust backend was being kind of actively under development while the tool was deployed, we run into a lot of issues where the tool wasn't able to tell if an error it's getting is from the feature being unsupported or it has found a bug. So for example, we have this error from when the Dafny compiler, the Rust backend crashed. And as human, you can kind of read and see that it's about unsupport invalid operation. But the tool didn't know. So we reported it, turns out it's not a bug, and we decided to ignore all of the errors with the same class. So that was kind of easy. But then we run into other more complicated case. So in this case, we have a code, a Dafny code. It compiles successfully into Rust. But then when you feed the Rust code to the Rust compiler, it comes out with this error. And once again, this was actually not a real bug, and it's because the Dafny code contain traits that has constant attribute. And during the time that we were testing this, constant attribute on trait was not supported, even though trait was already being implemented. So as human, I don't think we'll be able to tell if this is a bug or it's just unsupported. And the only people who would know is Mikel or Fabio. So this is actually still unresolved, and I think there will be more cases like this. But it does raise the question of, when is it the right time to start fuzzing a compiler? Because on the plus side, you know that if bugs can be found early, they can be fixed early. And as Ali found in his other work, fuzzing can also kind of prevent developer from committing to a problematic implementation or design. But then as we've seen in this work, the fuzzer catches a lot of the unsupported features, and it cannot tell if it's a bug or not. They report it to the developers, and that's kind of annoying, and it's a waste of resources, to be honest. Okay. We also learn a lot of things from trying to automate bisection. So if you're not familiar, bisection is actually a process of trying to find the commit that introduced the bug. And you do this by searching in the history of change of the Dafny compiler in a binary search fashion. So every step of the binary search, you would kind of check out the compiler at that version, build it, and then test it. So if the bug exists or doesn't exist, you just kind of follow the algorithm until at some point you find the first commit where the bug exists. And this would require you to invoke the Dafny compiler in an equivalent manner, like wherever you're in that history. And this turns out to be pretty hard because things change a lot over time. So there were changes to the command line interface, right? You have the new command line now. The old one is getting deprecated. But then at some point, if you're bisecting back in time to when the new command line doesn't exist, you need to invoke the old command line in the way that would produce the same output as the new one. So that's one thing. There are also changes to the compiler default flag values. So at some point, maybe warnings in the compiler would be treated as error, and at another point, it is not. So you need to know exactly where that point of change is so that you can know, okay, after this version of Dafny, I need to expect errors to rise from warnings or just start suppressing. There are also changes to the interaction between the Dafny compiler and the downstream tools. So at one point, maybe the Dafny compiler so when you try to translate Dafny to Java, maybe at some point it would invoke javac to produce class file. At another point, it would invoke javac to produce jar file. And because we need to execute the resulting file, we need to know which type of file we're actually dealing with. There were also temporary breakages, which is normal. There are also changes to the dependencies in the compiler. But I think the point of this is, for compiler developers to kind of be more cautious about the changes you're making, either with the user interface or anything else, in order for automated bisection to work a long time. Because I think Dafny is relatively young, and even that, there's already a lot of obstacle in doing automated bisection. We also run a simulation to figure out if CI fuzzing would have been helpful in the past in finding bugs. So we did simulation with 20 known bugs that was introduced by 13 pull requests. So out of the 10 repetition that we've done, 6 of the 20 bugs were always found. And there were 14 that were just never found. So now let's look a little bit into why. 8 of the 20 bugs were actually missed because of the fuzzer's limitation. So in this case, it would be fuzz delimitation. So for example, it might be because the keyword that is required to trigger the bug is way too specific for the fuzzer to generate. Or maybe the bug is related to recursion, and most fuzzers aren't able to deal with recursion. But I think this would inspire anyone who's trying to make a compiler fuzzer for any compiler to kind of look into how the compiler works internally and think about where its weak point might be. Because for Dafny, because you're compiling into a bunch of other high-level languages, you will need to escape the keyword in those languages properly. So maybe when you make a fuzzer, you can say that, okay, whenever you generate a test file, try to include some of these keywords. So you can check if the Dafny compiler is escaping it properly or not. 6 of the 20 bugs were missed because of complexity. And this is actually interesting because it was found during a 12-hour fuzzing campaign, but it was missed in the 2-hour fuzzing campaign. But I think this is to show that the mini fuzzing campaign is not good enough as a replacement to a longer one. Therefore, we should still keep the longer fuzzing campaign, working somewhere. Maybe as like a nightly fuzzing. So we would have nightly fuzzing, and then we would have like fuzzing in the CI. So yeah, to conclude, I think compiler fuzzing in the CI can be really helpful in catching edge case bugs during development. It should be applied as a complement to regression testing and as complement to nightly fuzzing as well. Fuzzing early is not always the best thing to do, especially when you have things that are not completely developed yet. For automated perception to work long term, the developer should be mindful about changes or maybe maintain a backward compatible interface. And for people who are trying to make fuzzers, in addition to generating interesting programs, you might also figure out how to exploit the compiler's weak point. Okay, thank you.
Yeah, so I'm curious about what the process of, so you have your random program, you want to find the part of it that generates the bug. I'm curious what the process of finding that looks like. I don't quite remember the term you used for it. But are you essentially just kind of pulling out random parts of the program and ensuring that it still should compile and then seeing if it causes the bug?
Yeah, so that is a process called reduction. I'm not sure how much detail I should get into here, but imagine you have the AST of the program, of the test program, right? You can kind of prune part of it, like just cut part of it out, and then you have like a smaller size program. Then you would try to run that program again, see that it compiles, see that it still triggers the same bug. Then you would know that, okay, this is a good version of the program. Another case can also happen that when you take out some part of the program, it doesn't trigger a bug anymore, or maybe it doesn't even compile. Then that would be a bad version of the reduced program. So you would do this repeatedly until you get the smallest size program that still triggered the bug. I'm not sure if is that good?
Yeah.
So you mentioned this 12-hour run compared to 2-hour run, didn't find it. Are these runs stateful? Because, I mean, if you're running these things on every commit of CI, then surely you can get 6 2-hour runs that would be equivalent in, I don't know, bug finding power.
Yeah. So these things are pretty non-deterministic because, again, it's just randomly generating program. And if you go back here, for example, the first program has like 3 things that are required to trigger a bug. And you were just relying on luck that the fuzzer would generate all those 3 things so that it can trigger a bug.
But you could still, like, with 2-hour campaigns, you could still accomplish the same.
We can if we're lucky.
Okay. I guess this is maybe more of a comment, but like you mentioned unsupported operations being indistinguishable from failures and like whether, you know, this would be a bug. I would say that that was obviously a bug in the sense that, you know, a portion of the code that's not finished should have markers saying it's not finished. And if it doesn't, then that should be reported as something
Yeah,
fixed.
it is a bug in the theoretical sense, but then I think we want to be helpful to the developers, so we want to.
Well, and you also want those unsupported operations to specifically be written in a way such that your CI can pick them up reliably.
Well, I think it's already kind of obvious. At least, like in this case, it was easy to avoid, right? But then I think something like this might be a little bit harder to do. I'm not sure.
Well, I mean, this looks like it managed to get past the part where it should have reported unsupported.
Yeah,
and
but
then it went up through the Rust compiler and then it started complaining.
Yeah, I think it would just put more burden on the developer who has to mark things, so like to check that, okay, if there's no constant on trait, if there's constant on trait, I shouldn't do errors, so yeah.
Let's thank Wu again. Last talk in this session is given by Brian Pano from CMU on teaching Dafny.
All right. Hello, everyone. I'd like to tell you a little bit about my experiences teaching Dafny as part of a secure software systems class and what I've learned over the last 4 or 5 years of doing so. So basically, think of this as a case study of what it's like to teach with Dafny. I think the highlight is that you can teach some fairly complex topics with Dafny.
Because of the technical issues earlier, the pause is a bit shorter, so we'll continue in 15 minutes. welcome back to the last session. The first talk in this session will be given by Eric Mugnier from the University of California, San Diego.
So hi everyone, I'm Eric, and today I'm going to present my work that I did with my collaborators at UC San Diego, Laurel, automating generation of Dafny assertion. So before talking about what we actually did, I want to talk about the problem. As we know, like the automation in Dafny is not like fully automated, it is partial automation, and let's talk about like what does it mean. So let's take an example. Here we have a function, parse decimal string, which takes a string, ideally with numbers. So here 123.456. And what we want to have is, as an output, 123 on one side and .456 on the other side. And so if we want to try to write a semi-formal specification, what we would have is like we want parse decimal string to return as a first element S1, and as a second element, the dot plus S2. And so now that we have this kind of semi-formal specification, let's try to prove it. And so a way to do this is, in general, we're going to have a sort of like helper lemma on which we're going to prove these kind of things on the output of parse decimal string. And so first, there's like some precondition. Here it's just about like the number. S1 is made of numbers. But the main thing that I want you to see is the first precondition, for example, saying that like the first value of the tuple is S1, and here the second value of the tuple is the dot plus S2. So we see basically our specification. We have a specification here. And so how do we prove this? Well, we use basic inductions where we're going to start with a base case, and then we're going to call recursively parse digits and DOS on a slice of S1 to get termination. And so when we think about proving things in general, there's the first thing when I think about it in my head is like, is it correct? And the answer is in general, yes. And the second thing, does it verify? And sometimes it tends to be a sort of like difference between is it correct and does it verify? And does it verify, I mean like does Dafny tells you like it's okay? And well, in this case, as I said, it's correct. But it does not verify. And the error that you would get is a post-condition could not be proved on the else path. And so what do you add in this case if you're an experienced Dafny programmer? Well, you add an assertion. And this assertion here is just to help the SMT solver, and it tells that like basically S1 is made of the first element plus the slice that we use after to show termination. And so that's something that like assertion you're going to write kind of all the time, and it's going to take a bunch of like your life away when you're writing program in Dafny. So there's a question is like, can we automate it? And so let's start by a really simple automation. Is like, can we generate just single assertions? Just one assertion. Every time I have a problem, I try to generate one assertion that is going to solve my issue. And so right now, the trend is using LLM, so let's try to use an LLM, and hopefully it will work because they're so great now. And so we're going to use some kind of naive LLM prompting, which tells, like, can you fix this proof by inserting one assertion? And so we try to do that on a benchmark that we'll talk about after. And here is the graph. What you see is the number of attempts on the x-axis. So like basically you try, retry until you get something good, and sometimes you never get something good. And then the success on the y-axis. And so the baseline is my naive prompting, which is basically just this prompt and giving the lemma to fix. And what we see is we don't even get 10% success rate by default. And if we try to be a bit smarter and we add the error message, well, we barely get 15%. And if we think about usability, getting 50% success rate when you try to generate an assertion automatically is not something that we want to use. So the question is, why does it fail? Like, what kind of things does it generate? If we take our previous example, and our naive prompting again, what kind of assertion? So one of the first assertions I will generate is, for example, it's restating the precondition at the beginning of a lemma. It does not help. The second thing is like it states thing about the element of S1 in the base case, where the base case already proved automatically. And the third one is states things about S2, which are not even true. So if we summarize some of the problems that we have is like, these assertions are not helpful, they're potentially incorrect, and they can be in the wrong location. So can we do better? And that's where we come. Laurel is basically a tool that generates assertion by leveraging large language models. And so how do we do that? Well, we try to answer two questions that you would ask yourself when we try to write an assertion. The first thing is like, where do I put this assertion in my program or in my lemma? And the second thing is what? So what kind of assertion does it need? Like, does it need to know about like this slicing that I showed before, or what kind of type of assertion? Because there's sort of kind of type of assertions. And so what we start from is first our lemma, the error message that we got, and then the code base in which our lemma is made. And we're going to say that like, so at the beginning, your code base is going to be completely empty, but at some point, you're going to arrive to the sort of point where you already have some lemma with some assertions that are already there. And so for the where, we're going to use the error message to basically try to find a location, which we call the placeholder, to find a location for this assertion and basically give this location to the LLM. For the what, we use a sort of like more interesting hypothesis, which is the missing assertion are likely to be similar to the assertion that you previously wrote in your code base. And by doing this, we can already extract a sort of like assertion that we think will be similar, and I'll explain how this similarity works. And then we give this both of this input, the first assertion that is similar and the location, to the LLM, and this is what gives made our project, Laurel, and we are able to successfully generate our assertion for S1. So now I'm going to dive deeper into the where and the what, and what we actually did inside. So the where, the assertion placeholder. So we have kind of like some rule on how to find this assertion placeholder based on the error message. So the first thing that we see when we read the error message is, first, well, the error message indicates us a faulty branch. So if there is a faulty branch in the error message, we're going to restrict automatically the location of the placeholder to this faulty branch. Pretty logical here. And that's something that a user would do too. The second thing is, well, here, for the sake of fun, I added a sort of like intermediate variable, S1 slice. But basically, it's to tell you that, like, in general, in this faulty branch, there are already like variables or assumptions. You want to basically be after that, so you can include them in your assertion. Basically, use what has already been done in your proof. So in this case, you need to be after that in the program. And the last thing is like, basically here it's telling us like, oh, there's a violation and this violation happened on a return path. So basically we want to be as close as possible to the violation. So like at the end, basically at the return path, the last thing they stated. And so when we do this, basically we kind of restricted the location to only one line. And so we place a placeholder here. So we saw the where. Now what about the what? Well, what we say is we have a lemma, it's missing an assertion, and what we're going to try to do is try to find similar lemmas because we're going to they're going to have similar assertions to the one that we're trying to generate. And so let's take these two lemmas that, like, if we take with a human eye, they kind of look similar, but the question is, how do we compare them programmatically? And so there are different methods in the related work. On one side, you have like text-based, that's really efficient, so neural embedding, TF-IDF, all these kind of things, but they don't have like a sort of like understanding of the code structure, and they're kind of sensitive to, for example, variable renaming. On the other side, there's like all of tree-based structures, so let's say like you parse your program already, and you're able to get the AST, and then you're going to do some kind of tree edit distance to see how far it is. And this is a bit more complex and a bit more involved, because tree edit distance has some kind of complexity, and also like getting the parser to work is a bit harder than just the text. And so the question is, can we kind of be in the middle? And yes, and that's what we do using a hierarchical distance, where we first start by the character, so the text, and then we go one level upper with the tokens, and then we have this measure of similarity above, like with the lines, and we encompass all of this into a sort of like measure of proof similarity. And so if we try to apply this to these examples, we see these colors that like basically tells you which line are similar, and then we can compute a proof similarity from this. But what I want you to see here is that if we kind of do this technique here, what we will see is like we will see the kind of same structure with the if-else that are appearing here, which don't have like these S1 and S, which are a bit different. And I guess like some text base could like match them well, but like the main thing is like if the body of this if and else is big, like the text base might not actually work, where like in our case, you would actually extract this structure. So finally, how does it work? Like I told you, how does it work? I want to tell you how well does it work. So the baseline, we saw this, so I'll pass on this, but I'm going to talk about the assertion placeholder, the proof similarity, and finally a Dafny gene dataset on which we evaluated all of this. And so the thing about our Dafny gene dataset is it uses like 3 code bases that are like all in Dafny, of course. So the first one is the standard libraries, then there's CDR, which is not anymore in Dafny, but like is an example of like pretty involved Dafny proof, and Dafny VMC. And what I want you to remember about this is like basically what I call extracted assertion here are assertions that if you remove, the proof will instantly fail. So no brittleness, no kind of thing, like just instantly fail. You remove this line and it will not work. And one other important thing that I want you to remember is that these lemmas from which we extracted the assertions are in general decently big. They're at least more than 10 lines, although some like at least 10 lines, and like some of them are like even above that, and which means that like as we saw before, like the proof get more involved the more lines there is in your lemma. And so how well does the assertion placeholder work? So start from a baseline. We add a placeholder on top of the baseline, so basically we provide the placeholder. And what we see is a 2 times improvement over the baseline plus error. The other thing that we see is already on the first try, you get close to 25% of success rate, which means that basically running once is in general most likely enough. But still, we get less than 35% success rate, which again, in terms of usability, we're not there. And I'm talking only about single assertions. Now we add proof similarity. And so here I have 2 things. The first thing is like we take a random assertion from the same code base. And the second thing is we use a similarity, which I call dynamic placeholder. But we use a similarity metric to extract our assertion. And what we see first is example assertion from the same code base are beneficial. They will help an LLM to generate the good assertion. The second thing that we see is example assertion that are similar using a similarity matrix are better. Like we actually get a better performance. And finally, while using this technique, we're finally above like a sort of 50% success rate to generate this assertion, which kind of starts to be potentially useful, although like there's still a lot of work to be done. So in summary, Laurel is a tool that automatically generates assertions by leveraging LLM. We use 2 things, the assertion placeholder and lemma similarity, and we use this on the Dafny dataset. And from the first thing, we get 2 times improvement, and on top of this, when we add the similarity, it is 30% on top of this. Finally, I want to say that we released a dataset Dafny Gym that is available, and it's a nice website with an image generated by LLM. And also, this will be appearing at Uppsala 2025, so feel free to check this when the full final version is out. And even more important and interesting for me is now that I like worked on the tool, I do the thing in the opposite order. I want to understand what users want and need. And so I've been trying to do a sort of user study on understanding like how does Dafny affect software engineering in general. And so I'm looking for people that like used Dafny in like decent sized project like in industry to be interviewed. Yeah. So thank you, and I'll take any questions.
Thank you. If you can go to the slide with the table with the numbers of assertions, I guess there was like about 1,000 assertions for each one, or for the first 2, and only 50 are the ones where you say you remove it, the proof fails. So the others, you can remove them and the proof still passes, or?
So this is not exactly true. So there's one part of the answer that is boring, is the first way I extracted assertion was not great in terms of like program. So I was doing this using regular expression, and they were not catching all assertions. After that, I implemented this better, and I could identify more assertions. The other part of the answer is, yes, there's a lot of assertion that you could remove and it wouldn't change anything, or it would maybe affect the speed at which the proof pass, either negatively or positively. So I think there's two. There's first, the extracted assertion could have been done better. The second thing is, yes, there's still a lot of cleanings to do in these assertions.
Thank you. And another question, if it's fine. I guess if you look at you have about 50% success rate at the end.
Mm-hmm.
Did you try to look and see what kind of assertions it gets and what kind of assertion it fails to get? And if you have some kind of intuition about some mental model about what it can do and what it cannot do?
So we tried, and I think there's like the easy answer, which is the longest the assertion is, the more difficult it will be. Then if it's a sort of like unique assertion, it's the first time it appears in the code base, you might get a success rate that is lower. But the maybe more interesting thing sometimes is that like, so LLMs are really good at understanding just by seeing the name of a lemma or something, what it does. And so sometimes they will try to like use in the assertion some kind of like function or things like this. And this function wouldn't exist, but would be really close to one that exists. And so if you had like some kind of like fixing there, because it's called hallucination. It's hallucinating that this function exists, which it doesn't. But if you would be able to repair this assertion by just changing one or two characters, you would actually get something correct. So hallucination is a problem.
Thanks.
Let's thank the speaker again. The next talk is by Simon Henninger from the Technical University of Munich.
Okay, short delay on the presentation. Sorry about that. Thank you. This is fine. Yeah. Just plug this in. There it is. Okay, thanks a lot for the help. Hi, so I'm here to talk about REM-CTS, which, as the slides are showing, is an approach to synthesizing programs for multi-step problems using a verifier, an LLM, and a tree search. These are all my co-authors, most notably David Brand-Fonberner and Nada Amin from Harvard. I'm going to start by talking a little bit about the setup. What are we actually trying to do? Then I'll introduce our algorithm, show you some experimental results, and go into discussion. All right, first the setup. As we've heard very often today, here's the kind of basic pitch for this kind of arrangement. An LLM is pretty good at generating code, but it's sometimes unreliable, by which I mean it's probabilistic. You know, it could output anything from some kind of brilliant proof to something that's really not very smart. Formal verifiers, on the other hand, are reliably correct, barring any bugs, but they can't generate programs. So why don't we just combine the two? Why don't we have some kind of mechanism where an LLM is wrapped into a formal verifier? The LLM just can keep generating stuff, and we'll use the formal verifier to kind of sift through the stuff the LLM has generated, checking which parts of that are good and which parts of that are not. That way, we kind of are reaching a best of both worlds scenario, where we've got the creativity of an LLM and at the same time the reliability of a formal verifier. For that, we need a language. Dafny and Coq come to mind. Our idea is here pretty basic. We give the model an English language prompt. You'll see one on the next slide. And then we have it generate specifications, code, and proofs of correctness. So in practice, this often looks like, hey, in Dafny, generate this data, write this data structure. And then write a function that works on this data structure. And then prove some relatively simple proposition about this arrangement. Here's an example. This is very simple, very, very simple problem. The sort of thing that you would see in like the very first week or maybe 2 weeks of an undergrad class on program proving. The problem is write a function repeat that takes an integer x and a natural number n as inputs and returns a list of length n in which every element is x. And then write the obvious lemma about this. We started out just kind of feeding this into the model. And it's worked well for a while. We're kind of monitoring everything. But of course, the question comes up, can we actually trust that the model will output correct specification? Right, is right here, we're starting out with something in the natural language. So we don't actually verify like end-to-end from the prompt into the verifier. And it turns out, and we're kind of trusting on the model to translate the specification according to which the code will be judged. Again, this worked well for a while, but at some point the model started doing things like this. When it found out, hey, looks like actually our like the code we were enforcing for the sorting works really well, even on an empty list, because the only theorem here that we were checking for was like, the output of the function sort is always sorted. And this smiley face is real. This was actually in the model output. This will haunt me in my dreams. I feel like this was the obligatory AI safety discussion here at this workshop. So the kind of solution we came up with for this is we actually internally we have more than just the word prompt. We also have a set of these functions. We call them final check lemmas. These are not visible to the model, but they're kind of just ways for us to communicate with the verifier and saying, hey, we expect this lemma here, repeat correct, to exist and to have exactly this shape, right? And then we inject this whenever we call the verifier without showing it to the model, and the verifier is going to break if the model has not fulfilled its promise to actually create this lemma. Okay. Informally, let me give you a vague idea before we get into the theory. The idea is we start out, we have the LM generate. The same way that, if you just put this prompt into ChatGPT, and then you'll find out if you do this, if you put word prompts of verifier problems into ChatGPT, so you find out sometimes it will work, sometimes it won't. And if it doesn't, you could just press regenerate and try again, right? That's the kind of naive approach here. And our idea is, hey, why don't we kind of interrupt the model every now and then? We generate a little bit, and then from that generation, we check with the verifier, hey, is this code actually correct so far? If it is, fine, we keep generating. If it isn't, then we have to backtrack a little bit. Okay, and we're formalizing this here by saying, hey, we have states, and the state is some kind of string, the prompt and a partial solution. Then we have actions, which are units of a program. That could be each line, if the line does something that's actually self-contained. Of course, if the line is just part of a function, that would be the whole function. In Coq, it would most likely be a command ending with a dot. And then through our dynamics is we concatenate these. And we have a reward function. So the reward function is defined by the verifier, obviously. We have reward 1. That's an accepted complete program, i.e. the prompt is done. We can stop generating. We have, 1 means it's okay so far. We have -1, that's for a rejected program, and 0 for an incomplete program. Now you might be wondering, hey, Dafny doesn't really tell me whether my program's incomplete. We have heuristics here that kind of are able to tell that are supposed to discern between just something that's incomplete, as in, for example, there's a missing brace or something, versus something that's actually already flawed. One is verified and has failed. And this also, by the way, we're not really distinguishing here between verifier errors and compiler errors. It could be either of those. From that we build an algorithm where we have some prefix, feed that into the LLM, try to expand it, feed this into a verifier, and then check, is this complete? Well, if it passes, we check, is it complete? If yes, we stop. If no, we add it to the tree, give it a high score. If it doesn't verify, then we can either go back to the LLM and say, hey, generate more stuff. This is incomplete. This would be this non-scorable situation here. Or we say, no, this is failed. Don't add, score -1. Okay, let's show you some results. These results are using FinCode Llama v2. We're just using one model here, keeping it simple. We have 15 problems that are all hand-designed. This mainly because, of course, the algorithm I've shown you works best when you actually have stuff that requires multiple steps. And there isn't very much in the way of workshops out there for problems of this kind. And then we evaluate based on passity. Passity means the probability that it passes, that we generate a program given a budget of T tokens. Again, if we just asked, hey, can the model generate this? Theoretically speaking, in infinite, using infinitely many tokens, we kind of have a problem of probabilities here because the model can just try it on indefinitely and it will most likely solve every problem, if the problem is solvable, of course. So we have a token budget. We have 3 baselines. The first is whole sampling. That's relatively similar to that intuitive approach I was just talking about for you using ChatGPT and just pressing regenerate until it works. We use a kind of more classic MCTS with rollouts. And then finally, we have reflection, which has the model print something and then feeds the verify feedback back into the model, asking the model to self-correct. Here's the results. This is for the problem I've shown you earlier. You see that our stuff is, let's start with the Dafny here. You see that our stuff succeeds at relatively high token budgets here, 5,000 tokens, with about a probability of 0.5. So about half the time it was able to generate a problem, to generate a program and prove its correctness. You also see that for Coq, the numbers are overall much lower, which kind of brings me to the discussion. Since this is the Dafny workshop, what is happening here between Dafny and Coq? Our presumption is Dafny's semi-automation might make proving a little easier for the model. So all the comforts that Dafny has introduced for human programmers are also working well on the model. We not only have the data I've just shown you, but actually there's also several test cases, e.g. a BST, which the model actually is pretty much unable to solve in Coq. but it solves them relatively consistently in Dafny. We think this is most likely due to a bunch of reasons. First, I mean, there's just fewer tokens to generate, and fewer tokens means there's less of a chance to mess up, right? There's also more familiar syntax, which means, I mean, the models that we're using have not been, they're not like specialized necessarily on Dafny or Coq. So, you know, the fact that Dafny uses a syntax that's more close to other languages might help the model. And of course, our mechanics is the model tries the proof once. It might get to try it again. If it still doesn't work, we'll backtrack actually even further. So in Dafny, this heuristic seems to be right in many cases, because you know, if your proof isn't simple, it's likely that your code is wrong. This is not the case in Coq. In Coq, it's often the case which is the proof is too hard, and so we will needlessly backtrack and backtrack and backtrack, leading to this poor performance. Okay, that all being said, what have we seen today? Formal verifiers can act as can operate as drop-in value functions to guide search. We think there's a lot more work to be done. A lot of it is based on, a lot of it is like for the data collection that we're using, we'd like to have more and harder problems. We'd like to have better models here. Also models that are actually like more specifically trained on verification. We'd like to improve efficiency of our measurements. We'd like to actually have learning here. You know, what if a model were to learn how to use, how to write Dafny? And we think that, you know, for that advantage that I just showed on the slide before, there's actually a lot that can be done as well. You know, how do we improve Dafny's semi-automation further for it to kind of match up with the model's intuition more, and let verification kind of guide the development of a proof by an LLM? Thank you so much.
So when it comes to benchmarking, there's a number of Dafny benchmarks out there.
Mm-hmm.
You might think that if you have a system for doing multi-step development, it should do well on these presumably easier single-step ones. So did you try even informally on these other benchmarks?
We've tried very informally, yes. I would say based on that and also based on my intuition, it will work, but probably the distance between our method and whole sampling, for example, would be much lower, right? Because the idea here is for us, we are like whole sampling in that we keep regenerating things, but we try to be smarter about what we regenerate. And if there's only one code unit in the whole problem, then basically we're just doing the same thing as whole sampling, right? So there's, at that point, very little benefit to doing this.
And are all of your changes sort of monotonically increasing, or do you ever like delete or change earlier code?
Well, we backtrack if things don't work out at all. But it's never like we just change one piece. We would completely backtrack, just remove everything, and then explore the branch anew.
In your Dafny comparison, you were looking at passive T, so you're
Mm-hmm.
basically considering the budget of the LLM. But I'm curious. There's also the budget of the computation that Dafny and the backend that it's using would be spending, and I'm guessing that Coq is much, you know, it can give both failures and successes much quicker than Dafny because it's not running an SMT solver with all this stuff.
Mm-hmm.
So, like, if you control for that, does this gap narrow, or like what happens? I don't know. Have you looked at that?
Yeah, we have. We've looked at this mainly in the sense of measuring how much time is actually spent in the model versus the verifier. And and luckily for us, maybe somewhat demotivating for those who are working on optimizing these compilers, it's actually negligible, the time spent within Dafny or Coq. It's like, I don't have the right number here, but I would informally tell you it's something like 1% of the time being spent in there.
Hi, my question is more about the setup of the problem. So you basically give the English description and you're expecting the LLM to come up with the code and the spec, right? So how do you confirm that both the code and the spec are meeting the English description? So for example, if you say that sort an array in ascending order and both the code and the specification generated corresponds to the descending order, which is, it verifies, but it's not meeting what the English description says. So how do you evaluate the correctness in this case?
Yeah, great question. That's what we have this for. So these are the check lemmas. those are not visible to the model at all. The model always sees only the English prompt and the code that's already written. But those are injected after the code that the model has written whenever we call into Dafny. Where the idea is, so this is a little hard to read, but the idea here is the model is supposed to write a lemma repeat correct. This is in the prompt. And we define a lemma called check repeat correct, which does nothing but just call repeat correct. So if repeat correct did not exist or did not do what it claims to do, then this would likely cause a compiler error or a verifier error.
So kind of in relation to Brian's question about the other benchmarks that were used with whole program synthesis, do you have some comparison of like, are your benchmarks longer in terms of lines of code, or do they contain multiple functions, or how do they, can you actually say even, like, can you see the effect of this multi-step to say, oh, prior approaches, they only synthesize roughly 10, 20 line programs with a single procedure, and we can go up to 100 lines with 5 procedures, or where is it at?
Yeah, I would say that the main difference is really that our tests are kind of covering a different scenario. It's one where we let the model work a little bit like a human programmer would, who has an IDE and who is defining one step after another. The benchmarks, most of the benchmarks I've seen actually are more kind of the sort, complete this one function, right? Where often actually there won't even be an English prompt. It will just be the beginning of a function. The whole thing ends at the curly brace, and then it's asking the model to write at the end of the function. Our stuff, I guess, is able to check whether the model is able to do all of these steps itself, from specification writing up to this. I don't really have a good intuition about the possible length of things. I can tell you that we have, I think the most complicated example we've had were like more complicated sorting algorithms, which are, I think, including proofs, something like 100 lines.
Hi, thank you for the talk. So you gave some intuitive explanation into why it could solve lesser number of Coq problems than the Dafny problem.
Mm-hmm.
Is there a similar explanation as to why some of the Dafny problems weren't solved? Meaning, is there some easier program in the benchmark that it could not solve?
Yeah, I think this is kind of a continuation of the general problem with AI, or with LLMs in particular, which is that it's sometimes unintuitive which things it can do versus which things it cannot do. I would say broadly, more complex problems are less likely to be solved, right? But there's so many factors, especially when you're looking at problems that are relatively simple, like the ones we're using, including things like, has this been in the training material, that it's hard to tell.
So maybe there is an explanation that all the problems that it can solve are actually very easy, and it's not really a big deal to solve those problems at all. So have you looked at some qualitative analysis of what kind of problems it can and versus cannot solve?
I think the only answer I can give to that is we are trying, or we've tried to compile a pool of problems that's relatively, that has all kinds of complexities. And in general, I mean, the only real heuristic that I have to figure out whether a problem is hard or not is kind of thinking about which week would an undergraduate student have to be in of some problem proving class to solve this. And I would say there's no correlation there. The model is especially, I think, okay, here's maybe one weakness of the model, and also of this approach, is that very often you've got things like relatively simple problems, and then you build on top of those. So you add extra constraints, for example. These are simple for humans because we can kind of abstract away there, and we can be like, okay, this is actually a two-step problem, You're not two-step in the sense that there's one function, then another function, but two-step in the sense that I modify the existing code to add this extra constraint. The model tends to perform relatively poorly at those. I assume it's because it has to keep too many things at the same time in its context. There is, and then whereas in problems that kind of would seem hard, like again, kind of more complex sorting algorithms, I would say are pretty hard to prove, especially compared to the simple stuff here. The model is actually pretty good.
All right. I think we need to move on. Let's thank Simon again.
Thank you.
Our next speaker is Gabriel Poesia from Stanford.
Okay, let me. Hello, hello. Is this good? Okay, let me try. Okay, that's a good idea. Okay, this must be better. Hey everyone, I'm Gabriel, and I will be presenting on our work on Dafny annotator. This is joint work with Chloe and Professor Nada at Harvard, and I'm a PhD student at Stanford. Okay, so I think we all know that bugs cost a lot of money, and it seems like they cost a really surprising amount of money if you've seen these reports on the cost of software quality. There are some estimates of like 1.5 trillion in 2020, for example, in the US. But in principle, we have this amazing thing called software verification, which could prune a lot of this, the cost of bugs, right? So why is it not the case that everyone is using it yet? And unfortunately, it might be the case that we're still at the stage where the cost of verifying significant software to the level where we would not see those failures appearing might be higher than actually just waiting for the bugs to happen and fix them, which is unfortunate. We don't want that to be the case. So then we have to think about, okay, so what are ways in which we can lower the cost of formal verification? And there are, I think, for sure more aspects here of developing verified software that are not covered here, but at least two of the obvious targets that we have are the cost of specifying formally. Usually people don't think about this or are not even trained to think about what their code actually does. So if this is a square root implementation that someone might write, that looks like normal code. But for a regular programmer, now that I have to write a logical formula that says what this does or what I intended to do, that is an additional cost. But just stating what we want the program to do is not usually enough. We usually also need to provide the verifier with some artifact, some proof, or in Dafny, less than that, maybe some invariants and assertions would be enough. And Dafny really tries to shine in this second stage for using Z3, as we've seen, instead of rely on users to interactively develop proofs. But oftentimes, even when we insert some logical notations in a program, Z3 doesn't seem convinced. And it's often unclear, as many of the talks refer to, if it is that we just have a bug, or if Z3 is just not yet powerful enough, or maybe the version changed, and if I had done this last month, it would have worked. So in this talk, we're just going to focus on one particular scenario here, which is the second case of convincing Z3, which is true. We assume that we have a function that is already correct, which was not the case here. So that's another problem. Maybe Z3 is unconvinced because you actually have a bug. We're assuming that you have no bugs. You wrote you have a method in this case. We're not actually dealing with functions. That is correct, but has no annotations. And Z3 cannot automatically prove its correctness, according to the specification that was written. And we're going to ask whether language models can help a user in this scenario, where they wrote regular code, and they actually wrote their specification of what they want the code to do, but the verifier is still not convinced. OK, so this leads to this tool called the Dafny annotator, which will basically work as this diagram shows. You have a program that's already written there, and then an LLM will try to incrementally add annotations until hopefully Z3 is convinced. So we basically repeat this process of giving the language model the program that we have so far, and then ask it to output one annotation that it would add to this program. It might be an invariant, treasure loop, a decreases clause, for example, to prove termination, or an assertion, or anything. OK, so we'll repeat this very simple greedy annotation algorithm while the method with timeout, or the method still not fully verified. We'll use the LLM to propose a set of candidate annotations to add to this method. We'll attempt in parallel to insert these annotations at each of the syntactically valid positions to lower the burden on the language model to actually localize where to do this. And then if Dafny accepts that annotation anywhere, we'll add it there and repeat. And repeat this until until either we verify the method or we time out. In our particular experience, we use 5 and 5 iterations and 5 candidates each time. And OK, so this is a super simple, straightforward system that we could try to build on top of current LLMs, right? And then we can ask, OK, so how well does that alone work? So we evaluated this using two base models, Llama 3.1, 8b, and CodeLlama 7b. So these are relatively small models that you can run on not huge GPUs at this stage. And we evaluated them on verifying programs from Dafny Bench, which will be, I think, maybe the next talk. So that will be. But as far as I know, Dafny Bench is the largest existing collection of Dafny programs that was collected from GitHub after some filtering and making sure that they compile and run standalone and so on. So what we did is we held out 20% of Dafny Bench for testing, and we'll also evaluate whether training the model in the relatively few number of programs that we have helps. And so for those test problems, we stripped all of the annotations, and we filtered out the programs that verify even without the annotations, which turned out to be most of them in this case. I think in Dafny Bench, it's more than half. I think like maybe 60% don't need any annotations. But a lot of the problems come from, for example, problem sets and classes, so the annotations are more kind of illustrative rather than actually required. Yes, so OK, so the one small detail that appears here is now that we have some training data, possibly, and we'll see how that affects the model, how do we train the model to use those programs? So language models are trained to predict the next token, given some tokens that exist so far. So the most straightforward thing you could do is to just train them on the programs that would reinforce that those are the tokens that it should generate in sequence. But that's not actually very helpful for this task, because here we have this format where we have a partial program, and we want the model to output one annotation to add to this program. So what we do is basically we strip all the annotations from the training programs when we do that, and then simulate this process of adding back the annotations one by one and asking them, making a training example that is like, if you have this program, this is the annotation you should predict, which is the next one that comes in the program. And then we add that, and then if the program still doesn't verify, there's another annotation that comes from the human program and so on. And we have that process. OK, so unfortunately, large language models have this large in their name, which usually means that both the models are large, but also their training data is also quite large. And it's hard and kind of unstable to do fine-tuning with small data sets, which turns out to be the case even for Dafny bench. So if you have Llama 3.1, just the base model can verify 15% or around 16% of these held out programs. If we fine-tune on some proportions of Dafny bench, we see this kind of unstable behavior of like, if you fine-tune on everything, there are a lot of actually low-quality programs in Dafny bench. It doesn't seem to help the model. But there are some subsets of Dafny bench that actually give it a little boost, up to 20%. Code Llama, which is a similar-sized model from a previous generation, actually benefits quite a bit more from fine-tuning. So it goes up to 40%. But OK, so usually one of the so OK, we get those numbers, that's fine. But usually that's not 100%, and we would like it to be 100% in the ideal case. And there's always a question when you have a black box component in your system that's like a language model. It begs the question of how can you improve this system, right? If it depends on this weird agent there that's making predictions that you can't really control. So it seems like fine-tuning generally helps language models. But if we want to rely on this recipe on fine-tuning them or more and more data, then we need data. And unfortunately, there's not that much data on Dafny out there. Dafny bench is kind of already most of the examples that we could use to fine-tune the model for this task. So what do we do? Maybe we just wait a couple of decades and wait for people to write a lot more programs, and then our language models will be great. That's one way. But if we want to speed that process up, there's another idea, another set of ideas that have been explored in language model space these days, which is to generate synthetic data. OK, so this introduces this method and data set that are called Dafny synth, which is a little bit of a wild idea, I would say. So the idea here is that all we want to make the system better is more examples of Dafny programs with annotations that are actually required to verify the program. It doesn't actually matter what these programs are or where they come from. So the high-level idea that we'll pursue here is to just set up an open-ended generation, open-ended system to generate Dafny programs. We'll see exactly how that works, but the basic idea is that we'll try to combine this generative model, which is the language model in this case, which can give us whatever we want it to give. It's not very reliable, with a verifier that can actually give us some stronger signal. In principle, these two components together could give us an unbounded number of verified good Dafny programs that we could use to train and then improve the system. So the idea is that we incrementally generate this set of programs, and the verifier will let us filter logical annotations and specifications that don't match, basically. And then after we do this and we collect a large number of programs, all of these examples can serve as training examples to fine-tune our model. And then we can see if that helps at all. So the idea of Dafny synth is this generation pipeline that is basically growing a graph where each of the nodes has some content. There is a root node that's just there to kickstart the process, doesn't have anything in it. But then from this root node, or by using language model, we'll propose high-level ideas of possible programs we could write in Dafny, in natural language. So that will give these nodes in this graph, which we'll call the idea nodes, which will just be text in them. And then given an idea node, we'll have an editor that will, one component we'll call the implementer, which will take this idea node and try to write not a very ambitious, like just a small Dafny program that's kind of going in that direction of what the idea is describing. So this gives a program node. Given a program node, we'll have editors that will then try to make this program more complex, like implement new features, maybe edit some of it, or maybe re-implement what is there in a different way, and so on. So this will be basically these editors. So proposer will create idea nodes. Implementer will take an idea node and try to write a program, which we can check if it's valid with Dafny. The editor takes a program, proposes a patch, so that will be applied, gives the new program. And we also have we found that it's better to try to keep programs that are syntactically valid but don't verify yet, and then let this annotator try to then annotate them, and sometimes you are able to eventually get a verified program. Yeah, so in principle, we could put money as much as we want and get programs on the other side, and then see if that's good training data. So this gives a graph that would look a little bit like this. And just as a concrete example, so from the proposer using GPT-4o, we'll sample, if sampling a bunch of ideas, one idea that we'll come up with is a program that verifies a priority queue and ensures that the elements, that the order of the elements is correct based on priority. So that's one of the ideas that will come out. I could not find actually this on Dafny Bench. Like if you grab for a bunch of these keywords, I did not find a priority queue in the existing programs. But GPT-4 will actually like start to implement a priority queue, and after a few edits, you'll get a few, like 150 lines of code of a class that implements a priority queue, has a bunch of annotations and so on. So I think this, yes, this can go surprisingly far, even this very basic idea.
Was the priority queue itself suggested by GPT?
Yes. So of course, it has seen tons of programs that people wrote in other languages, right? But the useful thing here is that it has, we don't have this one in Dafny, so that's already a win. Yeah, so in Dafny Synth, we use GPT-4o from the version from many months ago to implement all of these editors and spend $10 of OpenAI API credits. And $10 gives us a similarly sized data set to Dafny Bench, which is the programs that are collected from GitHub. So it's not a lot of money, and it's already quite a bit of data. And then the question, of course, is this useful training data? And maybe surprisingly, the answer is yes. So if we just augment the existing training set of Dafny Bench with Dafny Synth, we get one of the base Llama 8 model to verify 50% of the programs, or a tiny bit beyond that. Yes, Code Llama doesn't actually seem to benefit too much from the synthetic programs. But yeah, this could just be some instability of training as well. But yeah, so just to summarize, I think it's plausible that at this age, LLMs can help end users use tools like Dafny, for example, lowering the cost of verification. Maybe also for specification, though they might also misspecify things, especially for people that don't have the experience doing it by hand or don't understand the system very well. So they might get a program that was proved correct, but for the wrong definition of what correct means. And of course, there's a lot of ideas we could do in this editing pipeline that we don't yet do. So for example, right now it spends a lot of money trying to implement ideas that are completely crazy. And we kind of just randomly sample ideas and so on. Something like MCTS, for example, could very naturally, over time, focus on ideas that seem to be more promising, that seems to be able to keep growing, and so on. We could also just use programs from other languages so that it doesn't have to start from scratch, but maybe here's a Python program, write something that's a bit like this, possible specifications, and so on. And yeah, so I guess maybe the main takeaway here is that there is one possible path to creating good AI assistants, even for languages that haven't had yet large-scale adoption. And that might have this positive feedback loop of a language that has very good assistants might have more people using it and so on. So yeah, that's it. Happy to take questions.
Wonderful talk, great ideas. So you've measured the usefulness of the generated Dafny data by how well it helps to fine-tune the models.
Right.
Can you say something about like a human evaluation of the data set? I mean, are these good Dafny programs? Are these like reasonable specifications, or are these like smileys?
Yes, that's a good question. I think they're a mix. I found very few like completely bogus programs, if at all. I did find a lot of trivial programs and specifications. Like in implementing, for example, a voting system, it would ensure that the new vote is the old vote plus 1, and the implementation of the function is new vote equals old vote plus 1. Things like that. So you get a lot of that. In these more complex programs, usually like in the priority queue example, oops, this one. Usually the specifications make sense, and it fails to like fully verify some of the methods. But I think even the existing annotations, like the invariance that it writes, for example, tend to be sensible. But yeah, I think it's hard to think about like what would be the direct usefulness of this for humans to do a human evaluation. But it would be useful, cool to think about too.
Thank you.
Yeah.
So you mentioned that you use GPT-4o to generate this synthetic data set, but then you fine-tune another model, right? Code Llama. So have you? There is a little bit of a problem with that, right? It's kind of a poor man's technique to steal the weights of some model is you just query it for 1 million inputs, and then you train your own model on what you got, and then you have kind of maybe you've stolen the training. So to what effect, or do you have any way to kind of measure that effect? Or maybe put it in a different way, if you just use GPT-4o initially instead of this code Llama, would you get better results compared to after you did with the fine-tuning with the synthetic data set?
Yes. So we did a preliminary evaluation of 4o early on in this test set, and it did not get 50%. So I think, I forgot exactly. I think it was around what Code Llama got after fine-tuning, like 40. So even this process of synthesizing the data using 4o, combined with the information that comes from Dafny to like filter bad programs and so on, and then fine-tuning seems to do better than 4o alone.
And did you try to just use Code Llama or Llama for the synthesis instead of GPT-4o? I mean, what made you use GPT-4o?
Right. So I did, not super seriously, but I did. And it seems like this open-ended generation for the small models is really hard. Most of they don't generate anything like that's this long and still coherent, for example. Like they try to start to repeat themselves and things like that.
I guess let me try to pose two hypotheses and ask your intuition about which is responsible for what. When you're doing this process, one source of information is GPT-4o that was maybe trained on much more Dafny code than Dafny bench, and we don't know. And maybe it's very smart. And the other is that there is feedback from the verifier here.
Yes.
Right. You're using the verifier to get actually good Dafny programs. And I guess the question is, which one is responsible for more of the effect? Are you just stealing the training from GPT-4o?
Yeah, right.
Or is this generation process kind of getting more information because of its use of the verifier?
Right. So I think, it's unfortunate that we can't rule out one. Like maybe OpenAI has a lot more Dafny programs than we know of. But I think that's unlikely just because it doesn't. I guess one question would be like, where would those programs come from? Maybe they would have to crowdsource, like ask people to write more Dafny programs.
Maybe it generalizes better from other programs.
Yeah, exactly. So I think that's more likely the case. That like it actually sometimes still makes basic syntactic mistakes in Dafny. So I think it's not really good at the language, but it can sort of get the ideas right. So I would say that it's a combination of like having a not too bad, but still imperfect generator, and having the verifier to be able to prune things. So it's likely that like if you were to do a lot more samples on 4o alone, plus using the verifier, you could probably beat the small models even after fine-tuning. But then it's also just a matter of cost.
Let's thank Gabriel again. Our next speaker will be I think it's auto first.
Hey, Yuchen. We've got you pulled up now. Can you try talking and try sharing your screen?
So our next speaker will be Yu-Chan Lee, who is an undergrad at MIT, and will tell us about his internship at Amazon last summer.
Are you able to see my screen?
Looks good. Thank you.
Okay. Then I will begin. Thanks for the introduction. Today I'll be talking about a project I worked on during my internship at AWS using Dafny as an intermediate language for verified code generation. Let me start by giving a rough outline of this talk. First, I'll cover some of the background for this project. Then I'll give a brief demo of the project.
Hi, Yuchen. Can you hear me? It looks like we're frozen from our side.
Viewed as a prequel to Gabriel's wonderful talk, so please bear with us. I wanted to start first. Is it okay to start? We good? Awesome. Okay, thumbs up. Great. So how many people in the room have, I am curious, like have used a large language model to generate any sort of code before? Okay, that's almost, wow, that's almost everyone. Interesting. And how about, has anyone used a large language model to generate specifically Dafny? Okay, fewer, but still a decent number. Great, so this project really was spawned from the idea that there's an underdeveloped synergy between the programming languages community and the machine learning community, as Gabe actually alluded to. On the machine learning side, we think that writing in verification-aware languages like Dafny is a really interesting testing ground for how large language models reason or don't reason about code. And also it's a useful way to make sure that the code that comes out of large language models provably adheres to a given formal specification. And on the flip side, as Gabe mentioned, we think that large language models could help automate some of the tedium, the cost associated with writing in verification-aware languages, again, like Dafny. But we have a bit of a chicken and egg problem here when we think about training systems to write in verification-aware languages, because there's just not that much data. When we look at this table and we think about neighboring tasks or neighboring problems, like mathematical theorem proving or unverified program synthesis, there are many more benchmarks with many more problems. But for formal software verification, at the time of creating Dafny Bench, and there were really only two options, and those were Clover and Dafny Synthesis, which are great in their own respects, but quite small. And Dafny Synthesis is a bunch of MBPP Python programs that have been translated and verified with GPT-4, which shift the distribution, since these are mainly programs that we know GPT-4 can verify with Dafny. So with Dafny Bench, the original mission was to increase the amount of data that was currently available in benchmark form for studying and training large language models. And in order to draw this data from a distribution that was similar to what human programmers write in Dafny, we decided to set a first stake in the ground by constructing Dafny Bench by scraping a bunch of Dafny programs from GitHub. And so we basically downloaded all of the Dafny files uploaded to the site, GitHub, from before December 2023. And we filtered them, as Gabe alluded to, by checking for programs that verified as standalone files, and also that weren't trivial in the sense that they had at least 5 lines of code and included at least one ensures or requires clause. We conglomerated that amount of data with the existing Clover and Dafny synthesis datasets in order to create the largest real, I suppose, benchmark to date of Dafny programs. And the task that we envisioned using with this benchmark, which was taking a program like linear search here and stripping out all of the proofy parts, the proofy annotations in the body of the program. So removing all of the invariant, asserts, decreases clauses in the body of the program without touching the ensures and requires clauses that in the header of this method, for example. And then the goal would be to have large language models add back those stripped annotations. And if the language model is able to replace those annotations with equivalent ones that make the program verify, then we consider it a success. And so this is the benchmark task.
Thank you. Yeah, so I'm going to talk a little bit about the results. This should be the most exciting slide, but it's kind of the most boring, although it might be a little bit spicier now, based on what Gabriel was saying. So we tested what was at the time the cutting edge large language models available. Cloud 3 Opus did the best with 67.8% success on the benchmark. GPT-4 Turbo and 4.0 basically tied with 59.8%. 3.5 Turbo, 44%. Code Llama, interestingly, pretty low, 28%. You might wonder, oh, is it just because it's open source and it's poorer quality? To be continued, little cliffhanger. We found out why. But it doesn't really do any better than what we found the sort of control rate to be, where you don't even use an LLM. I guess this is the spicy part. I'm not sure why it sort of disagrees with what Gabriel was saying. We found 26.9% will succeed where you just take Dafny Bench and run it through Dafny to try to verify. Probably something we have to follow up on with Gabriel. And yeah, with that, hand it back to Chloe.
Cool. So we wanted to break down how models performed when they were given a chance to reflect on their answers without any sort of MTS or Monte Carlo tree search like scaffolding. We just wanted to see what happens when the model reflects for itself on the feedback provided by the Dafny verifier. So we structured this by giving a model a total of 10 attempts, and say I took GPT-4 and gave it like the linear search problem from the beginning slide and asked it to fill back in the strict annotations. It would, let's say that it gave us its attempt. The Dafny verifier said, hey, that's wrong for some reason. We would then give that Dafny verifier error message and the original attempt back into GPT-4o and say, hey, please fix this for us. And then we'd evaluate its next attempt at the problem. So this is what the x-axis represents. It keeps track of that number of iterations, that number of attempts I just described. And the y-axis is the success rate, the number of Dafny bench programs that the model successfully verifies at that attempt number. And we see from the graph here that we experience diminishing returns after attempt number 4. The best model at this appears to be Claude 3 Opus. It takes feedback most effectively and improves until about attempt 4, and then kind of the curve flattens out. It doesn't make much more progress. It would be really interesting to look at models that are known to be really strong at proving mathematical theorems, like O3 from OpenAI, which is coming out soon. It'd be really fun to put O3 through the same analysis and see how the shape of its curve changes, if at all. We also were curious about how large language model performance behaves with increasing complexity of programs. As Gabe points out, the majority of programs in Dafny Bench are quite simple, and that's partly because of the filtering process. We looked for standalone files that verified. But we implement a very, very crude proxy for program complexity, which is the number of characters in the program on the left, and then the number of characters in the annotations of the program, so the assert, invariant, decreases clauses in the program, that's on the right. And perhaps as expected, as the program becomes more complex, the large language model has more trouble verifying it. And to us, this suggests that large language models are okay at doing like one step of reasoning, where the annotations required for making the program verify are like echoes of the ensures and requires clauses in the method's formal specification, kind of like with the linear search example. But as soon as you have more complicated proofs that require multiple steps of reasoning or implementing intermediate lemmas in the process of building up to like a bigger proof, large language models still fall down on this front, it seems.
So we captured all the error logs for each large language model and each file, and we broke them into 9 categories because we wanted to, do a little bit of investigation here. Probably the most important ones for our purposes are code logic error, verification logic error, trivial verification, and altered specification. And then syntax issue might come up in the next slide. But to sort of draw out the distinction between code logic error and a verification logic error, a code logic error is like the type of mistake you might make if you're writing the imperative program where it's like an off by 1 error or something to do with a null object. And then that shows up really nicely in the Dafny error log, that like that's exactly what's going wrong. Whereas with the verification logic error, it just says failed to prove this invariant or this decrease clause, and it doesn't really tell you why. So we distinguish between those two. And it's sort of, the idea is the verification logic error is sort of the core thing we want to test for to see how well the large language models are at providing those non-errored verification logic. We check for trivial verification, which is like a type of cheating that large language models will try to come up with, and we classify that as a failure, even if it did technically succeed. And altered specification, anytime it changes the ensures or requires clauses, we classify that as a failure, regardless of whether it succeeds or not. And indeed, if we look at how the histogram shapes out, the closed source models, when the majority of their errors were the verification logic errors, so it's sort of like indicating the benchmark is keying in on testing the correct thing. And Code Llama mostly had syntax issues. And when we went to investigate it, it comes down to just a calendar issue. Its training cutoff date was September 2022, and all of these were run on Dafny 4 syntax, which came out in March 2023. So don't turn your nose up at open source models just from this result. We would expect, if we were to run it again on better open source models, it would do better.
Seth touches on an important limitation that's worth calling out in the section dedicated to discussion. Data contamination is a problem with Dafny Bench. When we think about how closed source models with later training cutoff dates were probably trained on data scraped from GitHub, which contain solutions to the problems posed in Dafny Bench, and that could artificially inflate the performance of these models on the benchmark. Gabe brought up another important limitation, which is that a decent number of programs in Dafny Bench are pretty simple in the sense that implementations are almost direct reflections of formal specifications. Ideally, that wouldn't be the case in the world's most perfect Dafny Bench benchmark. So ideas for mitigating this, I think Gabe touched on some. Synthetic Dafny is a great next generation of what we're presenting here, and also translating from benchmarks implemented in other languages to increase degrees of separation from what's on the internet and what we're using to test. Perhaps more importantly, Dafny Bench brings up this question of what does it mean to design better error messages or better edit languages for helping language models correct themselves and do better when they write in Dafny? And this is perhaps an echo of an even broader exciting question, which is what does it mean to design languages for large language models and not only humans? For now, that concludes the discussion. Happy to take more questions, but I'll hand over to Seth to conclude with some concrete steps we've taken on applications that we laid out, hopefully, in the original version of the paper as future steps.
So it occurred to us that all the code we wrote for actually running the tests would be useful to Dafny developers if sort of captured and presented in a useful way, because we basically have to take a Dafny file, send it to an LLM API with the right kind of prompt to get it to try to verify, parse that output for just the Dafny file, run it through the verifier. If there's an error, send that back, performing that loop in what is now sort of called agentic LLMs, which is, like a while loop. And so we actually acted on that intuition and built what we're calling Dafny Autopilot, which is a VS Code extension currently available in the VS Code extension marketplace. It's a work in progress, and the way it works is if you're a Dafny developer writing your sort of imperative style code, you maybe don't know too much about the verification annotations, you can right-click and send your code off to an LLM API. You have to bring your own API token, and it'll sort of perform 9 iterations in a loop, sending the error sending 2 errors at a time, because we found you don't want to overwhelm the LLM with too many errors. They'll just sort of build on each other. We're integrated with 3.5 Sonnet v2, Gemini 1.5 Pro, and AWS Bedrock. Should have a new feature coming out soon where you can sort of specify exactly which model and AWS region you want to use. We would really like some early users, to provide bug reports and feature requests in GitHub. Just an example, hopefully this will work in this sharing. It's not going to work. Let's see. Oh, yeah. Okay, come on. No. Never mind. I had a pre-baked, cake, a baking show example, but it's not going to work with the way we're sharing here. Another tool that we're working on, and this is being led by Max Tegmark, is called verilib.org, and it's sort of a generalization of the idea of Dafny Bench, where we want to take a bunch of verification tools, theorem-proving tools, build a big database of formally verified software, and we're writing code to sort of parse it down into the spec code and proof components to sort of be able to generate a diverse array of benchmarks sort of related to Dafny Bench in terms of challenging the model to fill in the annotations. Right now we have Dafny, Cock, or are we calling it Rock these already? And Lean. We're probably going to roll out Isabel really soon. It's sort of limited in that it's a single file upload, but it'll run the verification on the server side, and if it passes, you can publish it. And so we're trying to, create a watering hole for the community to contribute to a sort of growing database of verified software. So that's all we have for now. We're happy to take questions. Thank you for your time.
So just to clarify, when you were collecting Dafny files, you said you look for ones that were standalone files, and then if there were dependencies inside the file, did you sort of identify which dependencies needed to be fed in? And if so, did you run into like context limitation problems?
We did not do that. That would be a great next step if you want to contribute to a more complex Dafny bench. No, we didn't.
So you were just looking for a file that had a standalone that would verify with no other context?
Correct.
Thanks for the talk. I know that Dafny has like an experimental feature where you can show a counterexample if verification fails sometimes. Did you incorporate that into like your procedure of passing that error message to the LLM?
Once again, we did not, and would love to see your submission to Dafny Bench.
Does anyone know how to change which slide is shared or which screen is shared real quick? Since we have like a minute.
I think we're already running over time.
Oh, okay.
Pretty much. So, but thanks a lot for the great talk. So let's thank you again. Should we try to go back to Yu-Chen? I think he's back online.
Yeah, I'll try sharing my screen again and keep my camera off this time. So if it was a bandwidth issue, hopefully it won't fail again. Yeah. Is it visible now?
Just give me 1 second, real quick. Perfect. That looks good. Thanks, Yu-Chen.
Okay. Yeah, sorry about the issue earlier. So I'll begin. So as I mentioned, I'll be talking about a project I worked on during my internship at AWS on using Dafny for verified code generation. And I'll be beginning with the background, followed by a brief demo of the prototype we built, as well as explain some key implementation details, and finally discuss our future work. So beginning with the background, using an LLM to generate code from natural language is clearly a very popular idea, and there are many projects that are pushing the envelope on this. Unfortunately, it is not uncommon that LLMs confidently generate code that is suddenly wrong under close examination. So for example, here on the left, you can find a prompt that asks an LLM to generate an efficient Python implementation of a sequence that is similar to the classical Fibonacci sequence. It differs from the classical definition in that in the recursive step, one takes the sum of the last 3 entries instead of the last 2 entries. On the right, we see LLM synthesized code that seems to correctly address the prompt on the left. However, if you look at it a little bit closer, you'll realize that there's in fact a subtle error that causes the code to return the wrong value when n is greater than 2. We will revisit this example again later in the demo. This year, Dafny has become increasingly popular with research at the intersection of LLM-guided code synthesis and software verification. You could say that Dafny guided code generation lies somewhere in between traditional program synthesis and proof synthesis for math problems, which, for example, DeepMind's offer proof targets. One line of research explores prompt engineering and search-based approaches. Here, we have been particularly interested in a paper that uses few-shot prompting to improve the quality of generated code. Another line of research leverages Dafny to catch incorrect code, or to automatically synthesize specifications. Here, we're particularly interested in the consistency checking described in the Clover paper. Now, let us take a look at our current prototype. Before we watch the demo, let me give you a high-level idea of how we integrate Dafny into the code generation workflow first. The LLM, we start on the left with the natural language input of the user, and then the LLM formalizes the prompt in Dafny and returns to the user a natural language translation of the specification. The user is able to give their feedback from the formalization, and the natural language conversation between the user and the LLM continues in the loop until both sides have agreed on a formal description of the problem. This provides a transparent notion of correctness that we can validate a solution against. In the next step, the LLM then generates an attempt at the solution and a proof of its correctness. The Dafny ecosystem will either accept the candidate solution or reject it, in which case it will allow the LLM to refine it or perhaps start from scratch again. This process continues in a loop until a solution appears, or the number of iterations hits a bound that we chose and it gives up. This step is completely automated. Finally, once the loop has converged, the Dafny ecosystem generates additional unit tests for the solution, and it uses its compilers to translate the solution to the target language. In our case, this will be Python, but this could also be Java or JavaScript or any language backend that is supported by the Dafny compiler. The compiler output then may be further optimized by an LLM, for example, to improve readability. Finally, as seen on the right, the user is presented a specification of the problem, an implementation, and unit tests, all in the target language. The correctness of the solution is implicit, as it was present in Dafny and has been preserved by the translation. Let us now watch the demo video. We are running a Python chatbot based on Cloud 3.5 Sonnet that was modified such that it uses Dafny under the hood. During the whole conversation, Dafny will remain fully opaque. My prompts will have a white background, and the AI responses will have a gray background. I start by prompting the chatbot with the same inputs that I used for our FibFib example earlier. After a few seconds, the chatbot will respond with a formalization of the problem. This will be a natural language summary of the underlying Dafny code, which is opaque to the user. The slight delay comes from a loop in the background that ensures we only return code that is runtime safe and verifies. Observe that the summary mentions 4 base cases, but in our original prompt, we only had 3. This is because there had been a typo in my original prompts that caused the definition to not be well defined, and the LLM has attempted to fix it here by providing the missing base case. So before continuing with the implementation, I corrected the typo, saying that the last term should be n-3 instead of n-4. The LLM comes back with a new specification of the problem, which looks correct, so we accept it and proceed with the code generation. The next step involves generating an intermediate Dafny program from the specification, but this is hidden from the user. We only see the final result after it has been translated to Python. As you can see here, the final Python program contains an imperative method fibfib, a recursive function fibfibfunc, and a main method with the user-provided test cases. Note that it also includes the additional test cases that were generated by Dafny in the main method. Alright, and that's it for the demo. Let's briefly compare the two solutions we have encountered so far. On the left, you see the directly generated Python code from the start of the presentation. It was directly generated by an LLM without going through Dafny. On the right, you see Python code produced by our prototype, which uses Dafny as an intermediate language. The output consists of an imperative implementation, a functional specification, tests that were provided by the user in their prompts, and additional tests generated by our tool. The program is runtime safe, and its correctness is implicit through a proof in Dafny that we generated. The two solutions are almost identical, but note that there is a difference in that the program on the left incorrectly returns fib value 0, which would correspond to returning incorrectly A on the right. We've only seen one example so far. Let us now look at some of the broader testing that we have conducted. We've evaluated parts of our pipeline on Human Eval, which is a state-of-the-art benchmark for Python code generation. In the evaluation, we skip the first loop of the chatbot implementation that allows a user to iterate in natural language towards a specification. Overall, the results are promising. On a set of 164 tasks, the prototype converged to a candidate solution in 144 of the test cases. Hence, this allows it to pass up to 88% of the tests. This is comparable to direct Python code generation, which passed the test in 86% of the cases. These results are surprisingly good to us because there's almost no training data available for Dafny. So for example, on GitHub, there are over 15 million repositories that contain Python code, but only a few hundred repositories with Dafny code. It is also worth noting that after we moved our experiments from Claude 3.0 Sonnet to the newer model Claude 3.5 Sonnet, we saw a dramatic increase in the syntactic correctness of the Dafny code generated. This had previously accounted for a large class of errors. There are still plenty of opportunities to improve these results further, for example, by synthesizing Dafny code for training and fine-tuning. Now that we have seen the results, let me talk about some of the key implementation details. First, prompt engineering. We use a system prompt to provide the LLM with high-level rules that help with code generation by addressing different error classes. First, we stated the LLM's role. In blue, we then specified the LLM's task, given a prompt that contains a docstring and pseudo Python code, generate from it an equivalent Dafny program. In purple, we specify a format and constraints for the output, so we can extract the generated code and test them automatically. In orange, I explicitly add instructions related to Dafny syntax. For example, I instructed to generate a Dafny method instead of a function, which helps with the LLM mixing up the two due to the older Dafny syntax. I also hinted to use the option data type to handle Python functions that could return none. Finally, I tell it how it should translate test cases into Dafny code that can be checked at runtime. Moreover, we also use few-shot prompting. That is, we provide generic input and output examples to guide the LLM towards returning a Dafny program that has the right structure for further processing. On the left, you see the type of input that the Human Eval benchmarks provide the tool with. It consists of a function signature, a docstring, and a few test cases, all in pseudo Python style. On the right, you see the type of Dafny skeleton we want the LLM to translate the inputs into before we use it to fill in the part that is currently axiomatized. Notice how the docstring and the function name are preserved and the test cases are translated into expect statements. Given the skeleton you saw on the previous slide, we then use feedback from the Dafny verifier and compiler to iteratively converge towards a provably correct implementation. Initially, the example here, which is a bit more complicated than the initial fib one we looked at, fails the runtime checks since the method is not implemented yet but verifies successfully. The LLM then proceeds with the first attempt and definitely returns some verification errors. Taking that into account, the LLM then adds an assert statement, which ends up resolving the first error. However, the second error is a bit harder to resolve, and even with the feedback, the LLM does not get it right on the next attempt. Or even the following attempts, although it does end up simplifying the code a little. Eventually, however, it figures out the right assertions to write, and Dafny is able to verify and compile the code successfully. After we have generated this Dafny implementation that correctly implements a specification, we must still post-process it to eventually get the target language implementation. To achieve that, we first use Dafny's native test generation capabilities to synthesize test cases in addition to the ones that were already provided by the user in the prompt. Then we run the Dafny compiler on the generated Dafny code and test cases. Doing so, we're able to obtain their respective Python versions. With that, let me wrap up this talk with some of our ideas for the future. An issue that we struggle with is that the code produced by Dafny's compiler tends to not be entirely idiomatic and requires a Dafny runtime library. One possible solution to this is to use a different, more idiomatic compiler. However, such compilers are not available for all the language backends yet. Another possible solution one can imagine is that we can perhaps post-process the code, and doing so it could improve the readability as well as we can do so using heuristics or even another LLM. Of course, we'll still want to keep our correctness guarantees, so if we were to proceed with this approach, we'd also have to check for semantic equivalence. Finally, another consequence of depending on the Dafny runtime is that the generated code is not always interoperable with native code. So for example, on the left, we have a simple Python code sample returning a list with mixed types. So to model this in Dafny, we'll have to use a custom data type as seen on the right. So while this will compile to working Python code, it cannot be directly compared to the generated Python classes cannot be directly compared to native Python types at the moment. And with that, I have come to the end of my talk. Thanks for joining, and I'm happy to take any questions.
Let's see if there are questions.
All right, let's thank Yu Chen again. And with that, we come to the last talk of today. I'm not sure who the speaker is. Gabriel? Okay. So the speaker is Gabriel Ebner from Microsoft Research.
Okay, does this work? Okay, well then let's try this. Okay, so we're already a bit over time, so I'll try to stick to the important parts. So first of all, thank you all for having me. This talk is at the end of the day. It's already, the Dafny is already a bit over, and this talk is more about like F star. So so I want to tell you about our work on doing like machine learning and LM generated verification in F star. It's going to be similar to Dafny in the sense that it's SMT verified. And I'll try hard to point out learnings from this that are more broadly applicable to other languages like Dafny. So let's get right into it. So in a sense, F star looks a bit like Lean or Cog or Dafny in the sense that like you've got code, it has types, and like whenever you need some verification conditions in your code, it gets sent to C3. However, F star is a bit more syntactically difficult than Dafny, and I've just put on a small example of F star on the slides, which is a quick sort function. It's defined recursively as a functional program, and it's defined using recursion. It calls to some lemmers, I guess just as you would do in a Dafny program. And the task that we have been investigating and trying to see how well do models on that task is the simple task where we give the model like a description of the problem in the form of like the name of the function and its type, and ask the model to generate the whole definition and see how well they do on that. Okay, so for that task, we've done two big things. One is to gather a data set of F star code of like verified program code in this SMT-assisted proof-oriented programming language, and then we've trained models on it and evaluated them. So let's first get to the data set. So I guess like the big difference here is that we've been trying to gather like every single F star code, F star project that we could get our hands on that is on GitHub. That, you know, papers that were written 5 years ago, we tried to port it to the current F star version, and in total we get about 1 million lines of code. So we're not just focusing on like standalone files. We're making an actual effort to learn from code that is like in the middle of some repository, and we're trying also like trying to learn from stuff that's in the middle of a file, and so we can really make use of like the whole code base that is out there, and this spans like a lot of different topics. I mean, some of it is like, you know, something that you would reasonably expect an LLM to generate, you know, some easy lemmers about lists, some easy like recursive functions, sorting functions, and then it also contains stuff like verified crypto implementations, and various distributed algorithms and separation logics, and well, you know, you just put everything in there and then you see how well it works. So one complication that we have in F star that might or might not be that visible in Dafny is that a lot of things in F star, just like STR in Cog or Lean, are syntactically the same. If you have a type, if you have a proposition, if you have a lemma, if you have a program, they are all just first-class values in your language. And syntactically, they look very similar, almost the same, which is great because you can have a list of types, you can have a list of proofs, you can have a list of propositions, you can have a list of programs, and they all work the same. But for our evaluation purposes, we needed to classify those definitions because, well, we expect the LLMs to do differently depending on whether they try to synthesize like some type or whether they want to synthesize a fully specified program. So I've given you some like stereotypical examples here in F star syntax, right? So you can define refinement types, and those are like just first-class values, and they look the same as a simply typed function that just takes two natural numbers, gives you another one, and does not have any other specification. It could return 0. It could return 42 with a comment as a smiley, or it could add them. Like you cannot tell from the type, and so the task that we're evaluating on, generating a type-correct definition, is going to be relatively easy. And then you can also have like theorems that are also introduced syntactically in the same form, and where you might these theorems, they can be arbitrarily hard, and in particular, like for these theorems, it does not matter what the model generates as long as it checks in F star. It's good, and we are accepting the output. And the same goes for intrinsically typed functions and programs, where the precondition and postconditions already constrain the program well enough that we can say that, hey, if the model can generate an implementation that is type correct, then it's probably going to be good. And in total, we get like 3 different classes of interesting definitions here. One is like simply typed programs. Those, I mean, it would be nice if the model can generate them. In practice, it turns out that models still struggle with that. Then there's proofs, where you ask the model to exhibit some proof term that verifies a theorem. And then also dependently typed programs, which we kind of assume that they have a good amount of specification on them. It is all a bit heuristic, but we can see clear differences in our evaluation. And in addition to like the the just plain old data set which does nothing, we also include a whole harness to check the proof. So like given such a type definition and a body, it actually like packs up all the stuff of calling the verifier and making sure that there is like no assumes in there, no admits, that it actually like gets the doesn't modify the type of the definition. And there's a nice Python API around it, and we used it for our evaluation. And as another cleanup step in our data set, we filtered out definitions that are super easy to solve, where you don't need to call any external lemmas, where you can just have essentially the empty definition, like even in Dafny, like just curly braces. And if that already verifies without doing anything, then we filtered it out from the data set. So everything's really non-trivial definitions. So to sum up like this, V1 part of the data set, there is, various tens of thousands of definitions, and they are somewhat evenly split between simply typed, dependently typed, and proof definitions. And maybe a point to our data set split. So we have a somewhat very interesting data set split. So since we're not considering standalone programs, we are considering like whole developments, we need to take into account the dependency graph of the problem, of the projects. And our training split actually like respects that split. So the training set is one with that. So if you like look at the dependencies, there's no dependency from the training set to the test set. And then we have also additionally extra hard test sets where we held out whole projects to test them on. So like I don't remember exactly what we excluded, but for example, if we excluded I don't know, meet TLS star and verified implementation of TLS, then we would not fine-tune models on that particular project and only evaluate it there just to prevent any particular contamination. What we did not control for is accidental contamination, so where you have like 2 files that are very similar, like somebody is talking about uint32 and others talking about uint64. This can also lead to some contamination. We did not control for that though. Okay, so much for the data set. Right, we've got lots of data. We've trying to take this whole project developments into account, and we have a dataset split that really respects the dependencies. And from that, we've done evaluation on trying to predict those definition bodies from their types and names. And so there are some key ingredients in how we set up the prompts here. So since we don't just have a single file, but like whole developments, we can't just pass the whole development to the LLM. We need to filter it down. And so there is, we've done various things there. So one is we're using a kind of retrieval augmented generation where we find some related looking definition from the library. And we do that by taking an embedding of the type and the name, so like, the whole thing at the top, like the function signature, and then finding function in the library whose embedding looks similar. And let me just pick the top one. No, not the top one, but as many as fit in our small context window. So this is like an important part about retrieval augmented generation. And then we also add the names of some premises that look plausible and interesting. So the thing is,
if you put in like the whole definition in the library, then this takes up a lot of token space, a lot of space in the context window. So you can only get like a limited amount of information there. But if you only pass the name, then the model can still roughly guess what it should do, but it takes up a lot less space. And for that, we trained an actual custom embedding model. Again, trained on a data set. We know, hey, what names are being used in definitions, and we train a model to predict those names via embeddings. And then finally, we add what the model should generate, like kind of the type and the name of the definitive function signature. I guess one thing that I forgot is that we also include like the whole preceding contents of the file. So if we try to evaluate on the definitions in the middle of a file, we also include the first part of the file, or at least as much as fits into the context window. Okay, and with that, we can look at how well this does. And the surprising thing is, okay, so this chart shows us how well the 5 different models do on those 3 classes. So what we first see is that, as expected, simply typed definitions are much easier to solve, although nowhere near 100%. And like the dependently typed ones and the proofs, they are significantly harder and with a lower success rate. And what we are measuring here is like a pass attempt. If we do 10 independent attempts at solving, predicting the definition, this counts the number of problems where at least one of those predictions checks without an error. And the interesting thing, so okay, let me explain one more thing. So the first 2 bars, the blue one and the orange one, they are GPT. 3.5 and GPT-4. And the other bars are smaller models that we evaluated and then we fine-tuned. So the solid bars at the bottom are the off-the-shelf versions of those. It's Phi2, Orca2, and StarCoder. It's already a bit older, this evaluation. And then the non-solid one above, that's the results that we get via fine-tuning. And so the really impressive thing here is that if you fine-tune like small model, in this case like StarCoder, then we get a performance that is almost as good, even better in our case, than if you use a GPT-4 off the shelf. At, of course, much lower cost and much more accessible on your own machine. Okay, and this is maybe another like just interesting diagram, is that we can actually like see what the models learn while fine-tuning. So what we see here on this chart is the distribution of errors when running the models. And so like the big blue thing is syntax errors. And what we see on like the models on the right is that this blue bar is almost everything. So like an unfine-tuned Phi2 or StarCoder, it makes a lot of syntax errors. You know, like what we've heard before, like missing parentheses and so on. But if we fine-tune it, then those syntax errors almost go away. And in a sense, what we see here is that the model during fine-tuning learns how to write syntactically correct code in our language that it wasn't part of its training set, where we have very little data. And the other important takeaway here is that retrieval augmentation is really, really important. Just adding this extra context to the prompt of, hey, this is a relevant definition, and hey, this is the previous content of the file. I mean, this helps enormously. So the first line in this table here shows us how good the model is with all our like augmentations applied, and like this is a Phi2 model. It's small. If you try all these permutations, then you want to have a small model that you can fine-tune quickly. So this is not the best one, but the one that we can train pretty quickly. And so like the first line shows how well it does with all of these optimizations applied, and there we get I don't know, like in the intra project column, like 31%. And if we, for example, drop the file content up above the current definition, then it drops to 21%. If we drop the related example, then it drops to 26%. So like just adding these related examples in the context helps enormously. Okay, this is very much like initial work. We've submitted it, well, so it's an article at this year's ICSI. There's also like an extended technical report available. And from here on, we have some ideas on how to take this further. We want to cut down on identifier errors using monitor decoding, using where you, during inference, force the model to only generate valid identifiers by modifying the generated probabilities for the next token. We are looking at evaluating repair. Right now this is just like one shot, and as we've seen in the talks before, taking into account error messages helps enormously, so that's something we want to look into. And right, and another thing that I think people here are doing really great is like removing assertions from programs and trying to infer them again. That's also something we want to look into. And like one more thing that we want to do is, so right now we're generating like these whole definitions in one go. And what we see is that like the longer these definitions get, the harder they are for the models to predict. So what we want to do is try to find ways to split this up so that we can, I don't know, like generate like one statement at a time. This is unfortunately a bit harder because FStar doesn't really have this statement-like structure that Dafny has. Thank you so much. If you're interested, we have a Zulip chat and a website, and thank you.
I guess one thing that's really nice about this is that you're not restricting to single procedure or single file, unlike a lot of LLM works in Dafny or in Rust. Do you think the techniques that you use to do that would generalize to other verifier, like to Dafny or
Yeah,
Rust
I'm
and
like,
Verus?
that's kind of the thing. We're not doing really anything F-star specific, except for trying to classify like those definitions. Everything else should apply pretty much the same way to Dafny, I think.
Another small question: the 50% success rate on simply typed functions, it's just that synthesizing some function of that type?
Yeah. There's no constraints on it, right? So we're trying to only generate a single definition, so we're not trying to generate any proofs after it. So this is really the success. Hey, can the model actually write down a function with that type?
But then, now the 50% looks like a failure. I mean, if I just give you a type, how hard can it be to just synthesize that? Why is it not 100%?
Also, the thing is that you're in the middle of a whole development. Like if you get like a definition that says I need to produce a foobar object, then you don't know, is it a mk underscore foobar? Is it, you don't know what definitions you have. You actually need to find like the correct definitions to be able to construct it. So like, yeah, on a theoretical level, this should be as easy as, looking through a library and trying to put together functions. But in practice, it's really like you don't know what those functions are. You don't know how big the term is going to be.
Thanks.
So early on, you showed a list of the F-star projects you were pulling from.
Oh, sure.
I was just curious, you might hypothesize some of these are easy projects and some are hard projects. Do you actually have any data to show which ones the LLMs did good at?
I'm not sure if I have actually any data on that. At least not any data that is ready. I mean, I guess like typically you see some difficulty changes there. I'm not sure how representative they are. It might be that, I mean, like even like these more complicated projects have parts that are like, like some support libraries. And I would imagine that like this is just quantifying like how much support libraries you have there.
Take this opportunity to ask my colleague about this really. So I'm just curious as to when you run the small models, augmented small models compared to say GPT-4, can you say something about the cost benefits?
So I mean, I don't have the dollar numbers in my head, but like GPT-4o does cost you more money than like small models, that's for sure. And the other thing is that you can run those small models on your own machine or on your own hardware, which frees you from like this whole accounting thing of who buys for the credits.
Thanks.
Well, let's thank Gabriele again. And with that, we came to the end of the workshop today. I would like to thank again all the speakers for a diverse set of talks, all very interesting. thank all the reviewers for volunteering and everyone for joining today. And I hope to see you next year.